Oh, sorry. I was like actually on the double.
We're gonna wait before we're gonna be prepared, so.
I thought it just like a slightly weird sensation. But... I think Zoom works. Yeah, it works. And I hear myself.
Hello.
I can. USB Type-C. مش شغال معايا كويس، هو ده يبقى جاي محتاجه عشان بس خلاص اجيبه. متهيألي انا مش Can I try it? Can I try plugging mine in? Excuse me. Could I try plugging it in? Sorry.
Do we need لو الناس هتخش بده هيبقى في مشكلة لو الناس معهاش.
ما هو دي نقطة.
الناس هتشير هتسيب ده.
هنجيب ده نحط هنا وهو يحط اللابتوب بتاعه هنا ونشير سكرين ونتكلم بس نضيف كمبيوتر اوديو عشان خاطر ما يبقاش يبقى الاوديو ممكن نضيف كمبيوتر اوديو من هنا ويتكلم من هنا. طيب بس انا هكتب خد انترست. هو ممكن يشوف كده على طول. هو ممكن كل واحد يكون مش كومفورتبل ان هو يجي لك. Right. Welcome everyone to the fifth workshop on closing the loop between vision and language. Actually, before I start, I would like to express my gratitude and give my token of appreciation for the long journey of this workshop. It has been happening since ICCV 2015, and every 2 years there has been tremendous effort to make this workshop happen. And part of this journey was a lot of people to thank, including, for example, Marcus Rubrick, Anya Rubrick, Alini Saigal, Ahmad Al-Gamal, and many others. So I'd like to just take this opportunity to thank all of them throughout this journey. Andrew Brown from Oxford and many others who has been contributing to this workshop, and of course all the speakers from previous series who have contributed with talks, challenges, and all the presenters as well of the in the poster session or participant in the poster and oral sessions that contributed a lot to the engagement and the value that this workshop has offered over the past almost 8 years. Before I start, I'd like to thank also the organizers. This work wouldn't be possible without the hard work that has been put by my dear colleagues or organizers, Gamal, Kalish, Zain, and Angel. We have a really rich program today. We have speaker 7 fantastic talks by real people who are in the forefront on this in this area. So where all of us are looking forward to their talks and to learn from them about what's next in this area. We have 3 challenges in this workshop. The first challenge is about scientific figure captioning, and this will be led by Kenneth Wang from Penn State University. That will happen at 9:15 a.m. And then there's another visual dialogue based emotional explanation generation challenge that will be presented by Kalish. And it's about generating explanation on top of 50K visually grounded dialogues, aerial vision and language navigation challenge that will be offered by Zenek Eric Wang team. And it will be about basically extending vision and language navigation tasks to aerial environment. For the poster session or the papers that has been contributed to this year's workshop program, we have really more than 30 4 accepted papers. Almost like half of them in archival, half of them are non-archival. We selected 6 of them for presentations, but it was a hard selection. All the papers that has been like presented or submitted to the workshop are really adding a lot of value to the program. So this is a glimpse of these papers, and please, just to clarify, the poster sessions like they will happen from 10:15. These are the opportunities for us to engage with the poster participants. So from 10:15 to 10:45, and from 12 to 1:30 during lunch, people are welcome also to use some of that time for the poster participation. And during the afternoon coffee breaks, so we have 3 opportunities to engage with the poster participant. You can actually hang your poster anytime from now on, like maybe the next break or something like that. Feel free to hang your poster on the poster boards that are around you in the back of this room. All right, and the selected oral presentations are this. The way it will work basically is it's allocated. 6 oral presentations are allocated 40 minutes. They are divided into 2 halves. The first half will be 3 talks. Each talk is 5 minutes. So after 3 talks, this is about 15 minutes. It will be 5 minutes of live Q&A. That could be live either in person if the participants are here, or through Zoom if they manage to make it. So the second thing, after the first half finishes, then the second half will start. We will play the recordings of the second 3 talks for 15 minutes, and there will be another also 5 minutes for live Q&A. And then we will conclude that by a panel discussion that will start at 5:15 p.m. up until 6 p.m. And with that, I would like to pass it over to my friend Angel, who will manage the morning session and introduce our first speaker. Thank you very much for your attention.
I need a USB interface. Normal USB? No, this is like
Wait a few minutes.
Okay, I need to know that.
Switch the setup.
Maybe the key is needed. Okay, maybe the USB stick is needed. So I don't know how to handle this. Okay, maybe this is for this, right? This is for this, right? Yeah, we need it for this. Okay, perfect. Yeah, thanks. I think he's gonna share it. And it's live streams.
Yeah. My suggestion come here. My suggestion
Okay.
So now this sorry, this
Yeah.
can only, this is also only sharing the screen.
Okay. So I should have my video on too, right?
Yeah.
Okay.
Okay. Okay, I think we're ready. Sorry for the small delay. I'm delighted that to introduce our first invited speaker, Ranjay Krishna. Ranjay is assistant professor at the University of Washington. His research is at the intersection of computer vision and human-computer interaction and aims to bootstrap machine learning using frameworks from behavior and social science. Prior to his current position, Ranjay received master's and PhD degrees in computer science at Stanford. I met Ranjay at Stanford and had the pleasure of collaborating with him on a project that brought together vision language way back in 2015, when this kind of work was much less fashionable. And Ranjay's work has received numerous awards in the vision, HCI, NLP, and machine learning community. So let's please give a warm welcome to Ranjay.
Thank you, everyone. Thank you for coming for such an early morning session. So my talk is very much geared towards what this workshop is about, which is closing the loop between language and vision. And we're going to be talking specifically about a framing to sort of go about doing that. And that framework that I'm going to be introducing is called socially situated AI. And we'll talk about exactly what that is in the next couple of slides. Okay, so far, just to, put ourselves in the same sort of setting for what the expectations are. Today, we've gotten a bunch of computer vision models that work very well. They work really well at identifying a ton of different objects. And this is really exciting because we can enable a whole host of different applications. But our world is a lot more richer than just identifying those individual objects. People constantly surprise us when we go outside on our day-to-day with all kinds of new performances. They repurpose items for new use cases. They find themselves in predicaments they've never seen before. We see them using equipment we've never seen and in ways we haven't really imagined before. And even animals sort of surprise us with their fashion sense and even by their unexpected agency. And all of these new situations that we have all around us, we can interpret and understand all of these situations very, very easily. And our machines still have a very, very hard time doing it. So despite an amazing decade where we've had a ton of advancements in computer vision, all of these models that we have today, they completely fail whenever a concept is missing from their training data. And we've seen this happen over and over again, where we deploy AI models out in the real world, and whenever they encounter something they haven't seen before, they completely fail. And this kind of a phenomenon is something we could easily fix. It doesn't have an easy fix, because our world is constantly changing, because the concepts that we want our models to recognize, they themselves are changing. If you look at some of the traditional data sets in which we train our models today, things like MS COCO, the computers and phones in that data set are very different from the way they look today. And so within the last couple of 5 years or 6 years or so, we've completely changed a lot of the ways the products and equipment that we work with and expect our models to recognize to look. But aside from that, we have whole different kinds of products. We have new kinds of species that we've discovered. And so basically, regardless of how much we try, there will always be concepts that our models will not have in their training data. This isn't a fix that you can have, so we need to build around it. Now, this is something that people are very, very good at. So we know that people can recognize all kinds of things in new situations. And whenever they encounter something they don't recognize or understand, they can learn about those new concepts by asking people questions. And we know this phenomenon from a psychological point of view. For example, social development theory tells us that whenever children want to learn something new, they ask questions. They ask questions to more knowledgeable members of society. And through this question answering situation or encounter, they learn about new concepts. And now when they encounter those new concepts out in the real world, they have a way of recognizing. And so this ability, this human-like visual intelligence that can learn and continuously acquire new information, that's something that's really, really hard to do. And it's hard to do because we need to rethink how we sort of design reinforcement learning algorithms, how we design agents, how we design entire learning mechanisms so that they can actually continuously learn in the real world. And even like the big systems that we have out today in the world, things like ChatGPT, they are also continuously learning. And they've also recognized that you need to continuously have people go ahead and train them. So even RLHF, which is a phenomenon that is currently being used to train and update your GPT models, those are being used with real people interacting with those machines. So how do we do that? So inspired from a lot of ideas from human learning, a lot of my research really investigates ways in which we can learn about the visual world through this process of learning from others through human interactions. So a lot of what I'm trying to do is trying to move AI agents outside of their training from fixed static training data sets by training them out in the real world. And today specifically, I'm going to be talking about a paper that we published at PNAS less than a year ago, where we introduced a framework and a deployment that actually goes ahead and does that. And at a very, very high level, if you don't remember anything else from today's talk, the thing to remember is that what we do is we develop a framework that's inspired from social development theory that allows us to sort of build agents, deploy them out in the real world, and have them ask questions when they encounter situations they don't recognize. And through that sort of dialogue, learn to acquire new information that is absent from its current training data. And over time, these active agents become able to learn not only new concepts, but also learn how to interact with people in real social environments. So the roadmap for today's talk is going to be 3 parts. In the first part, I'll design a framework, which we'll call socially situated artificial intelligence. And within this framework, we'll be designing learning objectives that will enable these agents to actually interact with people in the form of question answering and learn new concepts out in the real world. And finally, we're actually going to deploy this thing out in the real world, where we're going to have about, we interacted with somewhere over 1 million people out in online social media platforms to actually train these models out completely in the wild. And so each ablation of our model interacted with and trained using about 230,000 people. Okay, so backing up for a second, now that we have our roadmap, the reason that current models fail is because they are currently being trained using a paradigm that I like to use this metaphor for. Today, a lot of learning happens as if the agents are locked in a room alone with a stack of books. And we collect these books in the form of data sets or large amounts of scraped amounts of data, and then we feed them to these agents, hoping that it'll learn everything it needs to when it goes out into the real world. And like I said, it doesn't always do that. Whenever there are situations that it identifies something it hasn't seen in its training data, it completely fails. And of course, you can ask a question to try to maybe learn about this, but learning to ask questions is itself a very, very challenging thing to do, because it requires solving 2 primary technical challenges at the same time. The first challenge is that the agents need to learn how to interact with people. What I mean by that is that there are some kinds of questions that are just not informative. So asking a question like, what color is the grass is probably not going to teach the agent anything new, because it's probably already learned from its training data that grass is often just green. And similarly, asking questions that are difficult to understand are also probably not going to help the agent, because no one will actually understand what the question is asking and want to respond to the agent. So for example, asking the question, is the person sitting behind the person guiding the elephant holding the right hand or their left hand up to their eyes? That's a really difficult question to actually parse for us. And parsing that question is not something that all of us want to do on our day-to-day. And so you're probably not going to respond to an agent if it asks you that question. So these 2 goals, these 2 technical challenges need to be solved at the same time. So these 2 challenges are that if you want an agent that is socially situated and can learn out in the real world, it needs to be able to learn how to interact with people in order to learn through those interactions. So it's simultaneously trying to solve these 2 goals of entering to learn and learning to interact. Okay. And if you don't simultaneously learn both of these 2 things, this is what ends up happening. So let me show you an example of an agent that is only aimed at trying to understand and collect as much data as it can about the world. It asks questions like this. It asks, is that food? And that might sound kind of rude to somebody. So if you've taken a photo and uploaded this online, and I posted, is that food? It might sound kind of rude. Other questions might be too obvious for anyone to want to answer. Some questions might require way too much cognitive effort for us to actually want to answer. And then finally, there's some other kinds of questions that are so difficult to parse, again, that nobody wants to answer. They violate Grice's maxims, which says that we want to be able to ask questions that get directly at the point so that people actually listen to us and respond to us. So this is what will happen if you don't train an agent to learn how to interact with people. But what we do is we introduce a framework, which I'll go into, and let me show you some examples. So jumping ahead a little bit, the kinds of questions that it ends up learning how to ask. So it learns to ask about green vegetables. So what is a green vegetable? And it learns about bok choy. It asks about the type of dessert and learns about coconut cake. It learns to ask about specific species of birds and asks about what kinds of objects are on a table. And you can see from all of these different responses that the responses are quite varied and people respond with all kinds of different things. They give you the answer, but in a lot of our cases, we found that people give you more than just the answers. They also give you some amount of sentiment behind how they feel about that interaction as well. They give you emojis, they give you entire paragraphs sometimes, telling the agent as much as possible. And again, these are people completely online, unpaid, and no reason to give you any data. They have no reason to respond to you. This is only because our agent has figured out what are the kinds of questions that people actually want to respond to. Okay, so that's the framework. So let's dive into it. Let's talk about exactly how to go about building out the sort of learning mechanisms and the systems so that this entire agent can actually work in the real. So again, stepping back, the traditional way in which we train AI agents today is 2 steps. Again, I'm simplifying machine learning quite a bit here. You collect data and then you train with that data and you deploy it. Now we start off with this traditional first step. We collect some amount of data and we train something. And then once we have that model, we deploy it out in some social environment. And then we look for things that people are posting about. So we're going to run an image that contains something that we don't recognize. And when we do, we send that over to our socially situated agent that learns to ask a question about that image. And if people respond to us, we parse that response to extract the answer, and we send that answer back as a new additional data point for our model to learn. And then aside from that, we also take every single interaction that we have to determine whether it was a good positive interaction or a negative one. And the positive and negative interactions will help us decide what kinds of questions people are actually interested in answering and which ones people are not. And this is important because every single social environment that you're part of has its own set of norms and guidelines. The way we talk to one another at ICCV is very different from the way you talk to your friends at home. And so knowing the norms and exactly how people want to interact is very important. And this isn't something that you can necessarily hard code. A lot of these things are completely implicit. So these agents have to discover these implicit social norms completely by themselves. Okay, so let's take it a step further. So how do we actually generate these questions? The easiest thing that we can think of is train this entire thing as a simple policy that takes in an input image and learns to generate questions. And we have a ton of models that do this kind of stuff today that takes in an input image and outputs a distribution over tokens that when put together gives you the question that you want to ask. And because you have variational kinds of models, you can generate hundreds of different questions from a single image. Okay, and we trained our initial model with using data from Visual Genome, which had a bunch of images with somewhere around 1.7 million questions. And we use that data to learn how to ask questions in the first place. Now, of course, there's a lot more that goes into figuring out how to ask questions for deployment because you have to clean up data sets a lot. There are tons of questions that are just not okay to ask a person, even though they're okay to have in a VQA data set. And so we did a lot of manual filtering before deciding exactly which question should be used by the agent when pre-training it. Okay, so now we have an agent that can ask questions, but over time, it needs to learn how to ask better and better questions. And so to do that, it needs rewards that helps guide its question asking behavior. And we designed 2 rewards to optimize for the 2 goals that I was talking about. The first reward is this knowledge reward. So every time it generates a question that is hard for the current vision model to answer, it gets a high reward. Those are good questions to ask. And then we have an interaction reward that incentivizes the agent to produce questions that people actually respond to. So it looks at all the past interactions that it's had and identifies which interactions are positive and which ones are negative, and then learns a binary signal to determine how to guide the agent towards asking better and better questions. And for the knowledge reward, we sort of model that as a simple uncertainty-based approach where we measure the uncertainty in the output space. You can use any sort of uncertainty-based model you want. And our entire framework is agnostic to individual models. So even if a new model comes in, you plug it in. Even if a new uncertainty measurement comes in, you plug it in and it's good to go. For our experiments, we use a simple entropy on the output space to determine whether a model knows how to answer a particular question or not. And then to train our interaction reward, what we do is we keep track of all of our past interactions. If a person doesn't respond to us or responds in a way that's confusing or responds without an answer, then those are all negative interactions. And if a response actually contains the answer we're looking for, then that's a positive interaction. And we keep track of all of the positive and negatives and learn a binary signal between the two to determine what kinds of questions are likely to get responses and which kinds of questions are likely to get any response or likely to confuse somebody. So what happens if you only use one of these rewards? Well, if you only use the knowledge reward, you get the kind of questions I was talking about earlier, where people just don't want to respond to it because it's too difficult to parse and make sense of. And then if you only use the interaction reward, you end up asking questions that people will respond to because they're easy questions to respond to, but it won't teach you anything new. Okay, so you need both of these two rewards because without one or the other, this entire framework doesn't work. Okay, so that's how we set up the entire learning objectives. So let's decipher exactly how to guide this entire process using these rewards. Because even if you have the rewards and the policy in place, turns out that the RL to optimize this entire thing is extremely, extremely hard to do. And to intuitively understand why it's so difficult to do, let's take a step back and dive a little bit deeper into this policy that's generating these questions. So you have an image and you're generating a question, and you can treat this entire thing, this policy, as two parts. You've got an encoder that learns to embed your input image in some latent space. And then you have a decoder that takes that latent space and outputs some distribution over the question space. Okay. Now, this latent space of possible things you can embed into is extremely, extremely vast. So the possible space of all possible questions is really large, but we don't want to explore that entire space. Ideally, we want to only limit ourselves to interactions that people will actually understand and given the social context. But even that space is really large. And what we really care about is maneuvering around the space of questions that talk about visual content. And once we identify a space within that area that contains the kinds of questions that we don't know how to answer, that's great. Now we have a space and we can find good questions to ask. And within that space, we also have to simultaneously figure out the space of questions that people actually want to respond to. And then the reason this entire thing is really, really hard to do is because you don't just do this one time. Doing this one time is what RLHF is. You do it one time and you're good to go. But as soon as you figure out and learn new things, that space moves because now you know how to answer those questions and you need to find out what other things you don't know and learn how to ask new questions that you haven't asked before. And then within that new space, you have to rediscover the space of questions that people actually want to respond to. So this process of continuously learning and updating, it happens throughout the entire deployment of your agent. And this is what makes this entire process really, really difficult to actually build and get it to work well. And so far, in a lot of RL, there's only been two conditions where things have worked well. In the first condition, where feedback is explicit, where people tell you explicitly, this is the right answer or this is the right reward, that's when it works very well. And the other space it works well is when the action space is small, when the possible actions that you can take are only a few. Now, in a lot of the cases that we're talking about interactions with language where the action space is gigantic. You've got thousands of words that you can choose from. And then you also don't have real explicit feedback from people. You're learning that feedback and that reward throughout the entire deployment as well. So this is a scenario where RL is really, really hard to deploy. And so when you do deploy it using just traditional methods that are out there, using PPO, what ends up happening is that at some point, your model ends up generating some group of words that is nonsense. And the moment it starts doing that, people completely...
Hello, welcome to ICCV23. 25. P1 is the plenary source workshop. P2 Multidisciplinary Results Workshop.
Okay. All right, I'm gonna keep going. So what ends up happening is that at some point, you're going to end up generating some questions.
Verify disciplinary results workshop. And B2 disciplinary notes workshop room.
Apologies for this technical difficulty.
Yeah, okay. I'm gonna keep going. So what you end up realizing is that the moment the model ends up generating any question that is hard to answer, people completely disengage if they see anything that's nonsensical. And that means that all of our rewards completely go out of whack. They just stop updating completely. And the moment that happens, the entire learning process doesn't just stall, it just dies. And so the way we sort of fix this entire thing is, again, drawing ideas from several intersecting social science fields. For example, we know that the action space, although is really vast, the space of socially acceptable things that we do is very, very narrow. And what I mean by that is there's a ZIF distribution of possible ways in which we behave. The words we use is ZIF distributed. There's only about 2,000 words we use on a daily basis. The way I move my hands is also very, very dependent on the social norms, and I only move them in certain particular contexts. And so the way we behave, the words we use, all of our social interactions, they're more or less bounded because of the ZIF distribution by this lower dimensional sort of space. And if you can identify this lower dimensional space, then you can limit your entire RL to that space. And that's what helps this model prevent it from sort of going off off the rails. And so the sort of insight allows us to sort of say, is there this interaction manifold that we can identify in our learning process? And if we do, we can limit our action space to just that interaction manifold so that every question we generate will always be within that space and will never deviate from that process. And if we do that, what we end up doing is questions that refine themselves over time, but it never ends up generating nonsense, meaning that no matter what, there will be questions that people will respond to, and your learning and reward systems will always update over time. Okay, and the way we sort of do this entire thing, I'm going to skip ahead, is we learn an encoder, just like we had earlier. We learn it to embed into some discrete space. In this case, we have some d-dimensional space that we end up learning. And we can train this entire thing using Gumbel softmax or your favorite sort of discrete optimization method. And then you have a decoder that takes that space and outputs a distribution over your question tokens. And finally, those things go out in the real world, people respond, and then we calculate our rewards. But what's fun is that now the rewards don't go into your decoder, the rewards go directly into your interaction space, meaning that it's not just your social media and the humans that become your environment, but your entire decoder is held constant throughout your entire deployment. Your learning is how to embed your images into the correct space with the types of questions that help you learn the most at that moment. And so we have your rewards directly in, and the only thing that updates is the encoder part of your policy. Okay, let's quickly talk about what happens when you deploy these things out in the real world, and then we'll end. So we deployed this entire thing on Instagram, where we interacted with about 230,000 people during an 8-month process. Every single ablation that we launched interacted with about 230,000 people. And a lot of this work was done in 2019. And then, of course, it took us a long time to actually get this paper out because you have to train and figure out exactly how to get these models to work. Okay, so this is our overall system that we deployed out in the real world. People post photos on Instagram with captions. We take those sort of captions and images, we feed them into our policy. It generates a question. We post that question back as a comment on Instagram. If people respond to us, we have a parser that parses those responses. And then we take those responses and learn an interaction reward, as well as this uncertainty knowledge reward that I'm talking about. And then finally, when all these things are trained, this happens during the week, so Monday to Friday. And then every single weekend, we took those rewards and we updated our interaction policy so that next week we asked different questions that we hadn't asked the previous week. Okay, and then finally, we have a model that learns about the visual world. Okay, here are some kinds of questions that it ends up learning. It learns to ask questions like, what is the dog's tail sitting on? Or is the boardroom carpeted? It even learned to ask about life vests and what is and isn't a life vest whenever people near water. It learns to ask about objects. For example, it also learns that people don't just like answering questions like, what is this object? But they love to correct other people. And so sometimes it guesses. So it asks, is that a real bird, even though it's obviously a crocodile? It also learns to ask about attributes, so it asks about the shapes, the materials, the colors of things. And here's sort of what the learning process looks like. With the interaction manifold restricting the entire learning space, you end up learning to ask better questions over time so that eventually, by the 8-month deployment, the model was getting about a third of its questions responded to, so about 33% was responded. And not only that, we also collected a data set of VQA questions from Instagram because we wanted to test the model on the social environment it was deployed in. And what you can see is that it learns to ask questions that are only talked about on social media. So things like tofu and bok choy, these are completely missing in a lot of computer vision data sets, but people love posting about them. And so it learns to recognize those specific kinds of questions and concepts, and so it performs a lot better. But what's sort of fun is that because these are people taking photos and uploading them, they know intimate details about these images that you can't collect from other means. So you can't ask a crowd worker to fine-grain annotate birds or flowers or even vegetables for you, but you can ask the person who took the photo because they're more likely to know. And so we learn a lot of very specific information. And then, of course, if you only use the knowledge reward and you don't care about how people actually want to interact, you see the exact opposite happening, where over time, the people just stop responding to the agent. And because people stop responding, it just doesn't learn as much. So even though it asks questions that are useful for it to learn, it doesn't ask enough. It doesn't have enough of its questions responded to. And then the final thing I'll sort of leave you with is a lot of the emergent behaviors that we see are also the emergent behaviors that people have reported in the HCI community in terms of how we ask questions to one another on platforms like Quora. So we found that the agent loves to ask questions that are easy to answer because it learns that people want to answer those questions. It also learns that mentioning and showing social proof that it knows some things about the image before asking the question also helps quite a bit. And then it also learns to avoid questions that have multiple answers because whenever there are multiple answers, people don't like responding because they don't like being wrong. And then finally, it also avoids any question that's really difficult to actually understand. Okay, we also played around with how to introduce our agent, because as you can imagine, we're doing this all out in the wild. So the way you actually introduce your agent completely impacts the way in which people will react and respond to it. So we did a special study where we tried to figure out, keeping everything else constant, how should you introduce AI agents out in the real world so that they get responded to? So for example, if you say things like, hi, I'm an AI, turns out that's a really bad strategy for introducing any sort of agent out into the real world. And to understand exactly why that's so difficult, we drew again on ideas from psychology, specifically the content stereotype model. What this model tells you is that whenever we interact with somebody out in the real world, there are two axes along which we make judgments of everyone around us. So for example, for all of you that walked in here, you have already made this judgment about me within the first 5 seconds of listening to me. You can easily categorize me along two axes of competence and warmth. You know exactly where I fall along these two dimensions. And if you think of any single person in your life, you know exactly where they fall in terms of competence and warmth. These are two dimensions that are so intuitive that they are fundamentally something that we immediately do within 5 seconds of meeting somebody. So it turns out that you can use this framework to also study how people think about AI agents when they interact with them out in the real world. And contrary to how we treat and react to people, turns out we react to agents, AI agents, very differently. we found through a very, very big systematic study that when you introduce agents as having low competence and high warmth, those agents perform really, really well, and people interact with them in very pro-social ways, meaning that people are more likely to respond to your questions with actual valid answers. Whereas if you project high competence, then people won't do that. And there are examples of this entire framework at play all over the place. We've used the same framework to justify and predict user adoption mechanisms and pro-social versus anti-social behaviors on a whole host of different models out in the real world. So things like Cortana, Google Siri, our paper talks about every single one of these agents and how people reacted to them, and they follow the theories that you're putting forth in terms of how people will react to them. The reason GPT is such a great name is because it doesn't invoke anything. The letter GPT mean nothing to most people. And that's why that particular model does so much better than a lot of the other ones. And why people like that a lot more than something like BARD. Because the moment you call it BARD, you immediately project a particular kind of warmth and competence to what people should expect that model to be. And most of the time, you expect higher competence for something that's a BARD. And because of that, there are more anti-social interactions that Google has to deal with than OpenAI has to deal with. Okay, so I think I'm going to end right there. So we talked about socially situated agents. So a lot of this work is figuring out how to deploy these agents out into the real world. We have a whole host of new projects that are happening with space, and I'm happy to talk about them offline. Thank you.
Thank you so much. I'm going to sorry for the morning process. Do we have any questions from the audience? Do you have any questions?
Like the initial said,
yeah, that's a really good question. This is a concern we had very early on. And the way we circumvented it, we kept track of all of the data that we were getting. We trained with the entire data set just to avoid any sort of catastrophic. But it is a very open question. If you want this thing to actually work over time, over years, then you can't keep retraining on everything. So you do need a way of figuring that out. We didn't tackle it.
That is kind of curious on the that you would want the agent to ask this sort of question depending on its math. But I was wondering if whether you have a chance to study whether you put your agent in borders and focus, whether would the context that
Yeah, that's a really good question. I have two responses. One is we did a study where we tried to replicate this work across other social media platforms. So we tried it on Twitter, we tried it on Facebook, we tried it on English learning websites, and there were work in different areas. We didn't find anything that was similar across the board. What we did find, though, is that there are some platforms where you can't have social behavior at all. So on Twitter, for example, it was almost impossible for us to get straight responses, valid responses from anybody. It seemed like everybody on Twitter just wanted to tell us things that were false. Other platforms were a lot more pro-social. So, careful about Twitter. The thing is, we are very interested in culture and its implications on how we see. And we have a new paper coming out, it's not out yet, where we actually study if those differences actually manifest itself in how people see the world. And turns out there are a ton of differences. So looking at the same image, someone from America versus someone from China will see very, very different things. And because they see very different things, they will talk about very different parts of it. And because today we're training all of computer vision models by scraping data from the internet, and most of it's from English, there are entire parts of the visual space that are completely left unexplored. And we systematically, again, show that if you collect data on the same set of images using caption data from Chinese speakers versus English speakers, you end up learning a much wider spectrum of things about the image than if you only focus on one particular language. And then we sort of scale this up to 7 other languages.
Up the slides and keep talking. So hi everyone, this one is and today I'm here. Was actually from NLP and data mining community, and we will present the workshop to give this challenge a home in computer vision community, and we are here to learn.
Oh, shoot. So it turned out, okay, so don't worry, you are in the most important part. So for people on the Zoom call, I hope you can hear me now. So for this task, back in 2021, initially we want to imagine there is a model that we just give it a figure image, and it can just generate the figure caption for us. And again, this is not alternative text. This is the caption you can read from archive papers, right? And that's our imagination in 2021. And after 2 years of struggle, it turned out this year we published another paper and we figured out, oh, we actually need the content from the papers. You can probably imagine why, right? Even from this example I show on the screen, the figure itself probably does not contain very rich information. You still need the paper content to give you enough information. And in this year's paper, we actually kind of argue it's more of a text summarization task than a vision to language task. And we use this paper as the baseline of the challenge. So before I get into details, I want to talk a little bit about motivation. Why bother doing this very, very specific thing for your paper? And the answer is all of us or some of us did not pay attention writing your figure captions. Some of you didn't spend enough time to write your captions. So we know there are a lot of lower quality very vague high-level captions on archive papers. And this is part of our study of our this year's paper in INLG. We actually do user study with NLP PhD students, and basically more than half of them was rated unuseful. So we are thinking, is it possible to have a very cool model to generate slightly better caption when the original caption was terrible? And that's a one like user-facing motivation. Of course, higher level, you have like intellectual motivation. This is a really complicated task. You need to consider all the context and text in the document. So itself is an interesting task, but it does have some user implication. And the very straightforward question is like when we introduced the task back in 2021, people always ask, oh, we have many vision to language model, right? Can you just take all of them or some of them to run tests? And that's why it took us 2 years to figure this out. No, it's just very hard. And we actually tried several vision to language models, and it just didn't work. And that kind of moved us to look into the information in the paper content. And we also, in our paper, we also present some of the baseline of vision to language models, but we're not going to talk about that here. So this is a very hard task. And so my student will talk about the data cleaning details of the challenge.
Okay, so I will introduce our like current data set. So as many real world data set, the data it's require a lot of like many steps to do the data cleaning. So to simplify, like I just give an overview here, and there's our challenge data set. So scicap challenge data set is planned from initial scicap data set version. We actually extract like around 480,000 figures from archive papers, and it's from January 2010 to October 2020. And it covered a different domain like computer science, economic, electrical engineering, and mathematics, physics, biology, finance, and statistics. So you can see there's a lot of domain of archive paper. And we also include like ACO dataset, which is published in this year's CLVL5 workshop, and to as additional training. We remove the because some people when they publish in ACO, they also will put it in the archive. We remove those duplicates papers. And also the last part is so for the figure type, we include 5 different is bar chart, grid plots, node diagrams, scatter plots, and equation. So I will go to detail later, but just keep in mind this is the overview of our data set. Okay, so because it requires many steps to do the data cleaning. So to simplify, there's 6 steps for our data preprocessing. So the first one is data acquisition and preprocessing. So actually, we download like over 2 million archive paper from, as I mentioned before, from January 2010 to October 2020. And the next step we use is a published tool called PDF Figures from Allen AI. And in 2016, we used the tool to extract the figure effect surrounding caption. And we also extract the content of the paper. So we use Grobit, if you know that it's a very popular to extract PDF contents. So we extract it as a XML file. Here's the example here. You can see that we transfer the PDF content to the XML format. And we use heuristics method to extract those content related to the figures. We also extract the image tags inside the figure because we think there's critical information inside the figure. So we use Thursday OCR to extract those
information inside the figures. And the next stage, so because in the archive paper, like in the scientific document, there's actually many compound figure. Like you could have one figure, two figure, you could have multiple figure, or like whatever, like 6, 8 figures. So to reduce the complexity, we use figure separator because we want to reduce the complexity. So we use figure separator to identify if the figure have compound figure, and we remove those compound figure because we want to simplify and that's everyone participating to the challenge. And then last stage, so we use existing like published papers. We do classifier. We just classify all the figure type. So in original paper, there's 7 different types. Hello, can you hear us? Hello. Did you turn off your microphone? No. Hello, can you hear me? Yeah, you can go ahead. I think. Okay, so yeah. So for the last part is we also did the figure type classification. So in the original paper, they annotate 7 different types to reduce the complexity, because we think like table data and table figure and other type of figure is very far from like this bar chart graph part. So we just remove it. Yes. One thing I want to mention here. So after remove the table type and the other type, we actually found like the domain type is a graph part. It means like when people writing the scientific document, they use graph part a lot. Okay, so yeah, and then I will talk about our evaluation. So like one is very typical, like we common using the automatic metrics to do evaluation, like blue score, rouge score, as you know. And I want to mention here, we also did the normalization that's based on the different lengths. Because think about that, if you have like a different, actually caption can be very from like 5 words to like a whole paragraph. So it's hard to do the fair comparison. So we also do the length normalization. Yes. And the next is first in addition to the automatic evaluation, we also did the human evaluation. So we actually collect the human corrected subset of our hidden test set. So next, I will talk about how we collect the data sets. So actually, we use this human corrected subset to select the quality winners, and we random sample from the whole test sets, sample 1,000 figures, and then we first because you know like human annotation is very expensive, so we just first using GPT-4 to produce a 6-scale quality rating, and we just we hope GPT-4, I mean, it actually could identify those very bad quality caption. So we first build out those score lower than 5 and then it becomes around like 700 figures in the RASP. And then we actually free of our like organizer, like Asper, we do internal agreement. We manually select the final good quality caption, and it's around like 470. Yes. So the intuition behind this quality subset is basically one, we of course have the leaderboard winner, which is basically the score. We just compare the score on the entire test set. And we, of course, we have the public test set, and we also have the hidden test set, which they don't have gold standard. and we will let them submit to that hidden test set 2 weeks before the submission deadline. So they will only have 2 weeks window. And this is the final score of the entire test set, which we call it a leaderboard winner. And we have 6 different teams, external teams. This does not include a baseline model from us. And this is 6 teams that submit to our challenge. And you can see the top teams score basically is like way higher than the other teams. So they did a great job in these metrics. And by the way, we use a normalized ROSH2 to decide a winner. So that's a leaderboard winner. And we also have a winner called quality winner. Quality winner is the winner's scores with the highest score on the human curated subset of hidden test set. And the intuition is that it is possible that your model doesn't work very well for the entire test set, because we know there are a lot of low quality captions there, right? But if we curate a subset of higher quality test set, it is possible you can win on that particular data set. Well, however, in our challenge this time, that didn't happen. The highest score is still from the same team, as you can see in the bottom table. And because we promised we will select 2 different winning teams, so we choose the second place of the quality, the quality subset as the quality winner. And we will, oh, and by the way, we did purchase the trophy, and we have send it to them last week, and hope they will be happy. And so, can you please try the video? So both of the teams, they cannot attend the conference in person or even via the Zoom call because the time difference is pretty big. So we figured out a way to do it is that we did a short interview, Zoom interview with them, and we record the interview. It's about 5 to 7 minutes, and we decided to play a video so that at least you can hear their voice and see how they actually achieve their scores. Let's get started. So today, okay, yeah, let's go. We are talking with the winning team, the leaderboard winner of the first figure captioning challenge. So thank you for agreeing to chat with us. So can we begin with introducing your team and what motivated you to participate in this challenge?
Oh, yes. Our team hails from Nanjing University of Science and Technology. My name is Chao Dian. It's my photo, and it's my partner. His name is Zhongshu Peng. Our lab research focused on multimodal learning, large-scale models, and incremental learnings. We think this competition serves as a valuable opportunity for learning and collaboration. We look forward to engaging with fellow researchers in the field of multimodal large-scale models, fostering material exchange and knowledge sharing.
And can you tell us a little bit more about the methodology and the intuition behind your methodology?
The overall architecture of our model is shown in the figure. Compared to the Pixis model used in the baseline, we used the Pixis X model. On the basis of Pixis X, we found that the length of text input is too long. Even though the number of importable text tokens in Pixis X is 4,096, the number of OCR plus mention plus paragraph in the dataset still exceeds this number. Therefore, we use the lemma to effectively compress the length of these samples, just like the photo shows. At the same time, we found that the accuracy of the information provided by the figures greatly improved the model. Therefore, we used the pedal OCR to extract more accurate OCR information. Finally, we found that the Pixis X model used a cross-entropy loss during the training process, which is a gap between the evolution and the Roche metric used. Therefore, we nested the Pixis X model into the architecture of the Braille model. The Braille model is an effective model to improve this problem. It uses the idea of contrastive learning, uses the output results of multiple decoders to orbit multiple candidate answers, use the candidate answers with high routing scores as the benchmark. as a benchmark, calculates loss with other candidate answers and adds it to the training percent of the model. In order to meet the evolution criteria of the computation, we have set the evaluation index to normalized. Finally, we fuse the multiple model we trained. Lesson 9. We trained including whether to add the pedal OCR model, whether to use NEMA, and whether to add the BRI model. We used an evaluation metric to fuse the answers of these models. That is to say, we select one of the multiple candidate answers for each sample as a base, and then calculated the row-to normalized value between the other answers and the base. Finally, we take the average as a score for this base and take the best base with the highest score among the candidate answers. This is our final result.
Yeah, this result is very impressive, actually. So can you tell more about the challenges you encounter and how did you solve those challenges?
Our challenge is at this time, current summarization models often have limitations in handling very short input text, but we needed to process a large amount of information. To address this, we tried a lot, and finally we employed the NEMA to effectively compress the length of input text. This approach improved the quality of the generated summarization.
Oh, interesting. So can you also talk a little bit about the future direction?
Yes, we plan to continue our in-depth research on this task in the future. Over the course of these 3 months of the competition, we have gained valuable experience and insights. We believe that there is still significant research potential in this task, and there are many interesting methods worth further exploration.
So finally, do you have any suggestions if we do this challenge again next year?
Yeah, we believe that for the next generation of this competition, a crucial area for improvement lies in harnessing image information more effectively. While we use OCR for extracting information from the image and from the figures, we acknowledge that there is untapped potential in maximizing the use of visual data. Furthermore, with the continuous advancements in natural language models, there is significant room for growth in our In our approach, we use the NEMA primarily for text compression, the information refinement, but we are confident that using natural language model can offer more information and give more methods for the task.
Yeah, I think it is very interesting that the 2 winning teams basically kind of heavily focus on using text information. And I do agree that the next iteration of the challenge or the competition team should probably be thinking more about how to use visual information more effectively. Yes.
Yes, we think so.
Yes, okay. Yeah, so that's the interview for the first thing. And a little bit context of this is basically, like I said, we only provide a baseline that is based on text summarization model. And we did not provide multi-model or vision to language baseline. And both of things kind of mentioned that they hope we can provide a multi-model baseline to them. So that will probably be one significant improvement. Next round, if we do it again next year. And next, we are going to watch the interview of the quality team winners. And by the way, for the leaderboard team, I did invite them to turn on their camera so we can see them talking, and they prefer not to. So, but for the quality team, they are willing to turn on the camera. Okay, hello. Today we have the pleasure of chatting with the quality winner team of the first scientific figure captioning challenge. And thank you all for participating, and big congratulations on your achievement. So can you introduce your team members and tell us a little bit more about what motivated you to participate in this challenge?
Oh yeah, my name is Biao Zhang.
Okay, that's good.
And I'd like to give an overview for our work. And our team members it consists of Junyu, Xiaohua Qi, Qiangling, and me. First is about what motivated us to participate in this challenge. There are two aspects. First is interest. We are highly interested in participating in the challenge of generating chart and table captions using multimodal data, as we recognize the significance of automated caption generation in scientific research. The second is self-improvement. We are also motivated by personal growth. With the rapid development in the field of multimodal data, we aim to quickly familiarize ourselves with the latest advancements by participating in this challenge. That's
Okay.
all.
So can you tell us a little bit more about your model architecture?
Okay. We propose a system with the following overall structure, as illustrated in the diagram. Let me move it. The caption for an image can be produced by summarizing the content of both the blip caption and the paragraphs that reference the image. Blip caption is generated by the blip v2 model when provided with the input scientific figure image. We conceptualize the task of generating finger captions as a text summarization task. This section mainly discusses the following four parts in extracting blip caption, data acquisition, generating figure captions using a text summarization model, and post-progression. The first is extracting blip caption. Blip caption refers to the captions associated with scientific figures. We extract blip captions by utilizing the blip v2 model, which takes the input scientific figure image and generates corresponding captions. The second about data acquisition. We acquire the necessary data for our model, including scientific papers and their corresponding figures. We pre-process the data to extract relevant information, such as figure captions, figure reference in paragraphs, and the corresponding text. The third, generating figure captions using a text summarization model. We treat the task of generating figure captions as a text summarization task. We employ the text summarization model, such as a sequence-to-sequence model with attention mechanisms, or a transformer-based model to generate concise and informative captions that summarize the content of the figure and the associated text. And the fourth, about post-processing. After generating the initial captions, we perform post-processing to refine and enhance the quality of the captions. This type may include techniques such as language correction, grammar improvement, and coherence enhancement. Oh, that's all.
All right. So can you tell us more about the challenges your team faced during the challenge and how did you address those challenges?
Okay. The first, the challenge is integration of multimodal data. When dealing with the challenge of effectively combining image and text information to generate figure captions, we employed the following approach. Firstly, we utilized the the Blip V2 model to convert images into textual information, facilitating the seamless integration of the two models. And the second, handling blank and inadequate captions. Occasionally, the model-generated captions that were either blank or didn't meet standard criteria. To tackle this issue, we introduced ChatGPT 3.5, which is capable of regenerating and improving the generated captions. This step was implemented to ensure that the final generated captions match our expected quality standards. So that's all.
Yeah, all right. So what are your team's future plans? Will you expand on what you learned from this challenge for your future work?
Oh, of course. We plan to continue our research and development efforts in the handling and utilization of multimodal data to future enhance the quality and accuracy of generated finger captions. We will also work on refining our model architecture, training strategies, and post-processing techniques to adapt to a wider range of scientific text and fingers.
All
So that's
right.
all.
Yep. So this is the interview of the both teams, and I kind of want to encourage them and congratulate them by inviting them to give this presentation. This is their first time doing English presentation. And so that's basically all overview of our challenge. Go to the next. And any questions? I mean, we will likely do it again next year. And we are inviting all of your comment, feedback, or send emails to us. And we are happy to incorporate any new changes in the next year. Okay, and we have free stickers. We've been bringing 200 stickers to here. So if you want free sticker, talk to us. Okay, thank you. Any questions, suggestions, thoughts? Yes. Thank you. Yes. Exactly. So thank you for the question. So the question is about what do we mean by quality? We kind of skipped that part. So basically, in this challenge, we define the quality as usefulness to the readers. How does this caption help readers understand the message try to convey, the image try to convey? And even that is kind of vague, we understand, but that's the question we use in our user study, which we didn't use actual like human study in this. I mean, we didn't actually have like full-scale user study for this challenge. We mostly still rely on automatic evaluation, but in our own work, we did user study. Basically, we invite people to sit down, and mostly we have them read the caption from papers in their domain, like NLP people read NLP captions, and have them rate from 1 to 6 the usefulness of that caption. And that's what we define by quality. And of course, it has its own limitation, right? It's like, for example, junior PhD and professor, the way they define usefulness is very different. And for now, we focus on PhD students, and most of them are probably on the more junior end. That's basically the scenario we go after. Yes. Yes. So the initial SciCap challenge data set has been released in 2021. And this challenge, we expand the data set, as we said. That one is already available on Hugging Face, right? Yes. So the image, the caption, the figures, the mentions, the sentence mentioned those figures, like figure 1 shows blah, blah, blah. The sentence and the paragraph of those sentences are all extracted and organized and put it on Hugging Face. So yes. So for this challenge, we haven't released a compound figure, but in the following, we will like release it soon. Like it's over 2 million, like over 2 million figures. So yeah, if you are interested, we'll just really follow. Yes. Yeah, for evaluation. Oh, it's on Eval AI. I think we probably closed the leaderboard. We can reopen it, but yeah, I mean, the public test set is out there, and I don't think we decide if we want to release the hidden test set. If we don't, we will open the leaderboard. Yeah. Cool. Thank you. Yes. 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 Yes, if you only have 1 minute before the deadline, run our model, and probably and we have stickers, so talk to us. Thank you.
Yeah, so I think Kilich, if you're ready, or
Hello, can you hear me clearly?
yes, we can hear you.
And also, can you confirm that you can see my slides?
Yes.
Yeah. Okay, thank you. And should I start then?
Yes, please. Yeah.
Okay, thank you. Thank you. All right, so good morning, everyone. My name is Kilich Haydarov, and I am currently pursuing my PhD at King Abdullah University of Science and Technology. Today, I am thrilled to introduce you to a challenge, visual dialogue-based emotion explanation generation. So emotions, basically, they are a fundamental aspect of human communication, and understanding how to teach AI models to comprehend and generate explanations for emotions is a fascinating and important endeavor that we think. But before we delve into the challenge itself, let's set the stage. Our journey began with a project titled Effective Visual Dialogue, a large-scale benchmark for emotional reasoning based on visually grounded conversations. This project was as a result of collaboration between King Abdullah University of Science and Technology, Health Unity, and Google DeepMind. So recent times have seen a surge in interest surrounding effective explanation task or effective explanation. In a sense, we are tasking AI models with a complex objective. For example, given a visual stimulus, typically an image, the models must not only discern emotions, but also articulate explanations in natural language. So, for example, for this painting, like Paris, a rainy day, the model needs to produce like some emotion, deduce the emotion, and then like provide explanations like in text. The overcast sky creates a gloomy and dreary atmosphere. So now let's take a step back and look at the landscape of prior research in this area, affective vision and language. So this field has explored several key areas, including affective explanation in the context of art, where researchers have delved into the intersection of art and emotion. They have explored how AI models can provide insightful and emotionally resonant explanations for various types of visual art. And the second, like addressing bias in AI systems actually has been a paramount concern. So this work has focused on mitigating biases in effective image captioning. So ensuring that AI generated explanations are both accurate and equitable. And this work focused on cross-cultural presentation. This work focused on cross-cultural perspectives on effective explanations. So emotion, we know like they are inherently subjective and culturally might be influenced. So here, researchers have explored the cross-cultural dimension of affective explanations, investigating how AI models can adapt to emotional nuance like of various societies or like demographics. And lastly, beyond artistic and controlled settings, researchers here have delved into the area like real-world images. They have developed AI models capable of providing emotion-based explanations for everyday scenes and events. So as we delve into our research challenge, like it's essential to acknowledge these foundational works in these areas, and the insights and methodologies developed in prior research have paved the way for our exploration in this project. Now let's shift our attention for the first two papers. These papers represent the initial key highlight contributions to the field of effective explanation in AI. So let's take a brief look at each of them to get a sense of their key findings and insights. So first one is Artemis, and the second one is like it's okay not to be okay. So starting with Artemis, this manuscript of like paper, like in brief, focuses on the formation of linguistic effective explanations grounded on visual stimuli. And they propose they also propose a data set of more than 439,000 emotional responses and explanatory utterances to visual artworks. So if we look at the interface, user interface used for data collection, here you can see like annotators given some visual stimuli. They are asked to choose one of the emotion labels on the side indicated by emojis, and then provide explanations in the text form. The reason for using emojis was to ease the cognitive task of self-identifying and correctly selecting the dominant emotion, which was like felt by each annotator. So let's look at these examples, which offer some glimpse to the capabilities of models, basically like image captioning models trained on Artemis dataset. So each of these produced explanations here reflects a variety of dominant emotional responses, and as well as explanations. So the top row, in the top row, you will find examples where the deduced grounding emotion was positive, and the bottom row represents examples where the deduced emotion leans towards some negative spectrum. So now let's focus on the second work. It is observed a notable trend in emotional bias towards some instance-rich emotions in the Artemis dataset. So here, this bias had the effect of making trained neural speakers or neural baselines or models based on Artemis less accurate, and when it came to describing some underrepresented emotions. So as a remedy, we proposed the contrastive data collection approach to balance Artemis with a new complementary dataset, such that a pair of similar images have contrasting emotions. So now here again, you can see the contrastive data collection interface. The left interface here shows the painting. and 24 of similar paintings from which the user selects the closest painting that elicits opposite emotions to the original one. So here, if it's a sadness, fear, then we pick the positive one. And depending on the sentiment of the original painting, the user will either see the positive or negative emotion captioning interfaces. And after choosing their like emotion, they provide their explanations in natural language. So we show that after analyzing and retraining the models, we show that a model, for example, Chauvet and Tell, trained on using these combined data sets, which includes also complementary contrastive data set, outperforms all the other versions of the same model trained on previously proposed different data sets. Yeah, so while existing research has predominantly centered on investigating this direct influence of visual stimuli on emotions and express it via language, still some notable void exists in the examination of the impact of visually grounded language on affective responses. So our research aims to bridge this gap by investigating the formation of emotions in visually grounded conversations. So to achieve this, we embarked on a journey to collect some conversational data involving two individuals discussing visual stimuli. So taking inspiration from the visual dialogue paper, we assigned two distinct roles to participants in our conversations. The first role is that of the questioner, who exclusively asks questions about an image without actually seeing it. So the image is hidden for this questioner. The second role is that of the answerer, who responds to the questioner's queries while having access to the image. So to facilitate these conversations, we employed the Mephisto framework and connected annotators via Amazon Mechanical Turk. Now let's delve into the process of live communication. So imagine now you are in the shoes of the questioner. You receive instructions, including one negative and one positive emotion, positive opinion about a hidden image. Based on these initial opinions, you initiate a conversation by posing your first question. Okay, so here is the user is typing the first question. Now let's switch perspectives. You become the answerer. In your new role, you also receive the same instructions, but with the added advantage of actually seeing the hidden image. So as you notice here, you can see the hidden image. So as you can observe, like the interface remains the same with both participants engaging in back and forth exchange of like 10 questions and 10 answers. So the video will be like speed up. So they are exchanging like 10 questions and 10 pairs based on the visual stimuli. As a conclusion of this dialogue, you can see both participants are tasked with selecting an emotional label based on the conversation and provided a detailed explanation for their choice. Once the first explanation is received from the questioner, we reveal the hidden image and ask for their updated emotional response, whether they change their response or not. Okay, done. So in this way, we collected like the data. So, sorry. So our efforts resulted in the collection of 50,000 dialogues, where each dialogue contains emotion labels as well as the explanations to them. And the data collection process amounted to approximately 27,000 working hours. And then following our previous works described previously, as a part of our data collection process, we also offered participants selection of 9 emotions to choose from. This included 4 positive, 4 negative emotions, and 1 neutral category labeled as something else. And for our visual stimuli, we curated a diverse collection of artworks from the VKR dataset. These artworks served as a foundation for generating the visually grounded conversations that comprise our dataset. One of the interesting aspects that we explored in our research was how often participants changed their emotional response once the hidden image was revealed to the questioner. And here this analysis provided some insight into the dynamics of emotional reasoning during our dialogues. We discovered that more often than not, like questioners choose to retain their initial emotion choice even after the image revealed. In fact, in more than 70% of the time, participants maintain their emotional selection. But however, it's essential to note that interesting exception to the last something else trend when participants encountered the something else emotion label. This category proved to be more fluid, with participants frequently altering their emotional choice in response to the image reveal. So delving into the dataset characteristics, we conducted basic statistics to highlight the distinctive features of our dataset compared to some existing visual dialogue-like datasets. Our dataset stands out by containing both emotions and explanations, introducing affective dimension. And by analyzing part of speech tags, we also showcase the linguistic richness of our dataset. So, for example, compared to visual dialogue, you can observe despite our dataset being smaller, it contained more part of speech tags, for example, nouns, pronouns, and adjectives. And let's move on to defining the two subtasks that we designed to evaluate the models. First is the ability of models to answer a question based on the dialogue, and the second is the ability of models to predict emotion and generate explanations in natural language. So the first subtask is closely resembles like a visual dialogue task, and the second is our affective explanation generation, which is used for challenge. And here you can see some examples. When presented with an image, initial opinions and dialogue history and follow-up questions, models are challenged to provide the correct answer to that question. The last green answers are models output. And in subtask 2, given a complete dialogue, models are tasked with predicting both predicting the emotion conveyed within the conversation and also generating explanations. So also it's essential to shed light on some methodologies we employ to evaluate our models, like within the defined subtasks. So in order to assess our models in subtask 1, we employed neural baselines borrowed from the previous works. This included utilizing naive nearest neighbors, as well as training state-of-the-art models from the field of visual dialogue. For subtask 2, we fine-tuned language models like T5, BART, and also included multimodal explanation model, which is called like NLXGPT for emotion explanation generation. So for subtask 2, which focuses on answering questions within the dialogue, we employed standard retrieval metrics from visual dialogue. These metrics allowed us to assess the effectiveness of trained models in retrieving the correct answer based on the given inputs. And for subtask 2, we utilized weighted F1 score for emotion prediction and the standard metrics from image captioning, blue, BERT, and also BART, which measures the similarity between ground truth explanations and then generated explanations. So here, our results clearly demonstrate that the importance of dialogue context, so resulting in significant improvements in F1 metrics. And one intriguing observation is that training a dialogue-based classifier can be used to identify answers among candidate responses that maximizes the probability score for the target emotion. So this highlights the potential for interesting approaches in, for example, image editing tasks. And as we look ahead, our research opens up some exciting possibilities. So one intriguing avenue is the potential to leverage the newly selected generated answers to edit images using text. So imagine a scenario where the emotional context of a dialogue can be used to guide image editing process. So this concept like paves the way for the development of emotion-driven image editors. So these editors could intelligently adjust visual elements such as colors, lighting, or like some compositions based on the emotional, based on the deduced emotion from the visually grounded conversation. So here we picked the responses which maximize the prediction of like positive emotion contentment. And then, for example, there is a mountain in the picture, then we turned it to the instruction using like some GPT like models, and then edited the original visual stimuli so it can be reflected in edited image. So you can see the mountains added to the background based on the picked or selected answers. So to reiterate the core of our challenge, participants they are tasked with the following: given a conversation, given two opinions, or optionally image, the objective is twofold. First is to predict the emotion, and then generate explanation in natural language. So, all right, as we bring our presentation to close, we want to extend a special invitation to all of you. So our challenge deadline is extended actually till December 10, and we enthusiastically invite each and every one of you to participate. So it's an opportunity to put your skills to the test and make a meaningful contribution to the evolving field of affective vision and language. So our winners of our challenge will be announced later. And we are eagerly anticipating the novel approaches as well as solutions that will emerge from the collective efforts of the vision and language community. And yes, thank you for your attention, and any questions from audience.
Thank you so much, Kelubek. Do we have questions from the audience about this challenge?
For the presentation. I mean, that's about your life installation. And let me know that I understand this question. What difficult making the basis using AI agent and subject, right?
Can you hear the question?
Sorry, I cannot hear clearly. So could you just?
So I think you can come up, but yeah, it can come up. But I believe the question was about your demo and whether there was whether you had a live subject with an AI agent. You can come and repeat your question if.
For the demo, no, actually the demo that I showed was a live data collection process that we like engaged two participants to like have a conversation around like a hidden visual stimuli. But yes, so after training the models, we can also demonstrate this kind of like answering ability similar to visual dialogue, and show as a demo. But yeah, the demos that we showed, like the video that we showed, is actually the data collection interface, not a demo of some trained AI.
So I have a question for the data collection process. So how did you prepare the AI agent for data collection? Maybe I missed something.
Oh, okay. So no, sorry, it is not actually, we didn't prepare anything AI, but we paired two people in live communication here.
I see, I understand. Correct.
Yeah, so this is like way before training the AI model. So we needed to collect the data. So we just paired two like people using the Amazon Mechanical Turk and some Mephisto framework for like live conversation. And here we didn't deploy like any. This is that maybe icons might be confusing here, but this is not AI, but it's just like to show the roles for the participants. Okay, they are questioner, and also they are you are acting as an answerer.
I see. It's interesting for me. Thank you.
Yeah, thanks for the question. Thanks.
Thank you so much. Do we have any other questions from the audience? Okay. I think there are no other questions, and I think it's also time for the coffee break / poster session, which will be kind of the next half an hour or so. And so thank you so much, Kilic, for your introduction to your challenge. And just to remind everybody, this challenge is ongoing until December 10th, I believe. So you should all participate.
Thank you.
Yeah, so poster over there, and there's also some coffee outside. So well, thank you so much for
But excuse me. I will need some audio signal from the computer to make sure it works. We can just run. You. Oh, someone is talking. That's good.
Do you want to hear something to test out the signal?
Yeah, just in a second. In a second, please.
Yeah.
Yeah. When I just signal me and I'll put in.
Did we tell them that I was gonna tell them that
I
when do we resume?
think, let me check. Waiting for the synchronization to happen. Okay, so if you can talk a little, maybe I can check if we can make it work.
Hello.
Okay, so obviously this is still going through the wrong places. Okay, and if you're talking now,
Hello.
okay, again, please.
Hello.
Okay, that's good. Thank you. It's just very loud now, I think. Can you speak again?
Huh? Oh,
Hi.
couldn't they not hear very well?
Yeah, Kalish, can you speak again? Is it Kalish listening?
Hello. Hello.
we need to go because I have.
Yeah, I understand. Thanks for leading this.
I also realized I had a short something to do, like 11 something.
Yeah. No worries.
Thank you
Yeah,
for helping
thanks.
too,
Yeah,
because
appreciate
I was, I think you were very helpful.
Yeah,
Here.
thank you.
So thank you so much.
Yeah, thanks a lot. Yeah, I'll be here. So
Okay, so maybe I'll go and then I will, maybe I'll see Mohammed, but maybe let him know that I can go, but I'll be back in the afternoon.
yeah, sounds good.
Yeah, so I have something at 11 something, and then he says, well, I'm awake, it's probably
Yeah.
fine.
Thank you. Thank you, Angel.
Yeah, and I'll be back in the afternoon for the panel session.
Yeah, so so Mohammed's gonna take over for this session. I'll take over at 1:30. And then, and then you're gonna take over at the
Yeah.
panel.
Yes, I'd be,
We have a live stage. It doesn't fade.
Can they go to the periphery and
or can they like do, can they do two, like one on top, one on bottom, like across two boards?
In some certain angles.
Oh, I see.
maybe they can take two panels for now?
But I can come and take a look.
It's not responding. So can I just play a video or something? Let's see. Yeah. Just-
Speakers is better like this in both microphones at the time.
So when we have some speakers that share and project in Zoom, I guess they don't need to do like open their mic anymore, right? Like they get their own computer and then they present to Zoom, but I think their audio can come from here, right?
Yeah, if you have different computer.
Yeah, so they don't have to open their mic. That's what I'm saying.
Yeah.
Okay.
We will use this and
Yeah, they can use this.
yeah. But for this computer, and when someone is speaking through microphones, it's really best. It's like this.
Okay.
So, and they have to obviously talk.
Thank you. I appreciate it.
So I think hopefully it shows. Hi. Uh,
No, I think it's all good, thank you. I should select optimize the video clip or not? Should I should I optimize the video clip or not? I don't know what that is. Okay.
Hello.
It's not. Sorting out the sharing. Okay, I'll see you afterwards. So HDMI set there. Oh, yes. Okay, there's a USB over here. Okay.
No, we need to. Maybe here, right click. USB audio, it's okay, it's already selected this way. No?
Let's use this, yes. Okay. Yeah, please. Okay, I'm going to play the sound, right? No, I don't hear any sound. No.
Does it play on your computer?
Right.
خلاص يا اسلام.
Drink.
Yeah, that one. Sit down.
We're going to start in 1 minute.
Hello, hi everyone. Welcome back to our second part of the morning session. My daughter and is one of the community computer vision field in general. He is a principal architect of the modern computer vision. His work in 1980s in surface reconstruction has been well recognized. He's best known for leading the role during the 90s, establishing the computer theory on multiple geometry, and all of us are aware of his multiple geometry in computer vision that laid the foundation on many of the 3D computer vision courses in our community. Mr. Andrew has received several awards, including the PAMI, Mr. Shisher Award, Royal Society Milner Award, and many others. So this, without further ado, please join me to welcome Andrew. Thank you for joining us.
Okay, thank you for the introduction. Can you, at the back, am I loud enough? Can you lift your hands up? Too loud? Okay. So, yeah. Can't see the screen. Okay. So this talk is on automatically generating audio descriptions for movies. I'm going to start off just by giving some background and motivation why I'm doing this. So in computer vision, we've for a long time wanted to understand films, movies, video clips, and that's answering questions like who is in the video, what are they doing, where's the scene, maybe even more moving towards where's the story, but we haven't done that yet. And for short video clips like this, we could answer these questions. We could say, well, you watch it first. So we could answer these questions. This is Buster Keaton, that's a person. What are they doing? They're grabbing a car to escape from the police. You know, this is a sort of level of understand we can do. But maybe we could shut the doors as well at the back, perhaps, because there's lots of noise coming in. But what we can't do is long form videos. For here I'm thinking of movies which might be like 2 hours long. These are things we can't do yet. That's a challenge. And that's what I'd like to be able to do. And in terms of previous work in this area, there's been some work on summary prediction, some work of alignment of films to books, determining character relations through films, but not so much of really understanding the story. So that's brings me on to audio description and why we're doing this. So first of all, I'm going to say what audio description is. So what I'm going to do is play you a movie clip from a film called Out of Sight. It's about 25 years ago, this film. I'll play you the clip first of all without the audio description, just with the subtitles.
Buy a drink?
Yeah, I'd love one. Sit down.
Okay, so this is a clip. Now, what the audio description is going to do, its aim is to describe all the visual elements of the movie for the visually impaired, so for the blind. So I'm going to play the clip again now with the audio description, and you'll hear an extra voice added, which will be intended to explain to a blind person what's going on.
A man approaches toying with a lighter. She turns her head and finds Jack standing beside her.
Buy a drink?
Yeah, I'd love one. Sit down.
He takes the seat opposite, then places his lighter on the table. She opens her mouth as if to speak, but no words come.
Okay, so you can hear the audio description there. It's describing what's going on, as I said. And you think about this is for a blind person, so the audio description doesn't need to cover what's in the audio track, because obviously the blind person can hear that. But it does need to explain the visual elements, who's there, what they're doing, what their emotions are on their face, because a blind person can't see that, but particularly the ones that are relevant for the story. And also, the person who's doing the audio description has to know what they've said before, not keep saying the same thing. So if you notice, the narrator made reference to the lighter. The lighter is put on the table, and that's because in that film, that object, the lighter, is very important. It's significant throughout the film, why that was mentioned. Okay, so our objective in this work is to be able to take film clip, or film in fact, and learn a model which can generate these audio descriptions. That's what we want to do. And we're going to generate them as text, and then text to speech can read them out to a blind person. Okay? So the reason I'm talking to you about this is because I think this is a way to evaluate long-form movie understanding, which you could compare the audio description you produce automatically with the audio description that's there that is story aware. And other things, it's multimodal. You have to be aware of what's being said and the non-speech soundtrack sounds. And it's fine-grained. You have to be able to talk about human actions and human emotions, what they're doing in quite some detail. Another reason is it's for the visually impaired, this is very important. So this is a quote from a blind person, which is saying, I'm now able to enjoy lots of different films I grew up with, but wasn't able to understand because I'm blind. And this is a quote on a website called Audio Vault, where volunteers upload audio descriptions for films. They just upload the soundtrack, the audio description I did. That's what that's from. And we're going to use this Audio Vault provided by volunteers as a data source to learn how to do audio descriptions. Okay, so what we want to do. So we want to have a model which takes in video frames, and we'll have a video language model which is going to be generative and generate text. This is what I'm talking about at this workshop. And in addition to taking in the video clip, because it has to be aware of the context, we also need to supply what's been said before in terms of the AD context and the subtitles of what people are saying, so it's aware of what's going on. And then we want it to be able to generate text of which would be the audio description. Right, so from now on, I'm going to break the talk into two parts. I'm going to introduce a model which does AD and show how we can train pre-trained foundation models to do this. And then that's not worked so well, then I'll improve it so it gets up to quite a good standard. So this is the model we're going to start with. So it's a prompt-tuned GPT type model. So on the left, it's going to take in frames from the movie, from the clip. They're going to be mapped into sort of language tokens by a mapping network. I'll say more about these components in a moment. We're also going to supply subtitles and audio description as context, and then we'll have a language model which takes in all of these as language tokens, and we start at the beginning of sentence and it will output the audio description. That's what we want. Okay. And in this work, we're going to use clip descriptors, one clip descriptor for each frame. I'll explain why in a moment. So in a bit more detail, we take in these clip descriptors, maybe like 8 or 10 frames, and we have the map network is what's called a perceiver resampler. So it's basically going to have some learnable vectors which attend to these clip descriptors and produce these visual tokens that can be read in by the language model. So it's doing this translation between vision and language tokens. And the advantage of this is you can have any number of frame features and just the same number of learnable tokens that go into the language model. So it separates the number of visual features from the number of tokens that go into the model. And then for the subtitles and the AD, which we provide as text, we have to provide these tokens, which are shown here. We have to learn these tokens, which say, now I'm supplying you subtitles, now I've stopped supplying you subtitles, sequence position encoders, really. And here I'm starting to provide you the audio description, I've stopped providing you audio description. So all of that has to be learned. Okay, so this is the model. Now, how do we train it? There is some suitable data that's been provided by Kaus, a paper last year. So this consists of about 500 movies, 300,000 AD descriptors, and clip features. So to avoid copyright problems, they don't provide the raw pixels of the frames, they just provide clip features at 5 frames per second. So there's all this data, very, very good, very useful. So in an ideal world, we could take this data, train our model, and we'd be done. But unfortunately, that's just not enough data to train a model like this. So the model will just overfit this data. So we can use this data to provide us an evaluation data set for testing, and we can use some of it for training, but it overfits if we try to train a model like that. So that's the first challenge. How are we going to train this model when we haven't got enough data which is sort of end-to-end, which has everything, it has the audio description, the subtitles, and the clip features for the frames. So the way we do this is sort of a good idea. We can train, it's a big model, it's got many modules. We can train the modules independently using large-scale data sets that are available. So there are large-scale data sets for images with captions and with video clips with captions. I'll say more about these in a moment. And this audio vault data set I mentioned, we can get lots of audio descriptions as text, but no vision. So we're going to train the model partially using these large data sets and then train the whole thing with the MAD data at the end. So, let's explain these data sets. So this is conceptual captions, which many of you, it's this sort of thing that was used to train clip in the first place. So it comes from the alt text. You have images with some description, like the ones shown on the right. So tree and winter snowstorm, and there are millions of these available. There are also video clips with captions. You can get these from stock footage companies. So they can be quite short clips, like 10 seconds or so, and a few sentences describing it like this. Okay, so there's lots of data available like this, and that's going to train part of our model. And then the audio vault. So audio vault, as I said, this website where volunteers upload narrations, and it has 7,000 movies. That's a lot. That's great, but it's audio. It's only audio, and you have the original soundtrack of the movie, and spoken over that is the audio narration. So just one soundtrack. So we have to do some processing to make this data useful. We want to process it to text. So first stage is to take in the audio, run automatic speech recognition, and we run Whisper X ASR. So Whisper is the OpenAI ASR model, and we extend it so that the time stamps are more accurate. It's Whisper X. So now we have all the text and timestamps that's shown here, this data, but we don't know which is the narrator and which is the character speaking. So we have to do diarization. We use the voice to separate into clusters. We cluster based on the voice, and the largest cluster would typically be the narrator, or we pull out the narrator cluster essentially. So now we have all the text, and we know which is spoken by the narrator and which is spoken by the characters, okay, as text data. So we do this with the 7,000 plus movies on the Audio Vault dataset website, and all this is public released. Okay, so now we have our data sets, and we can train. So we've got this model, we freeze the video encoder, it's just clip, and we start off freezing the GPT and just train this mapping network here, okay, using the paired data, the visual data we have. So using the conceptual captions, that's images of captions, and using the web vid, that's short video clips with captions. So now this model knows how to take in videos, video clips, and output text. Okay, so that's done. And then we take the audio vault data, which is text, and we train the model to take in previous audio description and generate the next audio description. So the reason for doing this is that captioning of images and video is very, very different to audio descriptions when you're describing who's doing what, etc. So we want to bridge the domain gap by training it on this audio description data. Okay, so once we've done all that, then we take the MAD data that we have left and fine tune the whole model with that data. So that's end to end. We have the video data as clip, we have subtitles, we have audio description from previous, and we get it to write out the audio description for the current clip. And as you expect, each of these stages helps, but actually at the moment the subtitles haven't helped. So what people are saying isn't helping improve the audio description at the moment. Okay, so now we can see how well it works. So I'm going to show you a few clips, and in each case, you'll see the clip at the top, then the context, this is the previous AD, then the ground truth AD, and then what the model produces. Okay, so here's something from The Great Gatsby, and what's produced is a man and a woman dance in a circle. Okay, that's correct, but not very complete. Here's a second example from Titanic. They're spreading out, the ground truth is they're spreading out a blueprint. The prediction is that they look at a map. So it's definitely capturing some sense of what AD should do, just not doing a lot of it. Harry Potter, the ground truth is his mind fills with terrifying memories, and what's predicted is his eyes widen. Final example, again from Titanic. So you see there's a necklace pulled out, and the prediction is he takes the necklace and puts it in his pocket. So it's not quite right, but it captures some of the main objects. Okay, so that's where we are. So at this point, we have a model which we've adapted GPT by prompt tuning so it can do AD, and it does do it, but it's a bit limited. So if we look at this example on the right, it's again from the Great Gatsby. The ground truth would be Daisy, Gatsby, and Nick swim on this private beach. Okay, that's what's going on if you understand the film. And what this gives is a man swims in the pool. So you can see the main problem at the moment is it's not naming the characters. And that's very important for AD. So 40% of AD mentions the character. So it's very important. It's not doing a very complete description of the scene, and it's not predicting, and this is sort of a small thing, but it's not saying when it should predict AD. We're just giving it a clip and say predict AD for this. So in the second part of the talk, I'm going to try and improve on all those three things. So who is in the scene, what they're doing, and predict when. Okay, so that's what I want to do. And we'll start off with when. I'm going to do this quite briefly because this is relatively easy. So when you're doing AD, you mustn't speak at the same time as the characters, because then you can't understand what's going on. So you can only speak in the gaps between when the characters speak. So here's a short example where here's a speech shown in bluish color, and the AD happens in between. And basically, if the gap is less than a second, there's no AD, and if it's more than 8 seconds, there's always some AD. So it's really like a binary decision problem. You see a bit more. Here's a zoomed out version of when the AD is versus the speech. So maybe you just have to make a decision. Should I do AD here or not? So we proposed a model which takes in the video, the length, and then makes a binary decision whether to predict AD or not. You can read about this in the paper. It's a paper at this conference on it. What I want to spend more time on is the who, because that's really crucial for AD. So who is in the scene? And I want to improve that. Okay, so the way we're going to cast is we're going to have this idea of active characters. So in a movie, there'll be lots of characters. What we want to know is in this particular clip, who are the active characters that the language model could talk about? That's what we want to supply the language model. And our idea is that if we tell the language model the names of the characters and give them examples, this is what this person looks like, and here's what they're called, then when the AD is produced, it can name them. And that's what's going to happen. So how we do this is we're going to supply what we call a character bank. So for each movie, we'll have a different character bank. And we just create this character bank, supply it, and then as the model goes along, it can look at the character bank, find the active characters, and just do the AD based on those active characters. Okay. So the problem here is that there's been lots and lots of research identifying characters in movies, lots of good, very good research, but we're going to take a much easier method, which is to just look it up on IMDb. IMDb has all this information. It has the character names, it has the actors' names, it has also examples of the actors. So we can easily download this information from IMDb. Okay, so for this film, Out of Sight, we can get all the principal characters, we can get examples of what they look like, and the actor's name and the character's name. Okay, so this is easy to get. We then actually have to do some computer vision. Okay, so far there's not really much computer vision. Now actually some computer vision, because the sort of pictures you get on IMDb primarily are red carpet shots, good publicity shots, and that's very different to how the characters appear in the film. There's a domain gap between the two. This is the bottom example. This is Ben Kingsley, nice actor photo, and this is how he appeared in various films. There's a big difference. And if we just start off with these actor-like photos from IMDb, we're not going to be able to recognize very well. So we do the simplest thing possible, which is to take the actor photo, get a clip descriptor, find the closest matches in the film, and pull those out, and they typically are all correct. So here, this is George Clooney from the IMDb website for that film, and here are matches in the film. So these are going to be our exemplars for him when we use in our character bank. And so for Jennifer Lopez here, these are the matches in the film. Okay, so now we have exemplars of each of the key principal actors, and I'll explain how we built our character bank from these exemplars. Now, how do we find the active characters? Because in each clip, we want to find the active characters. Okay, so that's what I'm going to show. And we actually have a module, a network for doing this. What it's going to do is it's going to take in the exemplars we found, use them as queries. So each character, like George Clooney, there'll be a query, Jennifer Lopez will be a query, which is going to transform a decoder. They're going to attend to the frame features because we want to find out who's in this clip, and it will output a binary variable for each character. So in this case, the two characters that are active are Jennifer Lopez and George Clooney. So these two should be 1, and all the other characters are not there, so they should be 0. Okay? So why do we bother to do this? You know, why bother? And that's because, again, you have to use computer vision. So how does face recognition work normally? Normally, you want to say who's in this picture, like this. You'd normally run a face detector, then you'd have a face classification network, which would produce an embedding vector for each person. And you'd go to a gallery, you say, which is the closest vector to this one, and that would how you'd name. Okay, that's what you'd normally do. And you know, lots of good work being done on that. But we don't have that. We just have a clip feature for the whole frame. And from that, we want to recognize who's there. So that's why we have to do this extra module, because we want it to be face aware. That's what it has to learn. It's going to take in a clip feature for the whole frame, and we want it to be able to concentrate on where the face is. Okay, so once we've done that, we've got this module, we train it using MovieNet, which is just the sort of thing we want. And this is showing you how well it works, because computer vision does work quite well now. So the top red curve is after we've trained this module to be face aware. The bottom one is if we just use raw clip features. You know, take a face exemplar for George Clooney, compare it to the frame, clip feature, and say, is that person there or not? So it's a significant improvement by making the module face aware. Okay, so now we have a way to summarize. So for each film now, we've trained that module, that's all been trained once. So now for each new film, we download all the principal characters from IMDb. There'll be face actor pictures. We get in-domain exemplars. That's our character bank for the film. That's done once. Then we process all the clips to find the active characters, and we're going to provide the active character as names, actors' names, character names, and exemplars to our language model. So here's what we do. You've seen the prompt tuning GPT language model already. We add in addition, so on the left here, you see the clips that we want to generate the AD for, the audio description for. Here are the face exemplars, and here's the information we supply to you. It says, for example, here are possible characters as a prompt. Jack, played by George Clooney, and there's here the images of him. We do that for all the characters who are active in that clip. Okay. Now, so that's great. So we could just go with that, but we also want to improve our architecture. So far we've been doing prompt tuning, which means that we're mapping from the vision to the language tokens. Okay, and this is sort of the idea that is in ClipCat architectures and Blip. What we change this to as well, compared to, is a Flamingo-like architecture, where instead of translating directly from visual features to language tokens, we let the model cross-attend to the visual features. So it can cross-attend at many layers in the language model. The language model is still frozen when you do this joining up, but it's a different way of adding the visual features into the language model, and it can attend more closely at many layers. Okay, we can compare the two, and in this case, using this CIDR measure, which is comparing the audio description we generate to the ground truth audio description, it's caption loss. The cross-attention GPT gives better performance than the prompt tune one. Okay? Doesn't necessarily always mean that, but it does in this case. Okay, so now we've got all the elements together. We've got characters possibly named, we've got a slightly better architecture, and we can see how well it works. So I'm going to show you a couple of examples. This is Harry Potter again. So here's the clip.
Concentrate, Potter. Focus.
And here's what it predicted. So it says Snape points at Harry, so it correctly named the characters, and his eyes closed in horror. So it really is getting quite good now. I'll show you one final example.
So how are we going to get to London?
We fly, of course.
Okay. What it generated was Hermione, Ron, Luna's eyes are fixed on Harry. So again, the characters nailed that. We're standing in the doorway. Harry rides on the horse's back as the horse is up in the air. Now, some of you can spot this isn't a horse. Okay, and so Harry Potter film, you know, where people who someone would shout out what it is. Louder. It's a festival, isn't it? Festival. And if it had learned all the way through the film, that was introduced earlier in the film, so we don't have long context understanding yet. There's work to do, but it's getting there. So I'm ending, that's my ending slide. So we've introduced this new task of generating AD, and I've argued that it will understanding. In terms of it working well, the character bank significantly improved it. Because we're using clip features, we're somewhat limited on the what. Clip features are like a bag of nouns, but they're not doing so well on the verbs or the spatial layout. So we need better visual features. And the when also needs to be a bit improved. Okay. So going forward, I think this is a task that people should work on actually. There's lots of improvements we can make, as you can see. What I'd like to get to eventually is not just generate the AD, but able to have a conversation. We can answer questions about the movie. And here's some resources. There's a couple of papers we've published on this already. Audio AD1, Audio AD2, the sequel, and all the data is available on websites, so you can work on this. The context, so it sees a clip, so that's a fixed length. The clip is defined by where somebody speaks until some next person speaks. So that's the sum length of the clip you can see. There's a certain amount of context in the visual information, and then the other part of context is in the previous ADs. And at the moment we only give 4 or so previous ADs, but I think that's not somewhere else. Language models are taking more and more information in, so we can have much more memory effects, either directly just by having more AD or just by having some memory vectors. We haven't done yet. So I don't think the context is working very well yet. I think it's stopping it saying the same thing because it knows what it's just said. It doesn't say the same thing again, but definitely the context. And that's, to me, that's where the real thing should come, because the context is going to be the story understanding. Get through. A good question. At the moment, I don't think maybe someone knows here more than this, but I don't think you have different audio descriptions for the same film, like for children and for adults. I imagine an audio description for a cartoon aimed at children would be different from an audio description for a feature film like this. I don't think they provide, at the moment, multiple audio descriptions for the same film. But there are guidelines. When you do audio descriptions, there are guidelines you should follow and you're trained for. I know volunteers are doing a lot of these, but they say these are the things you should talk about, these are the things you don't need to talk about, and you can look these up. So maybe that's taking that into account. I wish it was. Mine's never age appropriate, but yes, it should be. Yes. Yes. No, I understand your point. I'm just saying, I think in practice it's not done at the moment. It's more film dependent, the level of audio description that's given.
Thank you. I have some question about the model that we put the on the frame and then subtitles and then the description. Since here we don't have that much order. Is it important to add?
Well, I mean, the details I'm not going into. So there's still tokens. Things are put in a certain order. It's trained with things in that order. There are special tokens defined in one of the models. So I think the information is there implicitly. It doesn't receive all this like as a jumble, and then it has to sort it out. It's always trained in a certain way. Yes, I mean, in the GPT prompting one, there's actually a token that says, here's audio description starting, here's audio description ending, and subtitles, here's... I see. You mean the actual, okay, I understand. You mean like give the actual, the temporal information of when they, yeah. We haven't done that yet, it's a good point, yes. Yeah. I think the whole way of how you supply time to models, you know, that can be investigated many times, especially when you've got simultaneous overlapping segments. So why it worked better? I think it's just got more access to the visual tokens because the cross attention is running all the way up the layers of the language model. So I think in this case we're not training, these aren't giant models. This GPT-2, you know, so any help it can get. I think in this case, I mean, if it was a much larger model, this might not be such a difference. Okay. Yeah, so that's I don't really want to get into that. That's not really my I'm sure that will come, you know, starting at maybe the cartoon level and very quickly going into full 3D rendered images. I'm sure that will come.
introduce السي والثلاثة والتايتلز بس وبعد كده تلاقي ثلاثة مع بعض وبعد كده في questions.
I want to set up your recommendation related to the prompt, the kind of global prompt. Kind of yeah. So the experience like that key value and yeah.
We're starting our orals now.
Okay, hello everyone. Now we will start our oral presentations. So we split them to two halves. First, we will present 3 papers, then we have QA sessions, then we will continue presenting the other 3 papers, then also we will have a Q&A session, okay? So the first paper will be sparse linear concept discovery models. The second one will be zero-shot and a few-shot video questioning answering with multimodal prompts. And the third one will be multimodal neurons in retrained text-only transformers.
Hello, everyone. The person is very happy about the discovery models. There is different text available by information. However, in this there are false. That is that then creates the model that then will be corresponding out here in the decision process. At the same time, it's next person information. It is high anxiety problem, especially safety or bias. And thus contribute to social well-being. Like there is a focus on data comparison, where command is really a very fair, some important model in the proprietary across the board area. It's very nice to implement the better responses that in textual and a linear indicator. Sit down, I see it's formulation or we start the and her content on the second performance, the one stage is what of the finalization where which we give our functions to parity. There is a great mechanical flexibility partial story. Although we see CPMs of the body are the terms, but also these higher part set of points example. We use script of the image possibilities of the text in line then we do a class however, we see the last amount of use and the creation in the same cost. I think in the cost of the guy, neither three elements. The solution is to be there and produce indeed a treatment, not the activity. That even if the presence or not of political. Now they can and the effect was other local license. And I also saw the data, certain one data to the first data and for the company costs all the data for all the stuff. And our way to go is to affect that we will get into the problem. And we will be less. And we are going to go big. We have to more than this. This will be more from the city. When there is general ones it is like to spread out prayer. In God, the very sound was present. For they declared so about years of that creating violation. When the started to use it very long time. During the for the level of Australia, any university with sport aligned for this level. For this experiment,
Hi, I will see the technical. I have a problem. The advantage of individual training power costs. We investigate the allocation of our stage in order to give judgments on the result of training training. To go to the question of that they will enjoy and their engagement to be outside the top to realize their own rules. However, other training of the generation or in data present on check. But to get people giving them more easy and finding the environment for these days candidates significant construct for it. So let's get people going. So I'm going to studying and work taking each and actions. For this I encourage the methods but online opportunities. Composing the renewable every next quarter. We incorporate visions to the course language using that renewable values inspired by those. We introduce a modification network that summarizes the game while the important to crash. In addition, people multiple learning to the mentoring for a person. A huge number of school and developers to be in the shuttle. Here is the only power of the game. If possible, before the event, engagement investment, before the next time of the game, before connecting shown and specifiers. In video frames sometimes, the region will exactly pictures. And if next time we say and then for me, only matters something and language model makes the video understanding and credit for people thoughts. I will put this on dictionary method and additional way. It basically change the purpose under consideration the project on the space, while the dictionary is provide growth. They will be basic in that concentrate the purpose spirit on the visual planning. Focus for instance, visual learning network, adapters, visual and exports, for concentrating the purpose spirit. Our visual learning network allows the parents. The non-commission works, the result video, opposite says the example the same destination. BDI consists of number of players. Each part of the process actually being normally with blocks and individual features followed by that hash. And BDI is not by the special per person. The later shown incorporates several of these blocks in the PI model fashion, each layer of players model. Each other projects of each other and for there to formulate. The other project is spoken rules and animation relates to correction. The conference is the one of those of organization of the English language is getting mistake. In the first stage of the English language, the one is on the website. And what is it from violations? In the observed parameters, analysis on the project by looking at the from the laws on web to the others. And the observed by the mechanism, but it must be with plans. We also perhaps to remind us on a specific relation in paper, finally into this people and that are members. If I took on the proper picture, then there's a vital problem. It should be sufficiently in class A as well. In future method provides that effect teaching on language. And we are able to follow. These traffic settings, first one, identical parameters, which correspond 8% of the parameters. Second is identical blocks, which correspond to 0.26% of the parameters. They also outcome of the word. And this is the initial level of parameters in all blocks by research. For the first time, we choose not only for learning for the divisional set. I will provide a study of fewer parameters from visually different classes. In proportional network of divisional set, translating region into testing while the number of dash. Our proposal of the parameters only not with the divisional network. In both version and the players. In your case, they will publish it. Thank you.
There is still 5 minutes left when we have for the weekly calls. But that was basically I was trying to be exercise to
Hi, I'm Neil from ICCV23. I'll be talking about multimodal neurons, the technical vision language architectures. Transformer language models perform a surprising number of anomalies from predicting next moves in game, protein design, or even answering complex questions about images. When we path with different modalities of vision, a common framework for aligning visual features representation states of text transformer is the federation translator and text encoder, and when we're directed to the teams of the game prefix to be the thought process of language model. These image prefixes take different forms depending on how they're encoded, and schemes range from using raw image data to a simple task. Using encoder release is provided by different language language. The second half of the final total neurons that are responsible for and text same command. You can vision and language very the same on the line. But interestingly, the recent Timber study shows that a multimodal model still successfully captures images in this matrix image components and never connects to text. And the matrix components are never connected before. We studied this model that is self-provided data image encoder, frozen data text decoder, and learned One possibility is that actions are already considered by linear. We can actually evaluate this here. Let's take a look at a single example actions after its features are introduced, and then cast into the input state of J by linear layer. These image prompts don't correspond to discrete image arrays, but we can use code simulator to find 5 layers of data. Not very rigid. In fact, random reference sample from the embedded space can be put it the same way with quite. We can measure how well the system is described in this way. We find that the distribution of the scores prevailing random models are extremely using data. But as a check, for example, from the ground truth image packets have much higher scores. So the image prompts occupy some substate that is accessible to the technical, but is readily decodable to the vertical. Actually, a deeper inside the transformer and see if we can trace the conversion between modalities to digital neurons. It's been shown that MLP layers inside the MLP operate as a p-value memory and are relatively interpretable, but to date they've been studied in language-only settings. Study the image features identify units with a high influence on model output using a gradient-based score to produce the first round of image patterns neuron activations. Once we've identified these units, we can decode the text data records the model of residual stream by recognizing that they contribute the value for the output matrix to layer. We can feed that row of weight matrix directly into the pre-trained encoder to see what rates are boosted for denoting response to certain inputs. We can take a look at the top 5 on the model layer, decoded for different samples of them and their activations over the data connect. In the paper, we showed that these correlate with the standard input for and that they match image descriptions of images we first for. Exemplars from Coco of maximally activating images for different multimodal grounds show that they are likely to the same images and their proper images. And we can quantify their activity for particular concepts by measuring the agreement of their receptivity of those images. Here's a greater neurons in the same layers. Multimodal neurons have a higher mean IOU score with ground truth objects and features for images in all of those categories, containing only a single object length. In these images, the top multimodal neurons actually themselves perhaps where they can and contributing very late seconds to the model output. Finally, we show that these units positively affect model output. A way that significantly decreases the probability of the original noun output token and also changes pattern content as search for relative to the original action also increases. Random neurons selected in the same layer have a much weaker pattern. We can see in some examples that multiple neurons are successfully able actions came from a dog act with higher bouquet of flowers to the sheep and the traffic on the roads to the city. Please check out our paper in the product page below for more insights. Thank you.
So if you have a question, please raise your hand. And for the author, yeah, please feel free to come to the stage.
So if they didn't produce a Bernoulli distribution, we'll select the Bernoulli DY1. So we train the model using the relaxation that is normal, but for example, and we learn the second amortization. So during inference, we use the paper of the neighbors, we get the Bernoulli output 0 and 1, and these are the concepts we covered per example. So contrary to other approaches that use a class-wide sparsity, you have, for example, sparsity in the same, the one the concept in which the Bernoulli indicators are what. All right. Or we can even say, if they have a probability of being active more than 100, they're active for all exams, for the specific exams. And you have many interpretation of how to believe and the same thing know the discovered common, right? So either how to discover and you see how many are active, or we have probabilities and the question of something like 1 in 100, 1 in 1,000. So if, for example, you can compare class sum and if you want, the examples for all the examples in one class, let's say for this class, have these discovered concepts, or another class, have another set of and so on. You can analyze a lot of stuff, between classes, in classes.
Yeah.
So we only did this for one thing, never this number, because we were particularly interested in the number of visual encoder was only trained on the text encoder was only trained on text, and we would probably have some results for multimodal models where the visual encoder was trained on text, but we were particularly interested in that setting. So I think that if you train a visual encoder in different ways, then it could learn more representation before and potentially have better equating after the. But I think in any case, the transformer is has a way of operating on visual inputs to extract technical features from visual.
Check the screen.
I think you could explain for that. It's one thing that you can about all the way. As long as that using the goal of we had another factor. The line that going to be that, for example, you can learn to be graph of like attacking that one when those lines that because it's very difficult to private that. In this case, I still think that you just provide language for that and kind of level of education for all that aspects of office we should find out and that's discussed. Also, so my point is sometimes I think that that's really those things which is difficult to describe by language. For example, with the spot of that line, this kind of that line.
Yeah, I think like models trained with grounding in text are like generally capable of understanding more complicated concepts like that. In our case, it was basically instead of just using a visual encoder, allowing the transformer to operate on image prompts, let the process the image in more complex ways and probably answer more complicated of image. So I do think like multimodal models with grounding language, your transformer can lots of data, essentially operate on more complicated. But, yeah. Okay.
If we don't have any further question, we can proceed.
Thank you. Now we'll start the second part. If you want to just share the screen, that you can just share with the screen and want to be live within the 5 minutes screen, we can do that for some people requesting that. So that's what you find if you want to do that. The main point is kind of time.
Okay, so the rest of the oral papers is as follows. The first paper is simple token level confidence improves caption correctness. Second paper will be course to find constructive learning in image text graph space for improved vision language compositionality. And the final paper will be visual coherence loss for coherent and visually grounded story generation. Okay.
Hi, everyone. My name is Susie Petrick, and I'll be talking about caption correctness. This was a joint effort between UC Berkeley and Meta, along with my co-authors Spencer, Joey, Trevor, and Anya and Marcus. Assessing how well a caption matches an image is an important part of vision and language understanding. People usually accomplish this using image text matching scores from a pre-trained model. However, the Winogrand task, one example shown here, found that even state-of-the-art models find this task challenging, so they might match the wrong caption to the image. We propose that the issue with this is that it's done in one pass from full caption to score, and it might encourage the model to treat the caption as a bag of words. And so instead, the matching should be done at a finer grained level, which brings us to our method. So we take a pre-trained model and we fine-tune it on image captioning. Then, given an image and a proposed caption, we can get confidences for every token in the caption. We can aggregate them. So for example, just by taking an average to get a single estimate for image caption correctness, one that's finer grained than that of image text matching scores. We call this simple method token level confidence, or TLC, and there's two types. So I'll talk about the second one in a minute. First, I'll briefly show results for a TLC-A, where we use algebraic confidences directly from the output distribution. So for example, using the logit or the softmax score. Testing this on Winogrand, like in that example that you saw earlier, we try TLC-A just using the average softmax score over the sequence. And we find that it consistently increases the group score across the range of model sizes of OFA, which is a vision and language model. So next, we try learning the confidences instead of using the distribution directly, using an in-domain data. So we start with a frozen captioning model and we train a confidence estimator on top of it. So for example, a few layer transformer. We sample a random ground truth caption image from the validation set, and we take a random time step within that caption. So say we start with a dog. Our goal is to predict whether or not the captioning model will get the next token predicted correctly. So we input the image and caption prefix into the model and get image and token embeddings. And then we let the captioning model predict the next token. So say it predicts standing. We feed these features into our confidence estimator and train it with this binary classification task. So the goal is to predict whether or not the caption prediction matched that of the ground truth. So here it was incorrect. And in inference time, we can simply take the predicted caption instead of the ground truth one. And so we also find that taking the rest of the sequence as input to the confidence estimator improves this prediction task. So now that we have ways to get token level confidences, we can use them to reduce hallucinations during beam search. So starting from the top beam, we search for all COCO objects mentioned in the beam, since we're doing this in the COCO dataset. And we get the confidences for each of these objects and compare it to a threshold that we found on the validation set. If any of the confidences are below a threshold, we reject that beam and move on to the next one. And we do the same thing, get the confidences and compare them to a threshold. And so we keep doing that until we reach a beam where all of the objects have a confidence above your threshold. We show that both TLC-A and TLC-L can reduce hallucinations compared to the baseline caption, while increasing caption diversity. This comes at the cost of a slight drop in captioning metrics, which prior works have shown do not measure hallucinations very well. And using TLC-L, we achieve state-of-the-art object hallucination rates on COCO. Qualitatively, some interesting things happen. So sometimes, for example, in here, the TLC-L caption has a more general concept like fruit, whereas the original beam has a more specific concept like apples, whereas the image was kind of ambiguous. And we also find that we can also fix misclassification errors in the original beam. So overall, remember that even state-of-the-art vision language models can struggle with caption correctness. And TLCL is a simple but effective way to measure correctness and reduce hallucinations. We have more results in our paper, and feel free to talk to me here at the poster session or send me an email. Thanks.
Combination. As an example, on the right, we see an image, a sentence in green, which describes it as the green plant and the white bird. A state-of-the-art clip model fails to match the image to the correct sentence. It gives a higher score to a minimally perturbed sentence in red, which has shuffled attributes between objects. So our goal in this work is to improve compositional reasoning capabilities of VLMs with a focus on models trained using large-scale contrastive learning like CLIP. For improved compositional reasoning, the model needs to capture both coarse-grained information, for example, high-level object information, and fine-grained information like relationships between multiple objects, fine-grained attributes of objects, etc. And this serves as our first hypothesis. Secondly, we also hypothesize that incorporating and improving relevant hard negative samples during contrastive learning is necessary for inducing fine-grained reasoning skills over these in these models. We now describe our model, Mosaic Clip, which consists of two main components. We heavily rely on scene graphs as an intermediate representation of text, which succinctly captures the information about objects, relations, and attributes. These are easily obtained using off-the-shelf parsers and help in decomposing the text into multiple subgraphs as shown in the figure. The subgraphs have coarse-grained as well as fine-grained information. Each of these subgraphs can explain a part of the image, and hence this subgraphs as well as the text which we derived from these subgraphs will serve as a positive text for the image under the standard large-scale contrastive learning setup. We use simple negative mining techniques on all subgraphs to create hard negative subgraphs. Keeping all this in mind, we will now see how we can use coarse to fine-grained subgraphs as well as hard negative graphs during contrastive learning. In this slide, we describe the contrastive learning process of Mosaic Clip and compare it with standard contrastive learning setup as used in Clip. The key difference is that in Mosaic Clip, we match one image to multiple texts. These texts are derived from the multiple subgraphs which were decomposed from the original text as described previously. We also include hard negatives in the batch while contrastive learning, which allows the model to learn fine-grained understanding of objects, relations, and their attributes. Note that we do not explicitly model text scene graphs, and all subgraphs are first converted back to text, following which text representations are made using a standard transformer as also used by Clip. The main use case of scene graphs is in decomposing text. We now look at some of the experiments. We measure the compositional reasoning abilities of our model, which includes aspects like relation and attribute understanding, systematic generalization, etc. We also measure the effect of our approach on general representation learning tasks for VLMs. After this, we analyze the reasons for improvements in compositionality brought by using Mosaic Clip. While analyzing the compositional reasoning capabilities of Mosaic Clip, we see that First, on an average, our methods improve systematic generalization capabilities by about 11 percentage points as compared to NECLIP, which is a previous approach. And this measurement is done over the PrEP dataset. Attribute relation and word order understanding also improves by about 9 percentage points as measured on the ARO dataset. Further, MosaicClip gives large gains in both pre-training and fine-tuning settings. For robust experimentation, we test MosaicClip over 5 training datasets, 3 model architectures, including a vision transformer and resonant backbone. While performing evaluations on 11 zero-shot test sets, we see significant performance gains over all these settings. Productivity is also an integral aspect of compositionality, referring to the ability of the model to understand increasingly complex sentences. While our model is not explicitly trained to generalize to larger sentences, we find that fine-grained and hierarchical understanding of sentences and images achieved by using our methods also leads to improvements in productivity. On the CLIP productivity dataset, we see a consistent significant increase of performance of MosaicClip as compared to CLIP and NECLIP, increasing over the best baseline by nearly 12 points over the whole range of complexity of the text. While gains on compositional reasoning datasets is the main goal of our work, we see that our methods also consistently improve vision language representations, leading to improved performance on classification and retrieval. Gains achieved on the elevator classification benchmark is shown in the slide. We now seek to understand the reasons for improvements in compositional reasoning performance when we use MosaicClip. For this, we analyze the tree score of the language encoder of our model. We find that MosaicClip's tree score is always higher than NECLIP's tree score, suggesting that MosaicClip's text encoder is performing more tree-like computations. More tree-like computations are evidence for improved language-side compositionality. There are a lot more results and analysis in the paper. Please check it out and drop by our poster.
Hi, I'm Xu Dong, a final year PhD student at Max Planck Institute for Informatics and Saarland University. I'll present our work, Visual Coherence Laws for Coherent and Visually Grounded Story Generation. This is joint work with Vera Denberg, Asta Saeed, and Bent Schiller. Why do we care about stories? Stories can capture our experience, construct memory, and help us to understand meaning and make sense of the world. The most typical way of storytelling is to construct a story based on events and characters from visual perception. We therefore chose to work on the visual storytelling task, where the input is an image sequence and the output is a story conditioned on the input images. Each sentence in the story corresponds to one image. The pure state-of-the-art model, TAPM, can generate readable stories. However, the system still produces incorrect referring expressions. In this example, the model generates Dave instead of Jack in the last sentence for the protagonist, which appears across 4 images. The main problem is that the characters are not visually grounded on the images. To tackle this problem, we make the following contributions. Firstly, we design an evaluation metric for the visual grounding of the characters in the stories named character matching. We then propose a new loss function named Visual Coherence Loss to encourage the model to generate correct referring expressions for the protagonist. In addition, we also experiment with different character features, but I will not present it here due to the time limit. Our work was published in the findings of ACL 2023. Traditional metrics for visual storytelling, like Meteor, is reference-based measure, which cannot capture visual grounding. For example, here is a story with higher Meteor score, but it contains more referring expression errors. To evaluate character grounding, we propose a character matching metric that compares the sentence character matrix with the ground truth image character matrix by computing the dot products between them. We then use the average of weighted maximum matching on the output matrix as the final score. Experiments show that the metric correlates with human judgments. More details are in the paper. After defining the metric, we use it to evaluate previous model architectures like seq-to-seq and TAPM. Results show that the generated stories from these models have much lower character matching scores comparing to human stories, which illustrates that the referring expression error is still a major problem. This is due to the fact that the previous models do not represent recurrence of the characters in the image sequence explicitly. To tackle this problem, we propose a new loss function, visual coherence loss, which captures the character recurrence without human supervision and encourages the model to produce correct referring expressions. For more details, please refer to our paper. Our experiments on the visual writing prompts dataset show that our model outperformed previous baseline over both reference-based measure and character matching metrics, and even approaches the performance of the model with Oracle information. The case study shows that our model produced less referring expression errors but maintained high story quality. In summary, our character matching metric can better capture visual grounding of generated stories. Our coherence-driven loss function helps model to learn better representations for image sequence to capture recurrence of the characters and produce better stories. Thank you very much for your attention and feel free to ask any questions. I'm also available at the poster session.
Please, if you have any question, raise your hand.
So there are some that we are completely wrong. This is depending on after that. But how do I have research on this? I think it's really still and perhaps a model validation system that they actually love this and help. So with the distribution, I really think that by fixing a lot of the behaviors, we get a lot more clear actions because models generally more long concepts. So yes, that would be opposite factors in that there is such a complicated research often seen in like so when we're we get this object in more correct, but actually we have to classify it and we don't have any
I'm sorry, I couldn't get it. Could you please rephrase a bit, like loudly? Could you please speak up a bit?
Okay. This is the loss function in the paper encourages the co-occurrence of the characters, right? So if there is a hallucination in the generated story, for example, if one person, if a person didn't hear in one person, but I will generate a story and include the person.
Okay. if I get it correctly, you meant whether there are hallucinations from the language models and whether the loss function can capture it, right? So yeah, so the purpose of the loss function is designed to capture the recurrence of the characters inside the images, and also like learn a better representation and to enforce the language model to notice this kind of recurrence and improve the coherence. So that's the purpose of the loss function. Yeah, so it's not directly operate on the language, but on the images. Yeah. Okay. Thank you.
Also the question for the second, so the last paper. So I might have missed this, but does this model also work for unseen movies, unseen characters? And it's sort of how does it ground, like the other character, and how does it ground images and characters?
Do you mean like unseen characters from like others image sequences or the same image sequence?
Well, if I just randomly improvise the image sequence, how do you know what the names of the characters in the scene? The idea that the character bank is in the names. Like how do you in the time lapse in the decoder of the function or the line input, it says Jack. How does it map Jack to the image of the character to simply see that character? You don't have to miss that.
Okay, I got it. So basically, we only generate placeholders at a test time. So because we replace all the character names in the training set. So to make sure, like you know, I mean, we know what characters that we are feeding to the model. And so that's why, you know, if there's unseen characters, it's like most probably either hallucinated by the model, or it could be some person bounding boxes that are in the image sequence, but it's not the main character. So that is possible that the model can hallucinate it. But because we have Go annotations for the main characters, so the metric can actually capture these, and to make sure the model is not generating something that is not in the annotation. Yeah.
So, I have a question for this.
So I wonder if you have maybe connected your work to the paper crepe or sugar crepe.
Which second or first? Can you recall?
I think the paper that integrates trees into.
Yeah, this one. Okay.
Yeah, into to facilitate convolutional clip.
Yeah. Which slide?
It's just a question about the method.
Okay. Okay.
Yeah. How relatable this is to the maybe crepe or sugar crepe benchmark?
Is the question for me?
If the author exists over Zoom, please feel free to unmute them.
Hello, can anyone hear me? Anyone?
Yeah, now we can hear you. Yeah, go ahead.
Is the question for me? Can you repeat the question, please?
So, Mike, did you evaluate on the crepe or sugar crepe benchmark? I think it seems to be a benchmark for evaluating conditionality. Did you use that benchmark for evaluation, or do you have any comments on using these benchmarks? Because we have some other methods for generating these negative examples. Your approach is more informed by the graph structure or the C graph structure, but they also propose some other way that maybe not graph based. Have you related to what these efforts or these baseline?
Okay, so the voice was not totally clear, but from what I understand, the first part of the question was that if crepe and sugar crepe like datasets are relevant for our work, and that is definitely true, because we in the initial work, in this work, in the paper as well, if you check, we have evaluated on crepe, and it's definitely a relevant data set, and we see that there are significant gains in systematic generalization. The newer version sugar crepe dataset is an improved version of the crepe dataset. And although it's not in the paper, but I did evaluate all our models when the paper came out, when the sugar crepe paper came out. And I was seeing significant gains on that dataset as well. So this work is under review, but when this work is accepted somewhere, I will add those results also to the camera ready version, the sugar crepe results. If there's a second part of the question, I'll love to hear that again. If there's a second part of the question, or if this answers it, yeah.
Thank you very much. Okay, I
Thank you.
think that's it for the Q&A. Yeah.
I would like to participate in the session with the laborers. Thank you. After they will be fine also for engaging.
Break message. We have a lunch break and then this is.
That's the full program.
Yeah. Almost number one.
Yes. This one is.
لو تعرف بس انت تتاكد ان كل نيكست سبيكر موجود All right. Welcome everyone again to our workshop on closing the loop between vision and language. So in this session, we have a great lineup of speakers coming up. So without further ado, our first speaker is Trevor Jarrell. Trevor is a professor of computer science at UC Berkeley. He founded and co-leads the Berkeley Artificial Intelligence Lab, BEAR, the Berkeley Deep Drive, and the BEAR Commons program in partnership with Facebook, Google, Microsoft, and Amazon. Trevor's group has conducted groundbreaking work to develop algorithms that enable visual recognition across a variety of platform applications. And Trevor's research interests include computer vision, machine learning, computer graphics, and perception-based human-computer interface. So please welcome the speaker.
Great, thanks a lot. It's fun to have the projector right in my face so I can just look like I'm like in the spotlight here. Thanks. Does it need to be like that close? Okay, good. How about that? It's fun to be here at a workshop in vision and language. I think, several years ago, it was interesting. It was controversial or like different to be in a vision and language workshop at a computer vision conference, but I think increasingly the entire field is becoming vision and language. So we are at the center of, I think, the revolutions that have happened that are changing the field, and it's exciting to see all of the work we're doing. And there's been a lot of recent advances in language models and large-scale language models, especially for vision, and I'm going to talk about that today. Actually, we already had a relevant presentation from Susie earlier today, and she has a poster in the back on token level correctness. I'll just mention that, but you already saw that. There's really 3 or 4 things I wanted to spotlight in addition to Susie's work. One is our work on sort of visual language models, mass reconstruction models that can do in-context learning, and some technical innovations we've built on top of MAE and whatnot. Okay, how do you get the little talking thing off there? That's interesting. Always the problem with these Zoom remotes. Maybe you can move that. And then I'll briefly talk about, no, it's on your screen. Then I'll talk about multimodal language models for social gesture, building on some earlier work we had last year, which learned how to turn take and respond to social gesture. And now we see in our most recent iteration of this work that you can use a text-only LLM actually to learn a lot of this. I'll go into detail on that. And then as time permits, I'm gonna also talk about how our vision and language models can be driven by LLMs, how modular and neurosymbolic architectures can solve a lot of challenging EQA challenges. And then last but not least, there's a whole lot of eye candy that I've got rolled up to show you on how vision and language LLMs can actually generate much more accurate image and video creations using the LLM as essentially the layout or cognitive part of image and video generation scheme. So I just want to remind everyone, hopefully you're here, you saw Susie's talk, token level confidence improves caption generation. This is the idea of looking at individual tokens, building a confidence predictor of each. And if you're interested in more of that, look at the poster in the back. And so let's talk about visual language models. This is work that began a year or 2 ago, led by Amir Bar, also in collaboration with Tel Aviv University, Alyosha, and also with Meta in the follow-up work. And here we're taking vision models that I'm going to call visual language model, also could call it computational inpainting. And we want to basically, inspired by what you'd see in language models, the ability to in context learn with a few examples of a task, here a natural language task to do translation. Let's do the same thing for vision. And we showed in our previous work that a mass reconstruction method that we would normally think of as an in-painting method or MAE or MIM can actually in context learn new vision tasks. So if I give it a task description in the form of an image pair, which is showing an input image and a segmentation of that input image, and then a query of a new image, it's like an image analogy. It could be several different kinds of tasks. A single model for masked image prediction is able to in context learn each of these tasks. We set it up as a single image. We block one of the tiles and ask a visual language model to infill the answer. Indeed, surprising to us at the time, and even in retrospect to some degree, it works much more often than I would have expected. This model was trained actually on computer vision figures from computer vision papers. So by taking figures from computer vision papers, training a model to do mass reconstruction on that data set, we were able to build a model that just from a in-painting reconstruction loss could do this sort of in-context visual learning or visual analogies. It wasn't exactly MAE. We used a quantized version of MAE, VQGAN encoder, and then mass reconstruction of those predicted tokens, but similar in spirit. And at test time, it could solve tasks including segmentation, colorization, of course, in-painting, or edge detection. So this is cool, but it has some limitations. Tasks might be ambiguous. Sometimes there wasn't aligned input and output, or just it's just too hard of a task for a vision-only model to do alone. So in the true spirit of a vision and language workshop, the innovation that we're recently reporting is to go beyond just visual reconstruction, but now, of course, to multimodal reconstruction. And I think what's interesting is to see how simply this can be added in a modest scale architecture. I mean, we're not talking trillions of parameters, but we're taking this earlier work that was really trained on like on the order of 100,000 computer vision figures, and now adding text to that to improve it. So here we have the results from our NeurIPS 22 paper, which could in-paint, but sometimes would get it wrong. Like it didn't really realize that we wanted the entire aircraft in this example. So the solution is actually to add text. In fact, this was when I would give the talk last year for this work. I would say, hey, future work, let's not just look at the figures, let's also read the paper, or at least let's read the figure captions. And indeed, the figure captions can tell this reconstruction model what kind of task to perform. And of course, we can do both. We can have an image analogy and a textual description of each of the tiles in this image analogy and reconstruct the image. And the results are much stronger than we had seen before, and also applicable to a variety of different kinds of tasks. All of these in context learned on the fly by a single reconstruction model. Depth prediction, normal prediction, image generation from depth, image generation from normals, and so on and so forth. So this data set is now not just a figure data set, but a captioned figure data set called CCVF. And the architecture now incorporates a clip encoder to condition via cross attention the decoder and encoder stages. So it's pretty simple multimodal architecture. And it's obviously asymmetric. The reconstruction is still of the pixels. We're not doing reconstruction loss on the text. But the results are significantly improved, as you can see here. It can actually having the text and the location and even the class that's of interest can really improve the in-context learning. So you can see here, actually the text often controls the result. Even if you strongly try and prime the model with a visual cue that it should in-paint a red B, if you tell it in text that it should put a red T down there, you're going to get the T. Okay, and their baselines including stable diffusion that we compare against. And if you're interested, I'll refer you to, I'll skip this and refer you to that paper. Along this line of mass reconstruction, I wanted to quickly spotlight two different projects that are relevant. One that's relatively recent, which is improving mass reconstruction, especially this quantized token mass reconstruction. This is work that's collaborative with Meta and Tel Aviv University, led by Amir Bar, who also led the previous project. And so you're all familiar with mass reconstruction models of various forms. They're advantageous because in contrast to other forms of unsupervised learning, they don't require knowledge of ad hoc or arbitrary or wrong augmentation invariances that you're assuming. But there is kind of a problem with the traditional setup. Like you mask out half your image and you need to reconstruct it. But in the real world, you don't really know where things might go. We don't know whether that tail is to the top or the bottom. At least this is the best intuition that we've come up with to explain the following model, which turns out to work really well and improve performance in MAE, which is simply to add noise to the position embedding of your mask tokens. There's one of those, it seems like every couple of years I come across something where there's like this unreasonable effectiveness of noise story that arises. But here's a case where adding noise to your model ends up improving performance. The architecture is very simple in this model that we call STOP, stochastic position encoding embeddings. Typical MAE, we've got tokens that are observed. Those are the ones in gray without the blue dashed border. Those have a regular position embedding added to them. And then the mask tokens, the ones that have the dashed blue boundary, they have a position encoding added to them and also a random noise vector. And that's it, that's the architecture, and that works. This is built on top of IJEPA, and I won't go into details about that, but it's similar to what we saw in the previous part of the talk. And it significantly improves the performance of this model, very close to what you could get if you do assume, and sometimes even exceeding the performance of contrastive learning, which makes assumptions that sometimes are inappropriate. Just one of the interpretations on the right here, the features learned with the stochastic embedding are often more semantic and less simply correlated with the location on the object, but actually the appearance or the semantic structure of the object. The other innovation I want to point to along this line of mass reconstruction and visual language models is a paper that'll be presented at the main conference called Scale MAE. And in the MAE family, it's scale is often a challenge. You can train your model across multiple scales to deal, especially with situations like geospatial imaging or medical imaging. But in these cases, it's kind of interesting. You know the scale. You've got a sense of ground sample distance. So what Scale MAE does is say, let's take advantage of known scale, because we don't want to suffer the problem that we see on this slide, which is if a model is trained at one scale, it'll probably fail at the other scale. And we don't really want to necessarily have per scale retraining or all of the augmentations across scale. We simply want to tell the model that pixels come at different resolutions. And we know ahead of time in this case, what is the resolution here of the image of the Arc de Triomphe at two very different resolutions. And if we're doing mass reconstruction, we can build a position embedding that has known scale. That's essentially the main idea of this scale MAE. Also adding a multi-resolution, multi-scale pyramid, decoding or reconstruction block, I should say. And the results are significantly improved again. So here are these two ideas that I wanted to highlight in this masked image modeling family. One is adding noise for quantized embeddings, and here we're looking at scale dependent and therefore scale invariant performance for position embeddings. And that will be at the main conference. Okay, so second sort of somewhat of a significant pivot here, away from mass reconstruction to multimodal models for social interaction. Social interaction is great, gestures prevalent throughout all of our interpersonal interactions. We like to model how people interact face to face, and Yvonne Ng led this work last year that was presented at CVPR 22, where we model dyadic dynamics between two speakers. So we have the input from one speaker, and from that, we'd like to generate the motion of another speaker. And at the time, we were just getting out of COVID, and there was all this video from talk shows around. This very nice data set that we constructed of one speaker speaking, another speaker speaking. And we constructed what I'd call an autoregressive vision, or actually audiovisual predictive model, kind of a language model, which could actually predict what one speaker would do after watching another speaker and predict the spatial emotion. This is sort of the nodding and smiling of social discourse. There weren't any words or text used in this discourse, and I'm not going to worry about generating the audio for this presentation. And we can then also texture map or skin the output to see the performance of the model. And we had as I said, an autoregressive predictor. This was not like a large scale language model, and it could generate very nice results. Got a nice little joke here, but we'll see the limitations in a second, and we'll see that in a second that surprisingly a text-only LLM can then capture all of this as well, and that will be the update. So text-driven listener, and that's the latest work, which is also going to be reported at the poster in this conference. And surprisingly, you can take all of the, you can basically just take text of the model, maybe also including the punctuation. The punctuation turns out to be pretty useful for this kind of gesture. And from that, generate sequences of moving head gesture, head motions to generate compelling interactions. So here you can see same motivation, dyadic conversation. We have one speaker. I'm not going to bother to show the audio or play the audio because the audio is actually not important to this part of the work. But you've got the speaker text. Just from the speaker text, you can generate predicted listener motion and then render that with a textured video. Here's the model architecture. It's an underlying text-only LLM that's been fine-tuned to this dyadic gesture task, where additional gesture tokens, which represent the head motion of interaction of either the speaker or the listener, are introduced into the model. So the model can predict what tokens a listener will perform. So here we have a video of Joe Biden telling a joke. Even though I'm not playing the audio, I can assure you the joke is very, very funny. And so it's entirely appropriate that the synthetic listener, Trevor Noah here, is able to laughs. Whereas the previous work actually that I just presented to you doesn't, the synthetic listener actually doesn't really know that it's a joke because it's just nodding and smiling, but it's not really paying attention to the semantics. So that's why this text-only model is actually even more powerful. And for some reason, the slide didn't animate. Let's try and go back, and there we go. You can actually run this thing just from input text. So just by typing in this text, the model generates a synthetic listener. was a nice message from Yvonne. And you can also use GPT to maybe generate synthetic dialogue. So here we have one agent pretending it's Conan talking to Trevor Noah, and Trevor listening, and now the symmetric story goes in reverse. So it's really cool to see that a text-only LLM can actually process enough information to generate a synthetic gesture. And it's sort of one of these results in a line of results, we'll see a little bit later in the talk as well, where a year ago I would have said, no, text-only LLMs, they're not grounded in any meaningful way for a computer vision person. But increasingly we're seeing that even text-only LLMs, perhaps with a little bit of fine-tuning or even in context learning, as we'll see in the last part of this talk, they actually know things about the world that I would have thought are visual. All right, I'm going to have to probably go through this pretty quickly, but another major area of excitement in vision and language are these neurosymbolic LLM-driven code generation stories. I'll present ours, but there's a flavor, there's a whole fleet of papers that are coming out on related topics using similar ideas, where we're taking an LLM to drive the planning part of essentially a visual routine or neuromodular network story to write a program that then gets executed to solve a computer vision task. And this is motivated by the fact that, at least in visual question answering, traditional architectures often struggle when it's a very complicated scene. Here's an easy case, here's a hard case, or at least somewhat harder, requires understanding the relationship between entities in the scene, and kind of the holistic view of a medium-sized neural net can't get that. Now we can debate whether you can just scale your way out of this problem. But there's always something where I'm going to argue modularity will help, or the ability to have compositionality will help. And you know, maybe eventually these things will also emerge themselves from enormous data. But for now, it's cool to have one LLM essentially driving other LLMs, chaining their performance, having one of them specify a plan. We used to call this a neuromodular layout, or even earlier years, we call it visual routines, that were the output of some planning module. But now we're just going to output code, here Python, LLM outputting a little program that uses visual grounding to get something done. So it's an actual piece of Python in this case. There's specific routines that we use, and each of the papers that have come out recently has a slightly different story. We have a captioner as one of our elements. We have something that can locate a referring expression or select from a set of images. And this is credit to Carl Vondrek for this slide and the next slide. His group did the ChatGPT work, excuse me, the Viper GPT work, which is also very similar to what we're presenting here in Code VQA. And you know, he points back to the neuromodular network paper, which came out of Berkeley back in 2015. And back then we were assuming a neural net, very primitive neural net, could be learned or trained from a parser to do program generation. And now we're just dropping in this, you know, huge LLM to do the code generation. And that's amazing to me that it works. And that's kind of what's transformative about the current revolution. There's at least like 4 papers of similar ideas that are out there right now. Carl's work on Viper GPT, I'm presenting the Code VQA, but you can also look at the other 2, including BizProg, which won the Best Paper Award at CVPR this year. And I think they're all getting similar levels of performance, and there's a lot of innovation that's still to come in this line. It's a very cool direction. Here's one of the limitations. Here's one of the cases where our model doesn't work. Question: a person who eats only bees is called, should be vegetarian. I was thinking malnourished when I first looked at this, but our code outputs what is on the plate, queries it, finds the strawberries apparently, and answers strawberryan, which I think is not a really correct answer. And last but not least, I want to quickly go through how LLMs are transforming vision and language models for image generation. Stable diffusion, of course, is a super cool model that's been, I don't think you can have more impact than that in the world in what it tried to do. But it's amazing how limited the state of the art is up until this kind of technique that I'm about to describe today. Even the production systems still would often just be very, very wrong in terms of the semantics of a prompt when an image was generated. Like if you ask Stable Diffusion for a gray cat and an orange dog on the grass, it might just give you an orange ball and forget about the orange dog. So attribute binding was a big problem. Spatial relationships were also a big problem in Stable Diffusion. Negation, not so much. Although I could argue they don't look like bananas, but you get the point. But again, attribute binding, especially with gender, like every model we've put this sentence into gets it wrong, always puts the man in blue, always puts the woman in red. So we want to debias that a little bit. Again, at least as of a week or two ago, this was true even of all the state-of-the-art models. So one solution to this, surprisingly, is just to chain together the two major paradigms of our day, Stable Diffusion and LLMs. And it turns out what's surprising about that, it sounds trivial, but it's counterintuitive because you wouldn't think that an LLM can spatially ground the world. At least I wouldn't have thought that a year ago. But it turns out that text-only LLMs, as I mentioned earlier, have a surprising ability to know things that I would have thought were actually spatial grounding. But obviously they're symbols that are isomorphic with concepts that are spatially grounded. Like the model knows that airplanes are in the sky and that grass is on the ground and things like that. So the LLM can really provide a scene graph or spatial layout just without ever seeing any pixels. Never trained on a pixel, never saw a pixel, there's no pixel in the query. And it can generate a template of a scene graph that can then be used for Stable Diffusion to actually get the job done in a more accurate way. So that's essentially the plan. There's some technical details about how you do that, make the Stable Diffusion method optimized for that. But it doesn't require fine-tuning or training any of your foundation models. And there's a specific plan for how you can prompt that to have the LLM output bounding boxes and so on and so forth. We weren't the first to do that, but we were one of the first to do it in this way. And you can modify Stable Diffusion, as we and others had also done separately, to have shape alignment or grounding alignment in the attention maps. And the final result, let me just skip ahead to some of the visualizations. Again, a gray cat and an orange dog. We actually get an orange dog. We get a man in red and a woman in blue. We get spatial layouts. We get 5 cats when we ask for 5 cats. We don't get bananas when we ask to not have bananas, and so on and so forth. And I'll skip over this. You can interactively chain these and edit. So you can say, please give me an apple to the left, and then make it a pear. See, I'm running out of time, so I will finish quickly. Swap the apple and the pear, remove the pear, and so on and so forth. Last, I'll just mention, most recently, we've extended this to video. I don't know what to be surprised by now. It turns out that text-only LLMs actually can do at least have a rudimentary notion of cartoon physics. You know, maybe with just a minimal amount of in-context prompting, they know that if I drop a ball, it'll bounce, and that there's certain kinds of panning and zooming in the world, and we can get much improved videos through dynamic scene layouts that we have introduced as an intermediate bottleneck or conditioning of video generation. So that's on archive. You can check it out if you're interested and see the kinds of things that a text-only LLM can generate in terms of video scene layouts. These kind of tubes that I would have thought were, you know, signs of of real semantic grounding. And so these are sort of pseudo semantically grounded because they obviously have never seen a pixel, but still the model can imagine them when prompted just a little bit. Okay, you can look for the archive on the below there, or the website for the previous work called LLM grounded text to diffusion models. That's what I wanted to cover today, in addition to a shout out to Susie's paper earlier on the token level correctness, which is still a poster in the back of the room. I'm happy to take questions on any of these and look forward to all the great work in vision and language that is coming out in the community. Thank you very much. I'm blinded up here, so someone will have to just start asking a question if you have one.
Hello, I have a question. Voice document seems to be the keywords of language into inventing or predict next word. I think that's not all about language itself. It's just a popular method we deal with modeling. But do you think there are other potential directions that can interact with language beyond just depending or predicting next word?
I'm sorry. I didn't quite. Are there uses of language other than predicting the next word? Was the question? Or?
Right, because that's one of the interpretations of the words of language and visual application. But I think that's not all things about language itself. It's just a very specific design methodology that we see here. But is there any other potential areas that?
I actually don't understand the question. Maybe somebody could repeat it. There are plenty of other. All I hear is are there other ways you could do it, and there are. But I'm sorry, I can't quite understand your question.
Things we can.
There are all sorts of visual question answering tasks or tasks about understanding the world. Is that? So I can't quite understand your question. Sorry.
Great, thank you. Do you think once we have large language models that can handle lots of languages, that then maybe they can help be more culturally sensitive in terms of what type of images or videos could be created based on sort of the intricacies of different languages?
I mean, can the models have more cultural sensitivity for video generation? Yeah. I'm sure it could. I think none of the work that I've presented really moves the needle on that, but I've certainly seen others working on low resource languages on the speech understanding side. And I saw Mohammed present in another workshop earlier today, work on trying to understand cultural significance across video and different data sets. So I think there'll be a lot of work that comes out on that front.
Thank you very much for the title. I have a question regarding the limitation information. I think all these papers are using reconstruction loss, right? Maybe. So do you think this is a main drawback or the cause of this limitation, especially for treatment binding and compositionality?
Yeah, but I don't have a better idea right now. So, I mean, I'd love to hear other people's ideas on that. I mean, I thought you might be going the other side, which is for generation. You know, the reconstruction loss often leads to poor performance, and so even in MAE and so surprisingly adversarial losses, which improve reconstruction quality, but don't actually improve the semantic power of the model. That's another possible direction to explore.
So I'm making a question about limitations. So does this approach change different modes of performance? Do you think there's any limitation to this approach? Do you think it's down the line, or it's going to keep getting better?
The visual prompting?
And in general, changing different modes of
I don't have a theory that says where the end is. And there's another great question that often gets asked of, should it just be a single monolithic model or should it be a modular model? And I also don't know that I naturally gravitate to working on modular architectures. I think the human brain appears to me to have modularity as reading as an amateur neuroscientist, the literature. But it's hard to say, if we just train a bigger and bigger model, maybe this modularity, it will just emerge from a homogeneous model. It's right now, I think we should try both approaches.
When you kind of split the steps, and do you think where do you get a little bit motivation from that, or do you think you will put like draw me like a chat and the orange dot, and you will write first draw me the layout of the chat and dot, and then kind of paint, and then do this? Do you think will it work or achieve the similar result?
Probably. And I think there are a lot of ways. There's also our work, I think, is concurrent with half dozen other people who are publishing similar ideas in the last 2 months. So I think there's a lot of ways to explore this. One thing that's not obvious future work at the end there is that model doesn't actually look at the models. Sorry, I was going to answer the question. So probably, I think those ideas are good.
Yes, thanks, Trevor. And also the co-organizer for the first and second DQA workshop at CDPR. And Jason's going to talk to us today about unified IO2, multimodal re-entry provision, language, audio, and action. Jason,
thanks. Yes, okay. Hi, I'm Jason. And today's talk is about the unified IO2, so multimodal re-entry for the vision, language, audio, and action. Okay, so a lot of people talking about large language model recently, and also they demonstrate really strong capabilities, right? So, like some of the last figures, this is from like the OpenAI's ChatGPT thing. Like if you ask anything, they can give you a really reasonable answers. And also from the right side, people have using these models, and also like a lot of people have shown that if you fine tuning using like something like Lava, and then like actually understanding the content of the image. So one of the really great part of this kind of model is that it's actually demonstrate it's kind of like zero shot by default, right? So the language it can actually give you any part of the image, and the GPT-4 they can show that they can really understanding the content of the document and also the figures here. So, and also a lot of people are talking about this, how can we from the large language model to this multimodal LLMs, right? So basically the idea is that we can either from the single source test in, test out, we can go into kind of like multiple one that including image, test, audio, maybe also actions, and also we can output all of them. So also this input, output image, test, audio actions. So usually has 3 different ways. So the first one is called coordination, and second is adaptation. Also, or we can also train from scratch, right? So in general, the first one, why is called coordination, that we can using the LM as a planner, so to coordinate different modules for multimodal tasks, and we can see like visual programming and a lot of other work, like same time work. They're actually using this to generating code and to understanding visual or robotic tasks. And also another thing is called adaptation. So basically we can align the multimodal features with LLM by fine-tuning a small set of parameters. And we can see the Flamingo and also Lava and Mini GPT-4, like those kind of work. Basically, they're using a pre-trained large model, and they plug in some also pre-trained vision backbones, also fine-tuning together on some element part. And also we can train this multimodal LLM from scratch. So this usually is naturally grounded across modalities. And there are some work called Cosmo, and maybe some like Gemini, and there's upcoming to show that we can generate like image and text together. So one of the core questions is that why we care about this massive multimodal, like giving these examples, here's a concept of Apple, and we can actually using different representations like visuals apples, or like a Wikipedia definition of apples, or audio of biting apples, or you can actually picking up and a video or like navigating to apples in this, in this kind of tasks. So, and that's basically simulating that people contact world with a massive array of sensors. And also there are really a lot of the benefit. So one is the robustness, right? So we can actually creating a redundancy such as the system functions even with lots of one components. And second is that it also gives us this self-supervision that the different sensors, they can educate each other. And also this might be the key to making a model as a future learner, right? So kind of like people has working a lot of this, like in the last few years. So on the encoder side, we've seen this perceiver IO, right, which is also the first work they are trying to using a unified architecture. They're trying to like encoding multiple modalities, and also this multi-MAEs mainly focus on the vision side, but also encoding the depths or like segmentations, and also image bind is more like a click-like network that they encoding a lot of different style of modalities input. And on the decoder side, so like we can see there's a pixel 2 sequence which using the tokens to representing bounding blocks. Or there's X decoder that is design a decoder that can join kind of some output semantics or text. Like this UVM trying to learn the code for different tasks like service normal depths, and also our previous work on Unify.io, which trying to really unifying this kind of things together and using us like a vision token, text tokens to representing all these kind of tasks. So this is great, right? So a lot of the problem is that we've seen this, all of these things are presenting like disjointly, right? So this is one of the motivations of why we are presenting this Unify 2.0, which is trying to create a network that has strong language capabilities, but also can understanding and generating all of these modalities. So like the model architecture is something like this. So we are taking this image and image history. This is set of image, like here we are using 4. All these like spectrogram and audio history spectrogram, and also text, right? So these are the modalities are coming into the model. And we are using some pre-trained component that are extracting features. And these features will presenting sequentially as the embeddings. And further, they are going through this transformer encoder and decoder system. And then like we will decoding them into different output, right? These are like, it has like text and actions and audio token output and also image output. So the audio output and image output can further decode it by a pre-trained model. So we can using a VQGAN or VIPVQGAN to decoding this modalities back, right? And this is actually a generator, right? So, and the text and action output, they can also output key point, bounding box, and other informations. And also the image, they can output gaps, binaries, like surface normal or output flow, like all of these dense signals. Yeah, so this is a little bit details about how the model encoding. So you can see basically we are using like basically different modalities, and we are converting them to the sequence length and all of them, and also we are kind of outputting the image like size and sequence length, right? So, and also if we are coming by this way, the encoder will roughly has like 1400, and decoder will have 1,000, maximum like 1,000 like token lengths, but these are going to be pretty long. So next, I'm going to talk about the pre-training objective. So this is a figure of the UL2. So it's also a language model only one. So they are kind of unifying like this, like denoising and generation into this R denoising, S denoising, right? So basically they have these different prefix tokens, and this different denoising are unified together. They show that, okay, somehow this is working very good on the NLP part. So in our case, because we want to extending to this multi-model, right? So we are proposing this hierarchical multi-modal span denoising. So which basically giving these examples, you can see like it's actually taken from a video. So here are some like captions or like a text associated with the video, and there are frames and associated like audio spectrogram, and also you have a history of them. So how we are resampling the examples we are going to train the model? First, we are going to select the target modalities. And second, we're going to select the input modalities, right? So here, like we are selecting, we want to generating or denoising the audio target, but also we are going to using the text, image, and audio history. So these are the information we're going to use. And then like we are going to generating this input mask. So this will basically control whether how much information of masking from the input, either you want to reconstruct or you want to like generate if you mask all of them. And also we will pair this kind of all of the earlier three with the previous tokens or with some instructions, right? Here we are using this audio R, means that it's going to generate an audio target, but also it's going to denoising. So it's a reconstruction. Okay, and then like we can converting this original input, basically it's from a like input clip to this kind of like target, like this input and target, right? So you have this all of these different informations, and your target is going to be reconstructing from the input of this other information, and also the mask version of it. And we are using this kind of like idea to generating to all different data. So including the image generation on these 3D things, basically you're having this two image from a different viewpoint, right? So, and you can actually masking one part and trying to using the other information to trying to reconstructing the original image. You can either all the tasks like I just mentioned about, like you can using the taking of any videos from the internet, and you can kind of like constructing this kind of data and to predicting the audio span. Or you can giving like the generating this like agents are giving actions, and you can simulating your data from the environment. Yeah, and this is also a traditional one like image test, like test only. All of these can fit in this kind of framework. Okay, so the second things I want to talk about is about this pre-training objective, right? So we're talking about how we are creating a data we want to train, but then like we always see people are talking about this IMAE versus autoregressive, which one is better? So so in general, we see that autoregressive is widely using on any of these GPT-like model, but IMAE actually shows better understanding. But what if we want to do both, right? We care about generation, we care about understanding. So the first one is that let's assume that image token, you can see like we are already converting the image into these A tokens. So, and this like token in the black are the mask one. So then like actually the green one that are going to the target are going to predict it. So for the auto you are shifting by one, right? So you are actually earning token and on the left, right? But there are problems is that it might have this information leak, right? So although even like we are, all of the token are conditional only on the previous token, so we can see if we're going to predicting this token 5, it's going to using the ground truth information of the token 1, 3, and 4. And this is actually going to kind of leaking informations and maybe ignoring information from the encoder side. Right, so on the IMAE, which is pretty good. So in general, like you don't have this leaking problem, and you are using your mask tokens or learn about some embeddings to querying the target, but also we verify that it has really bad generation result. So what if we want to both, right? So here we are, our solution is quite simple. So basically we are having this dynamic mask plus autoregressive model. So in this case, when we're predicting 5, it only like sees information of starting token and token 2, right? All of the other input tokens are masked. And in this case, it can actually either maintaining this autoregressive manner, but also not leaking any information from the decoder side. So to train these models, we are using a huge pre-training data set. So here we are having roughly like 500 million image text pairs, 1,000 billion tokens, like 80 million video clips, and 10 million 3D clips, and also 300 million interleaved image and text. So this is roughly the distribution of our training. So you can see that so it's hard to see, but basically what you can see that it actually contains the mixture of different modalities, and these are sampled based on like we are predefined some like ratio to train the models. And notably, this is super large, so it's roughly it is a 500 terabyte data, so which is 100 times larger than compared to NLP only like data sets, like available one, right? Not counting only on this the big company secret like recipe. And also by having this large data set, and we actually require a huge engineering effort to pre-train these models. So the first one is that we need a super efficient data pipeline that can easily mixing arbitrary of this multimodal data, right? So here we are using the sequence IO, extending it into this multimodal version of it. And also because you see we are presenting this subset, like randomly sampling these different modalities, right? So on the language model side, they're going to be packing anywhere, and it's going to be making the model extremely inefficient. So we are implementing this dynamic packing, which it reduces the padding of the unused modality tokens by combining different examples together. So this is similarly in the NLP part, but it's actually pretty tricky and for in terms of implementation, because it's actually involved in the middle of the models instead of the data part. And also we are doing this model parallel implementations that can scale the models. So which we are using the T5X library. So we are training 3 different models. So the first one is 1 billion, and also the second, the middle is 3 billion, and the largest one is 7 billion different models. And when training these models, this kind of like this 7 billion models like this massive data. So usually a problem is that we will see the loss, something like that. It will jumping everywhere, and then like the model is really not stable, right? So this is basically the curve we have tried a lot of times that we are using the pure NLP large language model training recipe. So then we really need to solving all of these. So I'm listing a few of them, but all of them we will releasing once we release the paper, because this is still a working project. So the first one is that when we are adding more like image and audios, because they are more dense signals, it's more likely to have numerical issues, right? So, and releasing like using the flow 32 attention logic is really useful. Well, in general, like you can using this flow 16 on language model only like model training. And also this QP-norm plus Z-loss, they actually stabilizing training and enabling large learning rate. And that's kind of the tricks that can really helping we train a better like this multimodal language models. And in our case, this F factor is actually being better, but maybe it's just because our setup is also based on our like system setup. But also we need carefully curate these mixture ratios that also consider the modality distributions and data quality and also the size. So we were releasing all of these recipes like once the first coming out. Okay, so after all of these tricks, right? So this is what you see after the pre-training loss, right? So, and you see the blue line is a 1 billion model, and 3 billion model, and 7 billion model. So in general, you see that those curves are going down naturally nice, and there's not like oscillations, or there's not even like not going down. But if you observing that there might be still some of this part that having a little bit spike are going up, right? So that's because some of the spikes happens. So we are updating our recipe, and also when we are retraining the model part, like from the earlier checkpoint, there are like some of this logging has like statistics has a little bit different. So that's how these escalations. But in general, we're observing that the model has been good on both in terms of the text loss, image loss, and audio loss, right? They are all going down pretty naturally. So after the pre-training, right, we want to do some probing, like to see, okay, how this model trained, right? Because we are spending a lot of money and a lot of time on working on this. So one of the things we want to testing is to probing how the model looks like. And here is an example of the text generation. So if you are giving this prefix like Beijing is a global city, and on this sentence, we are asking the model to kind of like basically generating the rest of it, right? So we can see the model giving our reasonable answers. Maybe there are some hallucinations, but it's actually reasonable and fluent. And then we're also evaluating on this benchmark, like on HelloSwag or Sequench, right? So HelloSwag is a pure NLP training data set. So we see the model is giving scores. It's definitely not comparable with NLP only models, but they are in general is reasonable. And also for the Sequench, we see that from the pre-trained models, like without any instant tuning, so our model actually comparable to this like this least recent like Lava Mini GPT-4 on this benchmark like result. And if we are going to ask the model who generating doing image generation, for example, an image of avocado chair, which is kind of old prompt that people are using to evaluating DALL-E models. So this is a generating, right? It's not exactly comparable to the latest Stable Diffusion models, but it's doing a good job here. And also you can ask models who generating an image of elephant swimming underwater or something fantasy, right? So although the quality may be a little bit worse, but we see the semantics is correct. So it can also do this audio generation. For example, we can ask models to like say a video of the man saying the workshop is closing the loop of the between vision language. So this is man saying a workshop on closing the loop between vision and language. Yeah, so you can basically hear that man saying a workshop on closing the loop between vision and language. Yeah, so this is basically the model basically learns to text-to-speech translation because the YouTube videos has a lot of this kind of data, right? If you change the man to a woman, so then this is what the model sample. Woman saying a workshop on closing the loop between vision and language. Woman saying a workshop on closing the loop between vision and language. Yeah, so basically the model is kind of like learning the different kind of tones and intonations, and also understanding the kind of, if I say a man or a woman, it will go generating different voice, right? So matching the descriptions. Right, so this is also another visualizations. Like if I'm going to do this, it's called multiple view denoising, right? So basically giving this mask input, giving this reference image and target, right? The reference image is actually from a different camera viewpoint, right? So like given the this is the ground truth, and we can see that our models can actually sample by implementing the missing of the input quite nicely, right? So this is more like required this 3D understanding of the model. And also we can see this like embodiment thing, right? So basically say giving this initial image, right? We can just say, what if you're moving forward, rotating left, move forward, rotate right? So this is how the model generating the thing that it's going to look, right? So basically it's hallucinating a house that condition on the instructions to give. So which basically shows the kind of embodiment thing. After this base model we trained, so the next part is we want to do instruction fine tuning. So this is really a lot of the existing models they are trying to do. So we are gathering a huge data set, but the two questions we are going to ask is that first is how do we go beyond the benchmark tasks, right? And the second one is that how can we generalize to new tasks, right? So this is actually the two questions we are really caring when we are trying to building this instruction fine tuning data set. So how to do that is that we are gathering a lot of this existing instruction following data set, right? This including like instruct pixels that you can actually converting the basic image basic context. Also, there are a lot of this recently like fine tuning this single LLM to multiple LLM. Like one of them is order, right? So basically that it contains like image, videos, and output text. And also we will also using the SLAM-based only model, which is used on the language fine-tuning. And we're also creating a lot of test variants and combinations, right? So giving this like vanilla object detections, and we can actually by changing the output format, right, from this x1, y1, x2, y2 to the x1, x2, y1, y2. Or also we can say, what if you can detect all objects within multiple instances or detect the fastest object? All of this kind of variance. So then like we can creating a huge set, which is over like 200 data sets together. And this is a barcode of listing the distribution mixture. And all of this data set contains like the instruction tuned version of the existing models that contains like natural language, vision language, video language, detection, key point, and audio and language, also action 3D, and also instruction tuning data set from others, right? This is a mixture, but these are not the final version, so it's still ongoing work. And I'm going to share some like the preliminary result. So for example, in this one, if you input an image and you can describe the image briefly, let's say an old wooden jetty beside the lake of the trees surrounding on it. And you can also ask the model to provide a detailed descriptions. And then like if you give you a really long version of that, which is a lot of this multimodal fine-tuning LLM showing this. And then like I can actually ask the model to remove the dock, right? Or you can actually ask model to imagine you like basically painting a different style, or changing the render of sunset, or adding an aurora, right? This is how the model actually generating the kind of output. And we can do more, right? So I can say, make the image that displays orientations. This is a surface normal. And this is the model's output of this image. And also I can say, what is depth of the image, right? This model predicting some depth map. And what if I say, I want to locate the top half of the bridge, right? So the model give you a bounding box, but it focuses on the top half because here is because of the orientation we have. And also we can also ask model to second bridge. This is going to be the binary mask, the model, right? So you can actually asking the model to generating music of the scene, right? So giving this image, and this is what the models like generating. So it's not really meaningful, but basically it's kind of a relaxing part of music. Okay. But also you can like editing this model to make it haunted, and then you can actually asking it again. So then like this is how it business. Yeah. So it's pretty creepy, right? So like kind of matching the semantics. We are trying to doing some probing here. And also we can also asking different questions based on different image. And also the model can doing this robotic work, right? So because this is also in our instrument tuning data, right? So you can actually asking, this is like liquid, and this is a DEX, and this one is like taller than this part. And like, what if you put on less color, like liquid and the DEX, right? So the model can actually picking the right one and to the correct target. And this is one of the failure case we see, but also this is only the very initial version of it, of doing the instrument tuning. So hopefully these things can be resolved better. Okay, so this is basically what I want to talk. And so all of this is definitely not doing by myself. So I have three, like we have this Chris and Sanho and Charles. They are kind of a really core contribution of this work, and also others people who are really advising and helping on this project. Yeah, and also okay, and then like we are going to. I would like to acknowledge the kind of the GPUs, this Google TRC program, and also this JAX and T5X. This is basically where we are building the model, and also we are going to open sourcing all of this code model data and recipes. Once we have done all these things, so probably maybe in next month, hopefully. Yeah, that's it. Thank you.
We can talk. We have one for questions. So the model will be treated. The issue is that cookies information that learn association. After this work,
yeah, so I think this association is really what we hope the model will learn, right? So we assume that if we train them together, right, if the model share a lot of parameters, it might be learning that. But I think this really require a lot of testing or evaluation, right, to see if we're having only language-based models, or if we're having this training from scratch, what will be the difference, right? There might be some visualizations, there might be a lot of testing cases showing that, but currently, to be frank, I don't know that. So one of the things of this work, I think why it's meaningful is that it's really enable that the model can do this kind of job, right? Earlier, we are not really thinking about a model can do all of these different tasks only in a unified way, right? So we don't have a really shared decoder, and all of the text token, audio token, image token, they're only embedded, right? There's no specific decoder like stable diffusion, audio diffusion to plug in to kind of function. So I think this required a bit long time to answer after reviewing more. Yeah.
Another question.
Thank you very much. My question is regarding startup shop that you incorporate into my system. Does this support the semantic information that you can apply the style to one portion of the image?
So you mean the different style or like
Yes. For example, the site has to apply the style to the bridge without applying to the C. Do you support that? Yes or no?
Sorry, can you repeat the question? So you mean
the style you apply image supposed semantic information, whereby just decide to apply the style for one particular portion, not the whole thing.
Yeah. No, I mean the model, you just basically your input is just image, and the prompt you want to change the model, right? And then the output will be the edit version of the image. Right. The reason why the model can do that, the one is learning these visual informations during pre-training. Well, the most importantly is that we are using this instructional pixel dataset, which containing this kind of modification, and the model can quickly adapt into this kind of task. So you really don't need to specify the locations. You just need to providing the prompt of editing what you want to edit.
Especially with the panoramic where we have different borders. So we may decide, for example, just to apply the style, the wall will not apply the style. So maybe you may think about the panoramic image. Since it is the 3D image, you can apply the style. So you need to have a full where just apply the style in the particular function. I think it will be also interesting. So maybe I would wish to see your email because I failed to take the details.
Okay, yeah, definitely can talk offline. Yeah, if you want. Yeah.
Any more question?
No, it's also taking language and audio.
Yeah, but I think they're only taking audio processing, the image is not video.
Also video, right? For the video, we are taking a chunk of image, right? Here it can be 4 or 8, but it's definitely not a dense video. It's only sparse. You sample a few frames. Yeah.
So it's not long video.
It's not long video. It's only like 10 seconds.
Yeah. So if you want to extend it to a little bit long video, more than 5 seconds, does it need
Yeah, I mean, because we are training things more from scratch, right? So long video means long sequence length, and here we are already pretty long, and so I think that's going to be really challenging to train this model. So here we are really say we are considered start image, but maybe if you have a better encoder that can encoding videos into shorter sequence length, maybe you can also like function that. Yeah.
This sentence again. Okay, our next speaker is Sharan Saul. Sharan is an assistant professor at Stanford University, leading the robotics and embodied AI team. Before that, Sharan was an assistant professor at Columbia University. Sharan research focuses on computer vision and robotics, and in developing algorithms that enable intelligent systems to learn from their interactions with the physical world. So Sharan's talk is going to be about closing the loop between speech and action. So she recorded the video for us, but she's going to be also available for questions.
Hello, everyone. Thank you for the introduction. And sorry that I cannot be there in person, but I hope that everybody has been enjoying the workshop so far and also enjoying Paris. So I'm Sharan. I work in robotics and computer vision. So in today's talk, instead of just talking about bridging vision and language, I also want to add robot action into the mix. So to me, I think the most interesting question I like to think about nowadays is actually how to ground those very powerful large language models or vision language models into the physical world so that they can be more useful to our robotic systems. So I kind of want to start my talk with this concept of language as cognitive tools for reasoning. So long before the existence of large language models, there already has a lot of hypotheses or theory in cognitive development that kind of hypothesize that although language are initially learned through and for communication, it later internalized and used as a cognitive tools for us to organize our thoughts and perform reasonings and planning. Right? So in other words, the usage of language has become an important part of our ability to perform reasoning and planning. And then recently, I think the development of large language model really gave us a very convenient and easy way to validate that hypothesis. And we have seen many works in robotics that's kind of capitalizing on this idea. And here are just a few examples of that. And I think the most impressive part about all these works that use large language model as part of the planning system is that how flexible those robotic systems are, in particular handling new tasks. And we can see a large variety of applications, either in manipulation or navigation. And then the new task, the system is able to handle as long as they can be described by a combination of some object names and that can be detected by the object detector and some action that come from a predefined action library. So as you can see, this kind of object detector and action library has really become the link that kind of connects the structured language world that performing high level reasoning and also the low level unstructured physical world. But however, at the same time, this object detector and predefined action library also become the bottleneck for a lot of those robotic systems. So for example, if your object detector is not expressive enough to describe all the possible object states, then the robot agent may be very likely to lose some critical information to support their reasoning. For example, whether an egg is bricked or not, which will definitely change the planning, but maybe not able to be fully detected or described by an open vocabulary object detector. And similarly, if the agent, I think the robot agents today still have a lot of difficulties in acquiring skills, like manipulation skills, that is, if they are not already part of the existing library. So as a vision and robotics researcher, I'm actually quite happy about this observation, because that means that the problem of perception and low-level manipulation skills is still an open problem that still need to be worked on. So in today's talk, I want to talk about two of our recent attempts or projects that try to address these bottlenecks, which will cover both aspects of grounding, one from the perception aspect, the other is on the low-level robot actions. So first, we're going to talk about perception, where the goal is trying to describe what is going on in the physical world in order to, in a structured format, so that we can use large language models to support reasonings and planning. And in particular, we're going to study this question in the context of robot failure reasoning. So first, why we care about failure reasoning? I think with the increasing demands of us asking robots to do more and more complex tasks, I think we kind of have to admit that failures are just oftentimes inevitable, like our robot fails all the time. And also at the same time, identifying the cause of failure can be really tedious and oftentimes involve reading hours and hours of robot log data in order to identify when and where the failure happened. And I think today's self-driving car system are actually very good examples for this challenge, right? So although every day there's hundreds of cars driving on the road, but in the end of the day, we still need some humans sitting in front of the computer, reading through all these logs in order to identify and categorize the failures so that they can send it to the corresponding engineering teams to fix it. So the question we want to ask here in this project is that, can we develop the algorithm that's able to automatically detect and also explain the robot failures in natural language, which means that given the robot log data, which include both the videos and also their state information, the algorithm need to infer the cause of failure and also localize when the failure happens in terms of the time. So that is a task. So if we want to perform failure reasoning, and I think the natural question to ask is, what are the capabilities or like skills the system need to have in order to reason about failures? Right. So here are just a few basic requirements. Right. So for example, the agent need to be able to summarize what happened from their raw sensory data and identify what went wrong, and finally be having the ability to plan what to do in order to correct the failures and complete the task eventually. And if you look at all these three requirements or capabilities that we need, we can immediately see that for the later two capabilities, LLM or large language model is able to immediately help because they can leverage their common sense reasoning capabilities by as long as the information is summarized in text. So as we can see, the biggest challenge now is really lies in the first step, basically how to generate an informative robust summary from their raw sensory input so that the LLMs can reason about. So that is also the focus for this project. So then another question that we can ask is what make a good robust summaries from the raw sensory data? Right, so in this paper, we actually identified two very important properties. So first is that we noticed that the summary better to be hierarchical, means that it should have a different level of abstraction in order to support different level of reasonings. Right, so for example, on the highest level of the summary, this kind of summary should be able to support general failure categorization, like basically tell the system that whether the failure is come from low-level execution failure or high-level planning error. Whereas the low-level summary should provide detailed information about how this failure happened, and also provide information to help to localize the exact time and location of the failure event. So all of those detailed informations are very useful for error correction, but maybe not very useful for the high-level reasoning about just identifying or quickly localize the type of failures. And the second important property we notice that is important for an informative summary is that it should be able to leverage all the possible sensory data. In other words, it should be multisensory. So it is because certain type of failures or object states are just oftentimes much easier to be identified through some type of sensory data than others. And so for example, it is just much easier to tell whether the water is running through the sound instead of just looking from the image. So based on these two observations, our paper basically proposed a hierarchical multisensory robust summary for failure reasoning. So that is the core of our approach. So on the lowest level, on the base level, we basically want to summarize those unstructured raw sensory data and also multisensory data into a detailed text description. So on this level, we want to cover as many details information as possible. So specifically, giving an RGBD image or video observation, we first try to detect those task-relevant objects in this image by using open vocabulary object detectors, and then infer a corresponding object state using a visual language model like CLIP. And then we'll extract the object spatial relationships by using the 3D information encoded in depth. Right? All this information actually is stored originally as the 3D scene graph, which can be easily converted back and forth into text summaries. And then similarly, we'll also try to summarize the soundtrack using audio language models such as audio clip. And that summary is also part of the text summaries at the lowest level. And then in the second level of the summary, we will try to condense the information by selecting the keyframes from the video, where the keyframes can be detected by either changes in the visual scene graph, audio event, or a robot event, like for example, when the robot finishing or think it finishing a subtask. And then finally, in the highest level of the summary, we'll try to summarize the robot experience based on the robot's original plan, where each of the subtasks in the robot's original plan is summarized by their original goal and also the final observation in the end of this subtask. So as you can tell that in this level, the highest level of summary or abstraction, there will be information that got lost. However, this high-level summary is very helpful for the reasoning modules to quickly narrow down the failure steps and type. So with this robust summary, we then proposed a progressive failure explanation module that helps the system to systematically curate LLMs in order to generate a good failure explanation and also localize the failure steps. So first, the system will try to iteratively ask the LLMs to verify whether each of the robust sub-goal is achieved. And for this step, the system basically will use the sub-goal level summary. And then if any of the sub-goal is not satisfied, for example, the subtask is not complete based on the reasoning on the text, then it's very likely the failure is caused by an execution failure. So then the algorithm will actually go down one level to the event-based summary and use that to explain the failure. Right, so for example, here in this particular example, the robot failed to complete the task because it dropped the knife, and that is actually an execution failure, and is able to identify that through a text summary. And in some cases, it's possible that all the subtasks actually is successful, verified by the large language model. However, the final task is not complete. And in those cases, the failure is more likely to caused by planning error. For example, the planner is just missing a critical step, or the original plan has a wrong order of steps. Right, so in this case, the final state and the robot's original plan is used to provide failure explanation. And then finally, with the failure explanation, we can further prompt the LLM to generate a plan to correct the robot's error. And to ensure that the generated plan is executable, we're actually using something very similar to most of the language-based planners, that basically mapping the actions that are generated by LLM to the closest executable actions in the task environment using a sentence embedding model. And then to systematically evaluate our approach, we actually create a new data set called robot file, which contains a large variety of failure scenarios and see whether the system is able to correctly identify, localize, and correct those errors. So here is just a quick visualization of the data that we have in the data set. You can see that this data set actually contains two parts. One is a real world environment execution, and the other is simulation, and I think these two types of data help us to validate or evaluate different part of the algorithm. Right? So for example, the simulation environment is very helpful for evaluating the replanning accuracy, while the real world examples is very helpful for us to validate whether the perception algorithm is actually useful in the real world, or how robust it is against those real world noise. So here is a specific examples in the data set. So in this example, actually we are showing two videos that when the robot is doing the same task, which is trying to salted a carrot slice. However, this robot actually failed this task from with two different failure types. In the first example, in the first video, the robot failed to do this task because it's pick up a spoon instead of a knife. And in the second example, the robot failed this task because it dropped the knife in the middle. And then in the bottom, you're actually looking at the output of our framework that detects and also localizes the time of failure events. So before I move on, I also want to talk a little bit about the limitations about our current system and also some ideas of future work to extend this project. So first, I think the performance of failure detection or reasoning, I would say that's still kind of largely bottlenecked by the perception module accuracy. Right? So earlier I said that if your object detector or vision language model is not expressive enough to detect object state, then the system will still fail. And I think still today we are bottlenecked by the performance of that part. And then also I think the as an extension or future work direction that we can think about is that this kind of hierarchical summary from the robot log data actually can be very useful for many more other tasks instead of just doing failure reasoning analysis. Right? So for example, we can use it to analyze the robot's behavior or their efficiency, and also can be used as a way to collaborating with humans. And finally, I think a limitation or something that I really hope to expand further is the data set. We collect a robot file data set that contains quite a bit of failure types, but it still only covers a very limited percentage of all the possible failure scenarios that robot can encounter. And I really hope to see that in the future, there will be more work that's contribute to this data set. Basically, we need to share failure examples or failure videos of robots more often than just the successful cases. So that is the project or the examples of how we can ground large language models into the perception world as summarizing robots' experience into text in order to help them to reason about failures or reason about what went wrong. And in the next project, we're going to talk about how we can ground those language models into low-level manipulation skills. And here, in particular, when I say low-level manipulation skills, I mean those 6-stop closed-loop behaviors with very high rate control, which has been known to be a big challenge for language-based robotic systems today. So the project I'm going to talk about, the title is called Scaling Up and Distill Down, Language-Guided Robot Skill Acquisition. So as suggested by the title, there is 2 parts to the algorithm, right? So on the one part, the first part, we're trying to scale up the data generation or collection by using large language models and a simulation environment. And on the other hand, or the second part, we're trying to distill down all those robot experience that's generated by LLMs into a lightweight visual motor policies that can be directly deployed in the real world. So on the scaling up part, given any task description, right? So for example, here in this case is sending a package for return. We will first use large language models to recursively break down the task in order to generate a detailed plan. So this step is actually very similar to most of the existing works that use large language model as a robot planner. But an important difference here is that we are also allowed the large language models to call those sampling-based utility functions in order to perform the low-level execution and complete the task. Right? So for example, we allow the large language model to call motion planning, grasp planning algorithms, or placement sampling algorithms in order to try out different approaches in order to complete the task. So as a result, this kind of sampling-based method or the low-level execution really provides introduced kind of randomness for exploration in the low-level manipulation strategy. And at the same time, the task decomposition provided by the LLMs can also help us to narrow down the search space drastically and therefore makes exploration a lot more efficient. So for example, the system will sample different grasps around the object of interest, but because it's already like break down the task, it don't need to sample all the possible actions in the space. And also, I think more importantly, at the same time, we also use the large language models to generate a reward function, or in other words, a verification function that helps to verify each of the subtasks by using the simulation state. Right? So for example, if a subtask is not successful, like for example, if the robot is not able to successfully grasp the handle, then the algorithm will actually retry at that level without popping up to the higher level. So this verify, what we call verify and retry module, is actually very important because it's not only help us to increase the data collection success rate, but also crucially provides those robust recovery behaviors or failure recovery behaviors that is critical for the downstream policy learning. Right? So we actually store all this information into the data set so that the system actually learned about how they can correct its own error from this data set. So through this process, by the end of this scaling up stage, what we will get is a very large multi-task language labeled robot data set. However, as you can tell, this data generation process actually requires access to the simulation state, and which is of course not accessible in the real world. So what we're going to do in the next is to distill down all this robot experience into a language conditioned visual motor policy. So in this step, we'll train a policy that only the policy will only take in the language and visual observation as input and directly infer the action. So this step is actually very critical because it can potentially address several of those common limitations of existing LLM-based robotic systems. Right, so first, it allows us the end policy to directly infer actions from raw sensor input instead of rely on some external object detectors or state estimators. And second is that it also allows the agents to continuously improve its performance or skill with more and more experience without the need of actually fine-tuning the LLM itself, which is oftentimes rather expensive and not very practical. So in the end, we evaluate or validate this message with in many different applications and domains, where all of this tasks actually requires 6 stuff close loop planning, and many of them requires long horizon planning. Some of them requires common sense knowledge, also the ability to use tools and also understand intuitive physics. And we found that in our experiments, the distilled policy is oftentimes able to drastically outperform the direct LLM-based policies by quite a large margin. And I think that is actually inherently enabled by the robust retry behaviors that's presented in the training data, and also this distilled process is able to maintain this kind of robustness in the training data. So to summarize, in this very short talk, I actually talked about 2 of our recent work that both of them has this goal of trying to ground those large language models into the physical world, one through perception, the other through low-level actions. And if you look at these 2 projects side by side, we can realize the importance of a hierarchical representation. Right? So in the first case, we're actually doing kind of a bottom-up summarization. We're trying to summarize those sensory inputs from very detailed summarization to high-level abstract summarization, where different level of abstraction really allows the agents to reason about different type of failures, either it's execution failure or high-level planning failure. And in the second case, we're actually also using hierarchy, but it's rather top-down decomposition that's in order to enable the efficient exploration by kind of decompose a high-level task into subtasks, and then doing this kind of verification and retry at each subtask level in order to efficiently explore the space and collect useful robot training data. And I really think this idea of this general idea of using a hierarchical representation can be a very practical way to help us to ground those very structured language model into our continuous and unstructured physical world, and therefore making it a lot more useful for our robotic systems. So that is the end of my talk, and I'm happy to take questions from.
Can you hear Sean?
Yes, I can hear it now, but I cannot hear 1 minute before.
Yeah, so I have a question about the failure mode detection.
Mm-hmm.
So I guess what happens in cases multiple instances of failure rather than a unique failure mode? What happens in this case?
Yeah, so actually, the system is able to handle multiple failures in the execution, but it also depends on like how correlated or like whether there's dependencies in the failures. So, for example, if you have multiple execution failure, because the failure reasoning step is basically just progressively going through step by step and verify each of the steps whether it's correct. So they can easily detect whether there are multiple execution failures. However, if you have multiple, for example, planning error, then it will maybe have a little bit trouble because sometimes it's missing some steps, sometimes the order is wrong, maybe it's both of them. And I think at that time, the large language model will may have a little bit trouble or struggle to identify what is the root failure. Maybe they're able to identify one of them, but not the other. So it really depends on the type of the failure, whether sometimes it's able to identify like multiple failures, sometimes it may have trouble doing that.
Any other questions? Okay, this is actually over there. So our next speaker is Yue Fan. So Yue is a second-year PhD student in the computer science department at University of California, Santa Cruz. So Yue earned his bachelor degree in automation from Shandong University, followed by a master's degree in robotics from Johns Hopkins. Your research interests lie in the fields of embodied AI, computer vision, and NLP. And Ira is going to present the aerial vision and dialogue navigation challenge. So Ira is available in Zoom.
Yes, thank you. Hello, everyone. Good afternoon. My name is Yue Fan. I'm a third-year PhD student from University of California, Santa Cruz. It's a pleasure to have you all with us today for the CLVL workshop. And over the next 30 minutes, I'm going to guide you through our new AVDN challenge, which stands for Aerial Vision and Dialogue Navigation Challenge. This challenge is built upon the AVDN dataset, which is done by me and my coworkers in the ERIC lab of UC Santa Cruz, directed by Professor Xin Eric Wang. So let's get started. The structure of this section will be as follows. First, we'll introduce the AVDN dataset, and then we'll do an overview for the AVDN challenge. Next, we will announce the winner and show a winner talk. Then last but not least, we'll have a live QA session. Okay, first we're going to introduce our aerial vision and dialogue navigation dataset. First, the motivation of our aerial vision and dialogue navigation dataset is that we want to push the boundary of embodied AI from indoor to outdoor and from ground to aerial robot. Aerial robot, as also known as drones, are popular, but also hard to control. The controllers requires both hands and requires full attention of the pilot. So it will be great if we can build a hands-free drone control experience where people can control drones with only language. Here's an example. A person with his hands occupied or with some disabilities can control the drone with only his language. Here he said, "Drone, please fly to the yellow building to the north." However, we also want to mention that we pick dialogue as the form of language to control the drone because dialogues provides opportunities to resolve ambiguities in communication. Aerial navigation involves broad views, like the drone fly above the ground will have the chance to observe a larger area than the robot that run on the ground. So in the example here, the drone could wonder which yellow building the user was referring to. It's natural that the drone probably want to ask questions to resolve this confusion. So inspired by the vision and dialogue navigation work, which was done by Professor Thomason, we decide to build a vision and dialogue navigation dataset for aerial robots specifically. Okay, next, I'm going to do an overview for our AVDN dataset. So AVDN dataset includes the collaboration between the commander and follower. The goal of the collaboration is to let the follower reach the destination instructed by the commander. The commander, which are the users, will provide instructions, and the followers, which are drones, will follow the instruction and ask questions. We also present a drone simulator where the simulated drone within the simulator has a top-down view. It's shown as in this picture. The visual information in the simulator is based on satellite images, which provides a photorealistic visual scene. And we crop the satellite images to simulate the top-down drone view. the simulator also provides a continuous action space. The drone can continuously move within the simulator. On the right hand side, there's a AVDN dataset example. So initially, the user provides an initial instruction to the drone, and then the drone starts navigation. At some point in the middle of the navigation trajectory, the drone stops because of some difficulty, and the drone raises a question to seek help. The user, in return, will resolve the question and provides further instructions. So then the drone could continue the navigation. And finally, it reaches some point where the drone predicts a stop action and asks the user for confirmation if the drone really reaches the right destination that user wants. And in this example here, the user confirmed that the drone reaches the destination successfully. So our data set, AVDN data set, includes 3,064 sets of these three components. First is free-form human-human dialogues, where the dialogues averages 2 turns. And then the second component is drone navigation trajectories, which is averaged to be 150 meters. Then the third component is the drone's visual observation with human attention annotations. So the observation are a sequence of images captured by the drone. They are like top-down drone view, and the human attention are the mask overlay on top of the observations. The human attention mask was annotated by the annotators manually during the data collection process. In our paper, we demonstrate that this human attention data can be a useful auxiliary supervision for model training. Moving on, let's talk about the statistics of our AVDN dataset. Our AVDN dataset is split into 4 splits: train, scene validation, on-scene validation, and on-scene test sets. The scene and on-scene sets are separated by us making sure the visual scene used in the sets are not overlapped. So that means the satellite images used for scene and on-scene datasets are completely different areas. The statistics for each data split are shown on the left. Let's take the training set as an example. There are 2,221 dialogues, and each dialogue has 19 words. And there are 350 areas. And the destination in the training set are on average to 126 meters in dimension. There are 4,591 subpaths, meaning that there are also 4,591 conversation turns. So that makes 2 turns per dialogue, as we mentioned earlier. The subpath length means the length of the navigation trajectory corresponding to the subpaths are on average 145 meters. On the right, we show the frequent words and the path length distribution. So we see that the most popular words are, for example, destination, go, building, think. These words that are usually covered during the communication between the follower and the commander. The path lengths are centered at around 200 meters, and there are some shorter ones and some very, very long trajectories. Next, I'd like to show 2 demos of our AVDN. The first demo is AVDN in real world, where the follower and commander are both played by human human players, but the follower is a real human controlling a real drone. Where in the second demo, human follower is using our simulator and control the simulated drone. Here, the follower on the left is controlling the real drone, and the commander on the right has the destination in mind. The commander first gives a command, and the followers control the drone, trying to find the destination. Here, the follower stops but has a question. And the commander answers the question. The follower resumes the navigation. It resumes the control. Now, according to the dialogue history, the follower finds the correct destination. Next is a demo of our AVDN simulator. It's the same data shown in our data set. So the follower is using the simulated drone, which has a top-down view, and the view is simulated by satellite images. And the follower is still asking clarification questions, and after some conversations, the follower successfully reaches the destination. With these two demos, we hope to show that our simulator enables a very similar AVDN experience as in the real world. Let's get into the second part, which is the AVDN challenge. Our AVDN challenge is built upon the ANDH task, which stands for Aerial Navigation from Dialogue History task. The goal of this task is to let the agent or model under task to predict aerial navigation actions that leads to the goal areas following the instructions in the input dialogue history. So here, the dialogue history will be an input for the model. The model will predict actions which controls the simulated drone in the simulator. The simulator will return the visual observation of the simulated drone back to the model. The model will continue the interaction with the simulator until the model predicts a stop action. The inputs is shown as here, which is first a history dialogue, second, the visual observation sequence, which corresponds to the interactions between the model and the simulator. Each visual observation corresponds to a directions of the simulated drone. So the output will be a sequence of actions where the action could be either a move action or a stop action. Next, let me introduce the evaluation. First, we show two examples. The left figure shows a field trajectory where the final follower's view area is not overlapped with the destination area. That means the model under test could not predict the actions that leads the simulated drone to the final destination. Where on the right side figure, it shows a successful trajectory where the final follower's view area is overlapped with the destination area. We determine the success based on the IOU between these two areas. The metrics we use are here, these three. First is the goal progress, which evaluates the distance of the progress made towards the destination area. It is computed as the Euclidean distance of the trajectory deducted by the remaining distance from the center of the predicted final view area to the goal area, to the center of the goal area. So the closer the final followers view area to the destination area, the higher the goal progress is. The second metric is the success rate, which is the number of the predicted trajectory being regarded as successful over the number of trajectories being predicted. The third is the success weighted by inverse path length, which measures the success rate weighted by the total length of the navigation trajectory. So the longer the trajectory is, the heavier weight it is weighted. Now let's announce the winner. By August 15, the top one leader on our leaderboard is the team Susan Ping. The team members are Yifei Su, Dong'an, Yuan Xu, Kehan Chen, Yan Huang. They are from Institute of Automation, Chinese Academy of Science, and School of Artificial Intelligence, UCAS. Their report is publicly available. You can access it by scan this QR code. Next, we will have them to present their methods.
Hi, everyone. My name is Yifei, a master student from Institute of Automation, Chinese Academy of Science. I'm glad to share our method for the Aerial Vision and Dialogue Navigation Challenge hosted in this workshop. Target grounded graph-aware transformer for aerial vision and dialogue navigation. This is a joint work with Andong, Xu Yuan, and Chen Kehan. The Aerial Vision and Dialogue Navigation task, AVD for short, aims to train drone agents that can comprehend natural language dialogue and navigate in a real-world aerial environment, as illustrated in the figure below. The key aspects of this task include understand natural dialogue, associate dialogue history with bird-eye view observations, and make sequential actions towards the goal area. There are three primary challenges in this competition. The first lies in the cross-modal alignment between long dialogues and satellite bird-eye view images, which is more difficult compared to common text image alignment. The second is the presence of large continuous action space, which makes robust action planning and state tracking more challenging. The third is the scarcity of data, which will lead to overfitting problem and the reduction in models' generalization ability. Our model mainly has three modules. At the beginning of each decision loop, the data augmenter first synthesizes new observation images and the dialogue instructions. After that, the embeddings of the three modalities inputs are acquired via unimodal encoders. Subsequently, three types of embeddings are simultaneously fed into the graph-aware transformer to predict the next action. Meanwhile, the auxiliary visual grounding task applied for model training. The details will be shown below. The data augmenter simultaneously augments the dialogues and observation images. To be specific, we utilize the large language model, Vicuna, to rewrite instructions while preserving their details and the semantics, as illustrated in the left figure. Additionally, we employ the augmentations library for common image data augmentations, such as random noise, image blur, contrast enhancement, and more, as shown in the right figure below. The graph-aware transformer, GAT for short, replaces the traditional self-attention with a graphic attention mechanism. Concretely, besides the standard query key attention, GAT introduces an extra pairwise distance score, as shown in the figure below. Each element EIJ in this matrix represents a nonlinear projection of the Euclidean distance between node I and j. Through this module, our model can better capture the spatial information among the history nodes. Auxiliary cross-modal alignment task predicts referred goal area in the image according to the dialogue instructions, thereby enhancing the model's ability to perceive the landmarks in the environment. Concretely, a fully connected neural network is employed to predict bounding box and confidence scores for the goal area. And we utilize the smooth L1 loss and GLU loss to supervise the training process. We validated the effectiveness of our model on the official ANDH task. According to the experimental results, our model outperformed the current baseline model, HAA transformer, with a 2.2 improvement in the SPL metric, a 3.0 improvement in SR, and a 3.7 gains in the goal process metric. We also conducted extensive ablation experiments to understand our model. The first question was whether the data augmentation is useful. We compared our model with a baseline without data augmentation and a model that underwent only image augmentation. The experimental results demonstrated that both image and the instructions data augmentation were effective, with the diversity of instructions playing a more crucial role. The second question is concerned of the effectiveness of graph wire attention mechanism. We compared our model with one using a standard attention mechanism. The experimental results shows that the GET module achieves a higher goal process metric and performed better across all metrics. The final question revolved around the effectiveness of the multimodal alignment auxiliary task. We compared our model with a baseline with only human attention aided task for supervising. The experimental results demonstrated that the cross-modal auxiliary task significantly improved SPL metric. We introduced a target-grounded graph wire transformer model to address the aerial vision dialogue navigation task. We utilize a hybrid data augmenter to alleviate the issue of data scarcity. And we employed a graph wire attention mechanism to better model the spatial relations within the historical information. And we introduced a cross-modal alignment task to enhance the navigation performance. Finally, we achieved SOTA performances on the ANDH task. Thanks for your attention.
Thank you. Congratulations again. Now is the QA session.
Yeah, thank you. And any question? Happy to take any questions.
Thank you, Yuval, for presenting the channel. Any questions for you, Yuval? I have a question. So do you have the data available as well as the evaluation benchmarks?
Sorry, could you say that again? The data and?
The data and the evaluation benchmarks. Do you have those available, open source?
Yes, you can access it by scanning the QR code, the leaderboard, homepage, and the dataset webpage.
Any other questions? Right, please, thank you again. So this concludes our session. So we'll have now a poster session and a coffee break, and we're going to resume at 4:15. Thank you very much.
诺贝尔生物学他讲，
All right, we're gonna start in 5 minutes. Please take your seat.
Okay. Sam.
Please take your seats. We're gonna start in a few minutes. We're gonna start in 1 minute. Please take your seats. All right. Welcome again to our workshop on closing the loop between vision and language. So in this session, we have 2 speakers. So the first speaker is Kartak Nora Simhan. Kartak is an assistant professor in the computer science department at Princeton University and a co-director of the Princeton's NLP group. Kartak research spans the areas of natural language processing and reinforcement learning, with the goal of building intelligent agents that learns to operate in the world through both their own experience and leverage existing human knowledge. Kartak received his PhD from MIT in 2017 and spent a year as a visiting researcher at OpenAI, contributing to the GPT language model prior to joining Princeton. His research has been recognized by the NSF Career Award, research awards from Google and Amazon, a Bell Labs runner-up prize, and outstanding paper awards at EMNLP 2015 and 2016, and Europe's in 2022. So Kartak is going to talk to us today about language agents, machine that can read, think, and act. Please welcome Kartak.
Thank you, Jamal. Let me just, I guess, share screen. Can you hear me all right?
Yes.
Okay, awesome. Does this work? Okay, can you see the full screen?
Yes, we can.
So, all right, awesome. Hi everyone. It's great to be here, albeit virtually. So today's talk, I'm gonna briefly describe some of our efforts at developing these so-called language agents, and I sort of want you to keep in mind, ways that you can think about connecting vision to these kind of agents themselves. So all of you are probably aware of large language models. You're using them, right? And you know that they have basically crushed all NLP benchmarks, right? So we have these models that are very, very capable. And at the same time, it's not just NLP, right? So we have very, very, and I'm sure many of you in this workshop are working on things akin to this. We have very, very realistic generators that can just take a piece of text, and generate a very, very good piece of image, or vice versa, really have good understanding of images and be able to describe them in text. So this is great. We've seen all these advances and how LLMs are really contributing to them. But what I want to focus on in this talk is the idea that LLMs can also enhance autonomous agents in various ways. And so for this talk, I'm going to basically talk about several ideas, but the broader theme is going to be, how can we think about moving from language models that basically generate some form of text to more, a broader sense of language-enabled agents that can, interact with the environment and take decisions and do more for us as humans. So the broader field, of course, that many of you are also, pretty much involved in is the idea of language grounding, right? So this is not new, and there's been a ton of work over the last few decades. And the basic idea here is, getting machines to understand language, but understand it in the context of a particular environment. And there have been many, many different attempts, right? So you have dialogue systems, robotics, these sort of synthetic environments like game environments, or even things like visual navigation, which I'm sure many of you are working on. So language grounding is basically dealing with this idea of taking language understanding capabilities and putting them into agents that can take decisions. And just to start off with, right, I want to give you a sense for what most environments for language grounding fall into, right? So there's these practical environments that look at real world use cases, right? So think robotics, think task-oriented dialogue, visual dialogue, things like that. And these environments, while being very, very practical and directly applicable are not easily scalable because you have a lot of human involvement, right? Think about training your own robot. You need to be able to, handhold it and reset it every time. And at the same time, we have these scalable environments. These are environments where it's easier to collect data, easier to simulate these sort of environments, but it's not often connected to real use cases, right? So yes, you can maybe solve a particular game, but what does that mean? Do you actually have a grounded agent that can help you in some realistic task, right? So the sort of first question that we asked back in 2022 was, is there something in between, right? And if you think about it, right, there is, right? So if you think about the World Wide Web, which is basically a collection of websites and an interconnected network of these websites, it's actually a very, very interactive language and vision environment, right? So if you think about it, there's all these pages and you're navigating these as a human every single day. It's both practical as an environment to test out, autonomous agents, but at the same time, it's scalable, right? So you can train it on a particular set of websites and then, just scale it up to millions more if you want it. Right, so it's scalable because there's a large number of pages, transitions, and at the same time, if we can get any sort of agent that can operate on the web, we can leverage that for performing all sorts of tasks. And so this basically led us to the creation of a benchmark / environment for interactive agents that we called WebShop. Right? So what is WebShop? WebShop is basically a simulated shopping website. So think of, you go to Amazon.com, buy some stuff for yourself. Instead, we just basically recreated that into a simulated environment. And the task here is basically, given an instruction in natural language, the agent has to navigate through web pages and purchase an item with the desired requirements. So here's a sort of an example, as to how this episode would look like, right? So if let's say the human asks the agent, I'm looking for an extra large red color woman fur lined winter warm coat, and I want it under $70. The idea is, there's a sort of input into this language capable agent, and this interacts with this web shop or any shopping website environment, takes actions, gets back new web pages and so on. And then at the very end, chooses a product and then chooses the right attributes and make sure everything sort of satisfies the requirement. So once it then chooses, a product and clicks buy, just like how you would do, we have a mechanism where, we can basically provide a reward based on what the original set of required attributes were and what the attributes actually ended up with. So let me give you a sort of like more visual demonstration of what WebShop looks like. So you sort of also see the connection with vision and language. So here's the website we built, basically, right? So there's instructions, and then the agent types in some search query. It goes in, it sees all these, products available, and it has to basically navigate through these different web pages. And at some point, it has to decide a particular product. I guess now it's going back to search something else, right? So just like how you would, right? If your first query doesn't work out, you go back, try a different query. In this case, it's directly going for the fur coat. And then once it gets to a particular item that it thinks is good, right? So you sort of want to use the right set of attributes and then click buy. So as you can see, right, there's sort of several key features over here, right? So first of all, the website and the whole environment itself has realistic language and vision capability, right? So you have images just directly scraped from Amazon, as well as the text and all the reviews and so on, just directly from Amazon. So it's more realistic in those two modalities. It's also a scalable environment, as I'll show you a little bit in a bit how you can just easily scale it up to new domains. And it's also quite easy for us to collect data, right? So compare this to something like other kinds of environments where you're looking at having agents move around, right? So it's easy to just tell a human, hey, like I want you to shop for this particular product, and go ahead and collect this data. And so the last sort of thing is like it also allows us to evaluate quite robustly. I won't go into details about how exactly the reward function is crafted, but you can go ahead and read the paper to get a sense. So right, so what does this sort of bring us to? So we basically built this benchmark, and then we used sort of state-of-the-art language models at that time, basically BART and combinations of BERT along with ResNet to develop some agents that can basically perform the task, right? So this involves generating search queries, being able to select these different choices, and so on. And there's a bunch of things here, but basically just focus on the gray bar over here. That's a rule-based agent, right? So which gets less than a 50% score. And the other bars over here, if you see the dark blue, which is basically an agent that was trained with imitation learning, it uses human demonstrations, it's trained with imitation learning, and it's able to get a slightly better score, right? So, but you see sort of like there's a big gap between what the best human can do and what these agents can actually end up doing. So I just want to point out one quick thing that is actually relevant to folks that are attending this workshop. We use some basic models for processing the visual parts, especially, but we believe there's sort of like more to be done in terms of like actually utilizing the images in these products and so on to be able to more accurately define or decide which products to actually buy. Okay, so I want to show you one cool thing that we actually found, which also points to the scalability aspect that I mentioned before. So what we did here is we tried to evaluate whether these agents can actually perform sim to real transfer. By this, what I mean is, we basically train models on the web shop synthetic environment, and we basically built a wrapper over Amazon or eBay, live, and use these agents to directly interact with these websites online. And the overall, there's bars again, but like the overall result that we found is that it's actually quite promising. The difference between the performance on web shop and the actual websites themselves was negligible, or very, very small differences. And so that sort of gives some confidence that there's this nice into real transfer effect. So if you can sort of improve agents on these kind of environments, especially web shop, we would be able to deploy them directly, train them on these environments and deploy them directly on these websites. So this was this part is basically thinking about how we can enhance our environments, especially those that contain realistic language and vision parts, and use that towards building more capable agents. So sort of shifting gears, right? So we saw that web shop, we can use some of these models and we can get some performance. And then we started to ask this question: can we get LLMs or leverage them better to get these agents to act smarter, right? And let me sort of give you a prelude to what I'm going to talk about. So back in 2022, I'm sure you're all aware of this. There was this paper that came out from Wei et al. Talking about chain of thought prompting, right? And sort of the key idea here is that you don't just ask a language model to answer questions directly, but instead you ask it to also produce a reasoning trace, some sort of a thought trace about how to reason about the problem, and that seems to generally help increase the performance or accuracy of the model itself. So language models can help reason about a problem before giving you the answer. And at the same time, language models can also, produce function calls or produce actions directly. And this can help the models fit into sort of these modular architectures where they can help act in some sense, right? So there's this example of SafeCAN, which was released by the Google team, where you sort of have this language model interacting with a black box that includes the control and the perception parts. And what it's doing is basically, taking text observations, giving back sort of these text actions, and being able to drive a robot to do the right sort of things. And another example, of course, is just the web shop agent that I talked about. So we sort of have these two sides of the coin, right? So they can help reason, they can help act. And if you think about it, doing only one of the two has certain kinds of shortcomings, right? So if you have just a chain of thought sort of reasoning, the model can be prone to hallucinations, or error propagation, right? So if there's one step wrong in the reasoning process, it sort of goes haywire. And at the same time, if you think about just the models that produce actions without any extra reasoning, they can have insufficient generalization. They can be good on the environment that you trained, but this sort of lack of planning comes to the fore when you're testing it in a new or unseen kind of environment. So we thought about this, and we said, okay, why not sort of combine both of these, right? And this basically led us to the idea of React, right? So which is basically just saying, okay, let's just combine both the aspect of reasoning as well as acting into a single stream of thought, so that we can have language models take actions, get new information, but at the same time also reason about that information before taking the next decision or the next action, right? So it sort of provides this nice synergy, and this diagram shows you exactly what's happening with the language model itself, right? It's a very simple idea, right? And but at the same time, it has nice advantages. One being flexibility, right? We actually found that it's quite useful to have to sort of make diverse reasoning and decision making tasks. And at the same time, we found performance is better than doing one of the two. And interestingly, at the very end, I'll also show you an example where it can be used towards better alignment of these models, because they provide the loop provides some measure of interpretability and controllability. So what does React do itself? In a nutshell, the loop is pretty simple, right? Like I said, there's both aspects of reasoning and acting happening. So for each observation, you have some sort of historical context. It produces a thought, which is basically like how you would reason as a human, right? So think about what you have to do next, then produce an action. Just decide what you want to do next based on the entire context history and your reasoning, and then just provide this to the environment, which executes the action, gives you back the next observation, and basically repeat this, right? So it's basically saying, think before you leap or think before you do, and then use the new information and think about it in the entire context and continue doing this. So it's quite simple, and in order to train your React agent, there's these standard options that we can leverage, right? So we can do some sort of supervised fine tuning on a language model, or imitation learning, or use methods like reinforcement learning. We actually found that at least back in 22, there's more stuff in the pipeline. We actually found that in context learning with a few examples works quite well, and with sort of like we tested this with the state-of-the-art models then, PALM as well as GPT-3 on a bunch of different tasks, including multi-hop question answering, web interaction, games, and navigation. So let me just give you an example of how the task itself looks, so that you get a sense for what React is enabling. So in NLP, we have these question answering / fact verification tasks, so hotpot and fever, where usually you're provided with the relevant pieces of information, but we sort of consider this open domain setup where the relevant piece of information are sort of not provided to the agent, and the agent has to first go query, figure out where the relevant piece of information is, and then reason about them to provide the final answer. So in some sense, it's like how you would go and query Google or Wikipedia to find relevant knowledge before trying to answer a question. So I'll just show you a quick snapshot of how React actually helps, right? This was on 4 different environments, but things that might be closest to what you're working on are probably Alphaworld and Webshop. And we can see that, compared to just an acting only baseline that just takes actions, right? So if you just plug in the language model and use that to take actions in these kind of interactive environments, React actually does much better. So again, this is it results from the paper. Caveat that I want to add is there's been more work done after that, which has improved these numbers as well. But you sort of get the high level idea that we can use these language models to not only generate these actions, but reason about them more deeply before doing so. So let me show you this example of where React actually gives some measure of interpretability/controllability. So what we did was, this was in the Alf World environment, which is basically a text version clone of Alfred, which is the visual navigation environment. So what we found here was, React made some mistakes, right? The agent itself. We looked at one of these traces and see where it failed. And the nice part here is, you can identify exactly where it went wrong. There's this action 17 where it, I think it decided to find, it thought the keychain was in an incorrect place or something like that. So the nice part is, we can just go in and edit that particular action or that particular reasoning, and then rerun the whole agent from that standpoint, basically. And so this is interesting because it comes back to the whole idea of human in the loop interactive systems that can collaboratively solve problems, right? So imagine an agent that you're building for let's say visual navigation or something like that. You could sort of have a human sort of oversee the whole process and correct it or help it guide it in certain situations when it's stuck. Okay, great. So I just want to point out, there's tons of work that build on React. Some of this that you might have seen include frameworks like AutoGPT or LangChain, just more on the industry side. But there were more recent papers such as Reflection that uses the whole React idea, but then at the very end, you sort of also use a language model to evaluate its own trajectory. And that helps, provide some sort of pseudo reward, verbal pseudo reward that can help the agent improve on its own. Okay, so this sort of paradigm is generally interesting because it's using LLMs to sort of solve both the action and the reasoning problem. And then we sort of building on this, we ask the general question: okay, what about general problem solving, right? So if you're using LLMs to generate these reasoning traces and actions and so on, we're still using them in the sense of just one pass left to right decoding, right? So the model is just generating this full reasoning trace, and it doesn't really have a way to correct itself. There's no strategic look ahead. There's no sort of backtracking or anything like that. And once it sort of makes an error, it can really propagate all the way down the pipeline. So thinking about what might be good ways to solve this, we basically came up with this idea of that we're calling tree of thoughts. So basically think something like chain of thought, but just allow the LLM to have these extra capabilities about look ahead and backtracking and so on, so that naturally generalizes this idea of tree of thought, right? And so what tree of thoughts is doing over here is basically using LLM to suggest various paths of exploration, right? So there's a goal in mind for whatever task that you're doing. And the LLM basically can both help you explore by suggesting various paths, as well as evaluate which is the best choice that you can take in order to go towards to the goal, right? So just like classical AI search algorithms that you have, such as A-star or BFS and DFS and so on, but the high level idea is that you're sort of integrating the LLM as this guiding function, both in terms of deciding where to explore, as well as deciding which paths to exploit in some sense. So we found that this actually worked quite well. We had to come up with new tasks where models like GPT-4 didn't actually solve them out of the box, but we chose these strategic tasks such as the game of 24 or a crossword puzzle, where you actually need a lot of look ahead and sometimes backtracking in order to solve the task completely, right? And so here's an example of where you take a simple game like the game of 24, where the idea is you're given 4 numbers and you're trying to add in the operators such that they add up to 24. You can get quite a big boost if you just add this kind of searching exploration capability with this tree in mind, compared to just chain of thought or just input output prompting. Okay, so why am I telling you all this, right? So if you sort of see the evolution of these methods that I've been talking about, they lead to a broader high-level overview. And we actually, did this kind of survey slash framework building very, very recently. So this is a recent paper that we just put out on arXiv that we're calling Koala, or Cognitive Architectures for Language Agents. And so there's this broader theme emerging where, we think of LLMs as not just being language models, as not just being, models that generate text, but instead are part of a bigger architecture that can really power these agents, right? So to sort of give you a schematic overview, you can think of the LLMs as being these brain core structures that interact with different sensory inputs. This includes visual, speech, servo measurements, and so on, or sort of functional APIs, tools, and so on. And then they also have sort of these external knowledge sources as well as internal memories and data stores. So all of these different components, different modules that you have, and then the LLM is sort of this core in between, which can help sort of serve as a conduit between these different sort of modules, right? And so the sort of what I want to point out here is, there's a lot of these works that have especially been promising in the realm of dealing with language specific tasks. And I think there's a lot that could be done in connecting these language agents to the visual domain, and sort of closing this loop so that we can move them towards more realistic use cases and so on. So that's basically what I had. I'll leave some time for some questions, but just to summarize, language. I think language enabled agents are sort of the next evolution of language models. We already have examples where these agents can reason, think, and act to perform really complex sequences of decision making, and I think that's super exciting. And I especially think it's exciting to think about integrating visual perception into these agents more deeply, so that we can bring them closer to real world applications in both physical worlds like robotics and so on, as well as virtual worlds where you can think of these agents really helping us out on the internet and so on. So I'll stop here and take any questions. Thank you.
Thank you very much. Any questions? Hi, thank you. Thank you for the nice one. I had a question regarding your tree of thought. So the question is, you have to be more recent because the planning is which use Monte Carlo research and something like research would actually blend with the research of the business. Let's say kind of. I was just wondering how these are related with the tree of thought and specializations. So would it fall under the tree of thought, or would it be completely different? Or maybe more limited compared to the tree of thought framework?
I kind of can you just repeat the question, Gamal or Mohammed? It sort of broke out. Is it correct in understanding that you sort of want to compare how SECAN works versus Tree of Thoughts? Is that the question?
Not really. So I was talking about the more recent advancement on planning agents. So one of them is the Monte Carlo research algorithm. There's another one that uses the research over action space in relation to research over golden space for SECAN and K. So how would this compare with the tree of thought framework? Would tree of thought be a more general framework, or other frameworks more limited to this?
No, I think they're all going towards the same idea, right? So this is actually something that we talk about quite a bit in this paper, which you can sort of think as a combination of a survey as well as providing a blueprint. but they're all, going towards the same thing, in my opinion. Thinking about combining classical techniques in AI, around search, planning, reasoning, with just using the LLMs as these very, very nice, predictors in some sense, right? So actually, in this paper, we talk about we actually draw the parallel between LLMs and these the idea of production systems. If you're aware of these older AI/cognitive science ideas, where a production system is basically something that you think of, you have a set of inputs and it produces a set of outputs, right? And there's this function that is defined, which is called a production. And so a production is deterministic, but a language model in some sense is a stochastic production, right? So you feed it some kind of an input and it's giving you an output. And you can think of having a large memory bank of these productions, right? That can give you different inputs, given different outputs, given different inputs. And so all of these works, in my mind, are the way that we argue in this paper, are basically trying to develop a scaffolding around these language models, right? So you sort of have the language model over here that's taking decisions as to what to do next, but then you're retrieving different kinds of procedures, retrieving different kinds of things from your memory, but at the same time, you're reasoning over the observations that you're getting and so on from the external world. So I think they're all going towards the same direction. And this is exactly what we try to point out in the paper and, argue for having a universal / unified framework to think about and then develop these agents in the future.
So I have a question. So for basic derivatives, do you think approaches that use structuring the prompts are going to solve this problem completely, or do you need to change the control picture and other components? That's the ongoing story.
Sorry, can you repeat? Did you say whether prompts are enough?
Can you hear me now?
Yeah.
Yeah, so my question is about reasoning capabilities. My question is, do you think approaches that use structure in the prompts, like chain of thought, for example, solve this problem fundamentally? Or do you think we need to change the architecture for transformer components and have some missing components?
Oh, that's a good question, right? So I think sort of advances in both of these directions are probably going to help overall. I don't necessarily think, we still see, even with more structured, like chain of thought, tree of thought, you go down the line, right? Like the MCTS thing that somebody mentioned. All of these help provide the scaffold around the language models, but of course, if you improve the language model core itself, I'm sure the overall performance will improve. So I don't think it quite solves the problem completely. One can even go further and think about multi-agent versions of these, where you have different. There's several works coming out recently where you have these language models sort of interact with each other and so on. So I think, yeah, of course, there would be different. I think of these as like different components, and the stronger we make all of them, the better the overall system becomes.
Other questions? Okay, this
Okay, thank you.
So our last speaker today is Elaine Suhr. So Elaine is an assistant professor at UC Berkeley. Elaine received her PhD in computer science at Cornell University, and afterwards she spent a year in Seattle at the Allen Institute for AI as a young investigator on the Mosaic team. Elaine's research spanned natural language processing, machine learning, and computer vision. Elaine's research developed systems that use language to interact with people, example in collaborative interactions, and designing models and datasets that address and represent problems in language grounding. So please welcome Elaine. She's available online.
Can you see and hear me?
Yes.
Okay. Give me just 1 minute to share my screen. Can you see my screen now?
Yes, we can. Please go ahead.
Okay. Great. Okay, thank you. Okay, so today I'm going to talk about continual learning of language grounding systems from situated human-agent interaction. And in general, my research is focused on language as it is used in situated interactions with the broader goal of building learning natural language systems. These systems are systems that interact with users through natural language in these situated environments and continually learn through those interactions with their human users, with the end goal of building accessible and expressive interfaces to complex computing systems for non-experts. And that includes things like an interface to your phone or to a database or to an actual robot in a physical environment within some kind of complex scene. So to generalize this scenario a little bit, I want to define what I call the setting of collaborative interaction, where we have two agents that are acting in a shared world with a common goal. And the way that they actually complete this goal in the end is by using a natural language conversation. There are two language problems that are exposed in this scenario, both language understanding and language generation. So if we're building a language understanding agent, this system is going to map a user's utterance and the world state, which might include some kind of visual perception, as well as interaction history, to a series of actions that the agent's actually going to take in the environment. We can also consider the task of language generation, where we take this high-level goal of the interaction and the current world state, again, including potentially the visual perception and the interaction's history, to an utterance, which is then sent to the user. So a unique aspect of this collaborative scenario is that because we have these dynamics of a multi-turn interaction, we can study the dynamics that arise in a naturalistic two-person conversation. So for example, one of the phenomena that arises here is dynamic delegation, where as the user is interacting with the system, the user can adjust their language and their behavior to match the system's abilities. So here the user asks, can you take the pliers? And the robot just runs away to the corner of the room, which is obviously not what the user wants. But not all is lost in this scenario. Because we're in this multi-turn interaction, the user will probably just do something, will just do this task themselves and then maybe issue another task to the system, one that they know the system can complete. And what's really powerful about this kind of dynamic adaptation is that it really supports more streamlined collaboration, because instead of just completely terminating the interaction, our user and our system to some extent can recover from this error. But this kind of dynamic is only just one kind of adaptation that occurs within interaction that supports continual learning. So continual learning is really core to natural language use. We use explicit and implicit feedback to drive our own language learning. So for example, we might, as we're acquiring a new word, we might try it out in different contexts to refer to things that we haven't seen before, and then use some kind of implicit feedback from somebody who knows this word in how they're responding to our use of it in order to guide our word learning. But we also expect our human interlocutors to adapt their language use to our behavior via feedback that we give. So for example, I might be giving some kind of back channel feedback, like nodding or saying "aha" as I'm listening to somebody, or maybe the facial expression that I'm providing is providing some kind of implicit feedback on whether I'm understanding what they're saying. But in general, systems that can transform these kind of very naturalistic feedback cues that we're used to giving and receiving in conversation into learning signals will both support better collaboration with human users, but also learn really efficiently, because they'll be making the most of the kind of naturalistic feedback cues that people will give in interaction. So let's take a look at what this feedback might look like in a human-agent interaction. We might have different kinds of explicit feedback. For example, here the user is providing this instruction, hold this for a second. And as the system's moving towards the pliers, it's getting some positive feedback, either in the form of like explicit, maybe thumbs up, or maybe some kind of verbal feedback like, oh, great, thank you. But then if the system runs away with these pliers, it's going to get some negative feedback. So this is more explicitly aligned to what the user has instructed the agent to do. But we also might have different kinds of implicit feedback that arise in these scenarios. So here the system has an intent in this collaboration, which is it wants the user to bring it a hammer, but it erroneously maps this to an instruction of bring me a saw. Now our user, who really wants to collaborate with this agent because they share the same goal, will bring a saw to the agent, right? Now this isn't what the intent originally was. And because of that discrepancy, the system can derive a learning signal. And in fact, it can derive two learning signals. The first is that it probably didn't verbalize this intent correctly because the user did something different than the intent. But not just that, the user's actions actually align more closely with the instruction that was actually sent, bring me a saw, than the original intent. So this is also a positive signal of what the actual meaning of the generated instruction might be. So to summarize this scenario, in these collaborative situated interactions, we have two agents. They're acting in this shared world, and they're acting towards a common goal, and they use language to coordinate their actions. So again, we can study two language problems, language generation and understanding. We have these nice dynamic aspects that support more streamlined collaboration. And then we have a lot of opportunities for continually learning and improving these agents through human agent interaction. So today I'm going to instantiate this scenario in Serial Bar, which is a situated collaborative environment with sequential natural language instruction. In this environment, we have two agents acting in this shared world. This world contains a lot of different props for the agents to refer to, like we have a windmill, we have a house and a tree, a tent, another house, and some plants. There's different kinds of terrain, so the systems don't just reason about their perception, but also their actions and the affordances of the environment. So they can traverse the grass here or the path, but they cannot walk on the water or the mountain. There's also a variety of colorful cards scattered around the board. So we have two agents with distinct roles. The leader is responsible for planning how the two agents are going to accomplish their shared goal in the environment. This leader is responsible for dividing that plan into what they should do and what the follower should do, executing their part of the plan, and then describing what the follower should do in a natural language instruction. And they send the instruction in this command box here. Now, the follower's role is to just follow instructions to the best of their ability with respect to their perception and whatever the instruction was. The shared objective of the two agents is to pick up matching sets of cards where each set has 3 cards with distinct color, shape, and count across the cards. If you've ever played the card game Set, it's loosely based off of those roles. So in this particular board, maybe the plan that I would make as the leader is to first select this 2 pink stripe card because it's nearby me, then the 3 red triangle card because it's close to the follower, and then perhaps the last thing that might fit here that's relatively close to the follower is this orange square card. And this makes a valid set because we have 3 different cards with 3 different colors, shapes, and counts. And if we were to select these cards, we would earn a point. And this measure of this point accrual over time throughout our interaction is a rough measure of task completion. So we earn points for every valid set we accomplish, and then the final score after our interaction is a measure of how well we collaborated. And crucially, we designed this environment to require language in order to collaborate. So we really bottleneck the collaboration between the two agents such that they have to use language generation and language understanding in order to succeed. The leader writes instructions to the follower, and the follower follows those instructions, and they communicate through this command box here. But we also design multiple mechanisms that further encourage and require collaboration between the two agents. So for example, we allow the leader to see the entire view of the game board, but the follower only sees this first person restricted view. You can see it in the bottom right-hand corner here. This encourages the follower to follow instructions as closely as possible. So if they go off and start selecting cards that were not mentioned by the leader, that's at best just going to waste the limited number of moves that they share. But at worst, it's going to completely mess up the leader's plan, and they're really going to lose an opportunity to earn a point. But this restriction and this difference between the two agents here allows or encourages the leader to write instructions that are actually followable by the follower. So if I want my follower to get this 3 red triangle card, it's actually facing the opposite direction right now. So my instruction is going to have to tell it to turn around in order to actually see this card. So the other mechanism that we design is a capability gap where the follower can take more steps per turn than the leader. And this, first of all, encourages the leader to make use of the follower as a partner. It's almost impossible to earn more than 1 point in this game as a leader by yourself. So if you just move and you don't tell the follower to do anything, you're not going to earn a high score. But it also really encourages leaders to write high quality instructions to make the most of that communication channel. And in particular, because the follower can move farther, it encourages, when the leader's deciding who should do what, to give longer and more complex paths to the follower. Okay, so I'm going to show you just a quick demo of this environment and a collaboration with one of these agents. So this is an instruction following agent. It's going to map my instructions and its visual observations to actions in this environment. Okay, so first thing I'm going to do as the leader is pick up this 2 pink stripe card. I'm not going to do anything else as the leader. I'm not going to move around anymore, just because we're only going to pick up 1 set today. I'm going to write 2 instructions for the 2 cards that I want my follower to pick up. So turn around and get the red triangles next to the mountain, and then get the orange card. Okay, so I'm going to end my turn and let the follower move. You can pay attention to it moving here, or also in the bottom right-hand corner, you can see its actual first-person perspective. So the follower is turning around, and now it can see the red triangle card, which is great. It is selecting the red triangles, but oh no, there's actually a card hidden here that I didn't notice that's orange. It has an orange triangle. And I didn't notice it because it's kind of occluded here by the mountain and this tree. So this was a mistake, and it's my fault as the leader. But because we're in this live interaction, we can recover from this mistake. We just lost a few extra turns or extra steps. So I'm going to write 2 more instructions for the 2 cards that we now have to fix. So the first one is deselect the card you are standing on. And then I'm also going to tell it to get the other orange square. Turn left and get the orange square past the windmill. So I'm going to end my turn again. Hopefully we can recover from this. So now the follower is deselecting. Okay, it's deselecting the orange triangle card, which is good. It also reselected the red triangles after unselecting them. And now it's going to the left of the windmill, going past the windmill, and then successfully picked up this orange square card. Okay, so we earned 1 point, and that's great. Okay. So moving on. So serial bar, again, is an instantiation of this collaborative situated interaction setting. So we have these 2 agents, a leader and a follower, acting in this shared world towards their goal of picking up sets of cards, and they use natural language instructions to coordinate. So we can study 2 language problems here. The first is instruction generation. So where we take an intent and we map that to some kind of natural language instruction that a human user might, or a human partner might map down to actions. But we can also study the problem of language understanding, which is instruction following, where we take an instruction and we expect our model, which was the model that I just showed you, to map that down to actions given its model of the world so far. Again, we have these nice aspects of dynamics, for example, where as the leader, I could recover from my mistake by issuing a couple more instructions. And we have a lot of opportunities for continual learning. So what I'm going to focus on for the rest of my talk is how we trained the model that you just saw with explicit human feedback provided during human agent interactions. There's also opportunities for implicit feedback. I'm also going to briefly highlight this too, which you actually just saw an example of as well. Because the follower made this mistake, well, actually the follower didn't make the mistake. Because the follower did something that I didn't expect or wasn't my intent, maybe I can learn from that as the leader. For example, that my instruction was just too vague and I should be a bit more specific next time. Okay, so now I want to move on to talk about how we can actually do continual learning in human agent interactions in this setting, focusing on the task of learning to follow instructions. And this work will appear at NeurIPS in December. So our goal here is to learn and improve language use through live interactions with human users. Our task is instruction following. It's exactly the same task you just saw the agent take. So we want it to map a user written instruction and a series of environment observations to a series of actions. The training setup here is we're going to acquire binary feedback from the human users as they're observing their instructions being executed. So we place a person in interaction with our agent, ask the person to write whatever instructions they want to accomplish the high-level goal of picking up sets of cards, and then we run inference on our model to get these actions and then get feedback from the users. And our approach here is to cast this as a contextual bandit learning problem for learning. So we designed a feedback mechanism within the environment to allow users to provide both positive and negative feedback at any point in time as the follower is moving around. So they can use either the buttons, the physical buttons on the GUI, or they can use hotkeys on their keyboard. This is a really easy and intuitive way for the users to provide feedback. As the model is taking actions, the users aren't actually doing anything anyway because it's a turn-based environment. So it's really flexible. It's not disruptive to the environment. And so this is the kind of feedback that we're going to learn from in the end. So what does this look like? Let's say I wrote an instruction, move forward and slightly to your right until you see a card with 2 black squares, pick it up. So here is the follower behind this yellow tree. When their turn starts, they will take some actions. So sample from their policy and execute the actions. And then the user will provide some feedback potentially as the model is executing actions. So here, because the model turned right to face this orange star card, it receives a negative feedback because it looks like it's going to select this orange star card. So as the agent continues to execute actions, the leader continues to provide this feedback in real time. So the data that we learn from for once we actually have this agent deployed in the interaction is that for every action that we actually execute, we have the original world state in which the action was executed. So this includes all of the objects that it could see from its first person perspective. For example, we have the instruction that the user wrote. We have the action that the agent executed, the probability according to the policy that generated that action. That's a sampling probability. We also have binary feedback associated with the action. That's coming from what the user provided in the live interaction. So our objective here for learning is just to maximize reward. And this forms a contextual bandit learning problem. And the gradient looks something like this, where we have the user's feedback times the gradient of the log probability according to the current policy. And we're training in an offline setting where we're deploying our model for a number of interactions with human users, collecting the data, and then we're training. And this actually creates a bit of a problem for learning. So if we're training on positive examples continually in this offline setting, we don't actually have a problem because our objective is going to behave like supervised learning. This F just becomes 1. But as we continue to train on these negative examples, we actually face another problem, which is that as we're pushing the probability of those negative examples down further and further, we are actually exploding the gradient because our log probability is getting infinitely large. So these negative examples dominate our gradient. And in order to address this, what we do is we borrow this technique from reinforcement learning and contextual bandit called inverse propensity scoring to add a coefficient to this gradient. Now, IPS or inverse propensity scoring is often used for debiasing estimates of returns in offline settings. And here it also helps us overcome this issue of the loss exploding because we have this term in the middle here, this is the IPS term. We have the probability according to the current policy divided by the original sampling probability. And so as these negative examples have a probability going further and further closer to 0, so the coefficient of this loss also gets closer and closer to 0. We also clip the value of this at 1 to avoid overfitting on the positive examples. So the high-level overview of learning here is that we're going to initialize our model with human-human data. So this is interactions collected between 2 pairs of actual people where one user provides instructions and another user is having gold standard demonstrations of those instructions. This is sort of the minimal amount of initialization that we need to get a decent policy to deploy in the first place. So the first place here for initialization is just supervised training. When we actually deploy the model in human agent interactions, we will sample actions from our policy. So our policy is determined by theta R here, where R is the number of rounds. So we're doing this in a circular process where we have a number of rounds of training and deployment. So we deploy this model, we collect some interactions, and again, we're conditioning on instructions that the user has written in these new interactions. So these are not instructions that we've not necessarily seen before. We use these interactions to collect some training data, aggregate it into a training data set, and then apply this contextual bandit training process to get new model parameters. So again, the experimental setup in general here is that we're initializing our model with about 450 Wizard of Oz or human-human interactions, almost 9,000 instructions in total. Our main evaluation metric is instruction execution accuracy. So for all of the instructions that the users have written, we want to see how well did the model actually follow those instructions. But what's really hard here is we don't have any gold standard demonstrations of the instructions that people have been writing on the fly in these new interactions, right? So what we need to do instead is collect human judgments post hoc for a subset of the instructions that were written. So here are some results. We trained and deployed our model for 11 rounds with about 250 to 350 interactions each. And on the top left, I'm showing this instruction execution accuracy, which was computed after these interactions just by sampling instructions from each of these interactions, as well as the agent's trajectories. And we see that the instruction task completion rate is continually increasing from about 67 to 82% accuracy. We also see that this really, really high level metric of collaboration success, which is the score, the number of points earned, is also improving significantly over time from 3.3 to 5.3 points. Now, there's actually a big confounder here. These 11 rounds took place over maybe 2 or 3 weeks of interaction with human users. And what the problem is that as the users are exposed to this agent, they're going to adapt their behavior because humans are very, very flexible at using language in the most effective way possible. So in order to understand how human adaptation might have affected these results, we also deployed the very, very first model. So this model was only trained on human-human data, no human agent interaction at all, alongside the final model, which was also trained on human agent data. So these two red dots are the exact same model parameters. The only difference is that there's been 11 rounds of adaptation that could have occurred in the human, on the human side, right? And what we see, and actually the other difference here is because we're sampling instructions for evaluation, the instructions themselves here are different that are being evaluated on. The policy is exactly the same because this is the exact same model. So we actually do see what appears to be an improvement over time from 67 to 70% accuracy, just because the users are providing different instructions. But that does not explain any of this other gap between this final model that we've trained on human agent interactions and the original model. When we look into how people are using language differently to take advantage of this maybe subpar initial model, they're simplifying the language that they use. They're only describing a single target card per instruction, for example, more often. We also asked users over time after each interaction their general impressions of the agent, like whether it completed all the tasks, whether it only did what was asked, or whether the execution was efficient. And we see that these are improving over time as well. I'm going to just very briefly highlight another work which appeared in Tackle in 2021, where we learned to generate instructions for human instruction followers using implicit feedback. So the task here is instruction generation, and our model will be generating instructions in live interactions with human followers and learn by observing how users are executing them. And the approach here is to compare the original system intent with what the user did to derive a bandit signal. So at a high level, our system uses a deterministic planner to decide the plan that the human follower should take, and then uses a neural network to map that plan and the current state of the world to an instruction. And as we get humans to follow these instructions, what we get for each instruction that we've generated is the original world state, the deterministic plan, the instruction that was sampled, the user's execution, and both of these things are just trajectories, so sequences of observed poses that the agent either intended or that the human actually took. And we also collect additional metadata about the instruction, like whether the user thought it was correct with respect to what they did or whether the instruction was grammatical. So we map this data to a reward, a binary reward. And the general intuition is that if the user did something equivalent to the original intent, then the instruction probably accurately conveyed that intent. But if the user did something else, then maybe the instruction doesn't describe the plan, but it probably describes the execution, what the user actually did. So in general, if the user thinks that the instruction is bad, we just apply a negative reward. If the user thinks the instruction is good, then we assume that what they did maps to what the instruction actually intended, or sorry, what the instruction, like the form actually says. But if we see that the plan and the execution are equivalent, then we can say that the instruction accurately communicates the plan, and we add another positive example here. And again, so the training data here just becomes the world state, some kind of pose sequence or trajectory, which is either from the original plan or the user's execution, an instruction, and a binary reward. And again, we now have a contextual bandit scenario. So training over 14 rounds of human agent interactions where we have human followers of agent generated instructions, we see significant improvements in task completion from about 45 to 79% accuracy. And we can measure this automatically because we can compare the user's trajectory to what the original plan was. So the overall conclusion is that this model is continually improving its ability to generate instructions that relay its original intent. So some future questions that I'm interested in looking at is that we only explored a couple of different kinds of feedback here, this binary positive negative feedback, as well as the implicit instruction following feedback. So what other kinds of feedback can we learn from? Language-based corrections, maybe the actual deviations from the predictions of user behavior, things like timing, gaze, and interruptions in more of a multi-turn bidirectional conversational setting. Another question is, how should we scale up these kind of experiments in a larger scale way? And I think that Karthik had mentioned some of the ways that we might be doing this nowadays. And another big problem, especially when it comes to these multimodal settings, is how do we actually know which part of the representational space is broken? Is it an error due to a misrepresentation of the agent's perception, its action space, or the actual language that it's encountering? Okay, thank you for listening, and I wanted to highlight my many collaborators on this work. And I'm happy to take questions, although I would like them to be repeated because I'm not sure if I can hear them from the room mics.
I have a question. So my question is, have you thought of some maybe slightly different framework where the follower can actively seek for feedback rather than just receive feedback? For example, in the case of like having instruction that's unclear, can the follower ask for clarification, for example?
Yeah, that's another really good. I mean, we haven't studied that, but I think that that's a very natural sort of extension of this work. Not only, I mean, it's a little bit difficult because it does require some kind of representation of uncertainty in the model, and it's unclear that neural networks are very good at reasoning about their own uncertainty. But there is some work, I believe, on Minecraft type instruction following settings where they do represent uncertainty in some kind of formal representation of like the instruction and the plan or whatever the agent should do. And then they use this to generate they use this to generate clarification questions. But the policy, I believe there is a bit more like, it's not sort of a like quote unquote emergent property of the interaction where the agent realizes like it would be best to ask for clarification in this setting. But yeah, it's a great direction for future work.
Thank you. Another question? Right? If not, let's say it again.
Thank you.
So this concludes our session. So we're going to start the panel in 5 minutes.
Move this, move this square back.
Maybe this. I think.
But is it actually possible?
Oh, no. No, I think it's not.
مش كده تاني مش خلاص مفتوح خلاص مفيش حاجة تانية
أصلا ممكن يكون في ناس
ما عملتش حاجة شلت اللي
I think it's hooked here. So you hook now. Just hook now. I can actually do this. Yeah. No, it's fine.
But we keep this leaving. قصدك نحط ترابيزه هنا؟
ممكن.
واحدة من دول. طب ممكن تعمل واحدة من دول.
Yes.
هنا جنب بعض.
ممكن هو لو طاولة واحدة في النص والكراسي حواليها.
ممكن تعمل ايه عن ترابيزتين معاك مش ترابيزة واحدة كفاية لما انا حواليها بالعكس مش عارف نلاقي مكان اوكي كده لو شلنا الترابيزه مثلا كده فضلنا مكان عايز كده ودي زيه كده فنفضل عايز نعملها ازاي كده وهي كده كده بالظبط ممكن كرسي تاني هنا وكرسي تاني هنا والاخير ده برضه زيه الترابيزه نفسها مش عايز ناخدها لو شكل كراسي عاوزين واحد بس يا جماعه طبعا واحد بس
انا همشي كل ساعه ولا همشي كل minutes ولا ممكن بس تحت
مش خلاص تمام
عادي نعسل هو ليش عليه جنب بروتين وليش عليه هو لما نحط عليه وزن بحيث هو السك حاجة لا لا هو ده
Elaine, can you hear us?
Yeah.
Yeah, we just had a round of introductions, so
Okay.
for the panelists, so it's your turn.
Oh, okay. I can't really hear anyone else.
Sir, yeah, maybe just a few words about yourself because we had a few new panelists has joined us.
Okay. Yeah, sure. Yeah, so I'm Elaine Soar. I'm a assistant professor at University of California, Berkeley. And my work is generally in language in interaction, which intersects a lot with language grounded in visual reasoning, or visual inputs and perception, as well as action. So that's a few words.
Okay, thank you all for being here today. So we have prepared some questions for our panelists. So thank you again for joining us. So this last couple of years has been a very exciting time in vision and language. And I just wanted to hear some of your opinions. What are some of the most exciting developments in this area? And how do you see vision and language research in the life in the next 5 to 10 years? Okay, I will go straight or the volunteer.
I mean, obviously, it's been a very exciting time. It's sort of, I'm coming out of another session right now where Alyosha was talking about his 2019 predictions about where effective research we should not be working on. In 2019, he specifically said we shouldn't be working on anything related to vision and language because vision is just not ready for anything to do with it. It turns out that that was pretty wrong. There's quite a lot that vision can gain from this happening. Really interesting data associated with this. Okay, so it's great. So it's been very exciting. We have a lot of models that are doing very well, and they're being used all over the place. Clip models nowadays are everywhere, used for all kinds of tasks, including embodied AI tasks, things that it wasn't even trained to do. So its impact's been quite large. But at the same time, we don't really know exactly how to feed in visual representations into language representations. We don't have a good sort of way of measuring how these representations should be jointly represented within a unified space. If you look at work coming out of James Zhao's lab, it seems like the two representations are very separate. There's no similar axes along which they sort of correlate at all. And there isn't much structure that can really extract from those data. There's still a lot of work in terms of figuring out how these can be fused, how you and also years. Also, we haven't really figured out how to do this properly for 3D and language or for video and language. So I think those are going to be some big directions. Yeah, so I think I was working on video language with my PhD. So we are working on the VQA was my first project. And also after that, captioning and dialogue stuff. So it's really I think the big time, right? Our authority are coming out and actually changed my mind. So although earlier I was working on this kind of Bluebird stuff, which we are trying to scale at least back like level kind of like data, but we never exceeding to like a few billion of images. And then suddenly it became like 300 or now eating or even more. So I think what makes me feel really one thing is that that especially everybody was all in this space, which is great, but also this training like Google, OpenAI, they're getting more and more
like really large models, more data, better data. But then like all of these projects is going to be more close to the candidate world. So I think one thing is to closing once we want to evaluate, we need to really having this model, right, or open source version of the model. And I think this is one of the effort which I'm trying to do a little bit, which is kind of can be developing this kind of model, like maybe not at large scale, but even smaller that has decent performance, but was able to further being like used by the academia. And I think that's going to be one thing I think maybe making a little bit step towards better vision language model on the academic space.
I mean, maybe two comments from me. I think I'm thinking about two actors in this space. I think on the one hand, it's like really impressive to see this model that Jason and others have developed. I think on the one hand, I really like to understand them much better, sort of understand them, how they're working, can we make them more reliable so whatever fiction comes out, we actually can trust, and we're far away from that. But another, I'm also a bit scared about this large model, what they burn so with respect to energy and with respect to how much resources they need to actually build stuff. I mean, I'm not saying I don't want to train those models, but if everyone in this conference and wants to train those models, which need hundreds and thousands of GPUs, that's really not scalable. And if every company wants to do the same thing, then it's even less scalable. So also something to check it out.
So sorry.
Elaine, can you hear us? Did you?
Yeah, I can hear the panelists. I don't know if you can hear me.
Do you wanna share your thoughts on the state of the art of this area? Yeah, please.
Okay, so sure. So one of the things that I'm particularly excited about are these more modular systems for doing joint vision language reasoning. There's been a number of papers that have come out in the last year, one of which was from AI2, CVPR Best Paper Award. There was also another work from Berkeley at ACL, I believe. Basically, the basic idea is, you have this large language model that can, to some extent, map down from some kind of language to some kind of formal representation, often code, with reference to traditional like computer vision tasks like bounding box detection, things like that, in order to do more modular and compositional reasoning on top of the images. And I like these models a lot. I think they're very appealing from an interpretability perspective, as well as just, it's easier to identify what's going wrong with the model. I think one of the things that in terms of the state of the art that I find both in language and then also in vision is just the ability to represent really, really long tail concepts. So something that I've been particularly interested in recently is like the flexibility of spatial language and how context dependent it is, and how we can just sort of apply spatial references and relations to objects that we might not have ever seen before in completely new configurations. So humans are super flexible at using this kind of visually grounded language. So it's unclear to me just how well scale can be used in terms of data to represent these super long tail concepts, especially when they're used in completely new scenarios we've never seen before. So I'm excited about studying like more directly these lower level problems of few shot or zero shot learning of completely new uses of things like visual or spatial language. So those are some of the things I've been thinking about recently.
Thank you for all your thoughts. So I would like to also ask the audience if you have any questions. You have any questions? Okay. If you have questions, raise your hand.
他们家不好吃吧？太贵，不能去那家。那家因为 价格高一点，而且味道我感觉还不如我，而且肉少一半，是吧？你交了税也没这边贵啊，交了税这边也不便宜的呀。
我这个看那个上面甚至有中文，
都有中文的这边，越南餐厅都有中文，专门老板都中国人。
Sorry, can you mute yourself? Everyone on Zoom, please make sure you are muted.
那他们的 workshop 怎么开到晚上去了？妈的，当地时间都6、7点了，对吧？在巴黎啊。6点，对他们对6点都该饭去了，他们还在开这个，拖的时间太长了。
I believe the question was about in academic settings, how do you go about addressing some of these issues? You want to make this?
I mean, I used to be in one of these big companies recently, but now I'm moved back to academia. But even then, I think it's quite interesting to think a bit of formalism, maybe what is the very mainstream and what is the thing already all the big companies are working on, because maybe not the right place to compete with. I mean, I would not start training one of these biggest language models in academia in most cases. I mean, maybe there's very exceptions, but then it's probably like 1 or 2 labs that are working into it. So we've got other problems, think about how can we have models on the GPU or in the CPU, how can we be much more efficient so we can run the model on our phone directly and everyone can have the personal assistant on their phone, think about reliability, think about trust, other computer aspects, or even think about something completely different. I mean, we now have been working with these transformers for a long time, but I mean, my bet is that we have the next computer architecture, maybe something more efficient, maybe something modular, which is correct. I think there's like lots of orthogonal directions in a very high direction space of search button. Industry is probably typically the one which makes sense to them, which is maybe making a lot of money, and they put a lot of money in that, but there's so many other interesting problems. And then you don't need to compete with the compute which can't be applied. I'm not saying that it's not valuable to do that, but I think there's so many other interesting problems. I just mentioned a few in that volume anymore.
Sure. I don't know about anything more necessarily than that. I think Mark was putting very well. There comes a lot of problems to work on. In terms of my group, we either tackle problems that we can solve in smaller scales, and you just leave it up to the companies to sort of scale it up and see if the same things hold. Or the other model that's worked very well is starting collaborations with a bunch of companies. Specifically, a case where we have a problem that we want to sort of see it through at scale, and they have the resources and they're willing to sort of partner up. And that's worked pretty well.
I can. So I also agree that actually I believe that most of the interesting problems and developments that has happened mainly in academia, think about for example the fusion model and all this the very recent advances in the field that happens mainly in academia. In terms of there are some problems that were data collected more, they just not possible. So for example, if you want to build a system that recognizes all like existing animals or something like that, it's estimated that there are more than close to 1 million animal species and about 7 million that are not yet discovered, right? So if you want to build a system that can vision LLM system that can discover and focus about what attributes are possible on these species to inform an experiment that then can confirm that this is a very low resource problem. I don't think this is a data at all. Another thing, we want to build systems that are, let's say, inclusive to as many cultures as possible. So think about Alexa, for example, and you ask that question, and then I respond very visually.
And maybe if my knowledge is like this, is maybe from India, right? So we need a system that can understand the variation of different cultures, and those are huge, right? Like hundreds of different backgrounds, right? And culture. And if you want to build technology that can and has many of those people, we cannot collect a lot of data for all of them. So in this case, we need systems that are very resource efficient, and this needs algorithmic advances that I think are best suited for academic development.
Thank you for the responses. So I guess for academia, I guess the different route we can take, focusing on more low resource tasks or trying to do more efficient modular approaches. I want to talk a little bit about, so many of you have worked on data sets, and data is actually very important for training multimodal models. But we've also found that one key for these large pre-trained models, and they just gather everything that they can get their hands on. And what do you think is some of the limitations of the existing vision and language data set, and how will you address it?
So yeah, that's a good question. So I think that's one of the main reasons why we participate want to participate in this conference and pose a challenge, because as I'm working on this field, collect for a scientific figure capturing document for like 2 years. And we have done trying so many different sort of vision model, but it turned out it doesn't work. So yeah, so kind of because nowadays most of the sort of vision model is mostly trained on natural image. Is very different from our domain of data. So that's why we want to participate and want to just increase attention from vision people. At least some people, some companies, they have resource, probably they can do build on our collective skill data set to build a new friction model. So yeah, so I think that's the one of the, and that's the questions. Data set. Okay, so yeah, I think that's So the question was, what was missing in large scale data sets and how we're sort of building them and stuff. There's quite a lot of things missing. And there's quite a lot of efforts today in trying to bridge some of these gaps. For example, the Datacom challenge, which is trying to identify the best subset of pre-training data for a lot of these vision language large scale models. That's a big sort of effort. And they're basically finding that a lot of images associated with text online usually have text that is not really even referencing any of the content in the image, and training with that doesn't necessarily tell it. So figuring out the optimal subset of data to train on seems vital. There's also a need for better sort of video and language data sets. I think Jitendra has a paper that's out very recently where they're trying to figure out how many frames you actually need to be able to solve a video question answering data set. And for majority of them, you need 1 frame. So it's not really a video kind of task. So moving outside of vision language, there's a whole host of problems in video language and other sort of language and some other vision kind of modality, which is completely left unexplored or very, very explored.
Yeah. So, sorry. So some cursory looking at data sets like Lion, for example, I've seen the same thing where the language doesn't match up with the text, and it crucially doesn't require reasoning, not only, I mean, at the basic level of the objects in the image, but what I'm interested in these days, which is like relationships between objects in the image are very, very rarely actually mentioned, or things like describing motion or action that takes place in the images. So I think the images themselves are also tend to be less interesting, perhaps. Again, doing these searches, a lot of it is like ad copy, you know, so these images were scraped from websites that are like trying to sell a product or something like that. So I think that's one thing that's definitely missing. And I think there's, yeah, oh, okay. So I was gonna mention that like, there's some interesting work coming from Stanford and Elisa Kreis, who's starting, I believe, at UCLA as faculty next year on image descriptions, and sort of looking more at image captioning as this task of describing an image for accessibility reasons versus communicating something auxiliary to an image. And I actually don't remember where their data might be coming from, but it is an interesting perspective of like, if we're collecting data from the web where you just have captions of arbitrary images, first of all, you have a selection bias of what the images are. And again, they tend to be like product photos, at least in my cursory searches, but also like, you're not getting the intent, like the image descriptions and captions that exist are not necessarily communicating what we care about. I don't know exactly what the solution is. I'm excited about data sets that look at like YouTube videos or movie audio descriptions or something like Ego4D, although these kind of data sets do require, especially Ego4D, require like lower level annotation of like narration on top of the videos that are being collected. But the reason I like them is they're a lot more naturalistic. They show you the kind of things that our systems will need to perceive in the real world, just because this data, like the video data, does exist online because someone wants to present something in a video format. Just some thoughts, yeah.
I think I agree with Renji, and so I'm taking a little bit different perspective. I feel like we have a lot of data. So the problem is that if we refer vision language, we always assume that it has a language output, right? So if we are kind of say what it will be more on the output space, then suddenly we are unlocking a lot of new data. And we are actually trying to create an instant tuning data set for our model. And then it's surprising me that there's a new data set coming out every day. So if you're trying to keep pace, it's really, really hard. Also, we don't have that much people working on helping us to create this data set. So the quality is definitely one of the problems. But I think one of the fundamental things is that we don't have a way, like NLP runs everything can represent token, so they can tune everything very easily. So in our case, it's really hard. We didn't really figure out a way that how to make a specialized model. Maybe it's not even worth doing that, or maybe we can have specific coders to doing this. But then, like, how can they ensemble this data together, right? And like, I think this is going to be a problem. But the data set itself, maybe there is a bunch of them. And the second thing is that one thing that more video, right? So there's going to take a lot of steps. And how can we store them, right? So otherwise, so even the cost of this video data is going to be huge. Don't consider it. So like there are more efficient ways to store this data instead of storing the frame or storing the representations. And I feel like if we are really finding a really high quality or like a large scale, then all of this is going to be a problem. How can we really making like this more rich?
Does anyone in the audience want to answer our question? Okay. Okay.
I have a very question on long-term reasoning for more cautious and reading about hour-long videos or something like that. It seems to me that it's quite a challenge. What do you think about the task of getting and the journey getting there? It's already a challenge for language. I'm not sure for want to process your videos, and probably this can be needed for some applications and creating of example sport games and some application.
Yeah, so for the long video reason, right? I think like the most closest we can see is the equal for the challenge, right? So this is the giving you a very long video and they are asking to retrieve for specific task. That's what more retrieve a key where you place them or something like that. So so video representations, I think that you can improve it from two aspects. So one is that we can finding more compact representations. And I think the second is also from the modeling side, right? So we can developing better memory models, right? So because you can memory things, but the memory will kind of lasting for a little time, and you can also retrieve it fast and you see things more often. I guess like we can improve on either like having a more compact representations that you can for example represent the whole brain with a lot of information with only one actor, then you can potentially have like have 3,000 tokens, and you can have a very, very long videos, like maybe in, and also we can develop more memory-based architectures that maybe in our brain, and then like that things can efficiently storing things and retrieving things that. So that's what I feel how stressing this.
I mean, maybe that's I think that's good stuff. Maybe more research needed in our representations and maybe how to build structures around that. Maybe collecting in this of my database kind of systems. Maybe other.
I think you propose something that the paper broken is kind of related to learning efficiency of visual input. I'm not sure if that's something that is.
Yeah, I mean, management drop an octave. I think that it's not. I think it's just more locally. I think that's not sufficiently large scale. I think wondering maybe I mean, I think that is a database style integration has been proposed and usually taken out for that is not valid. Because it's challenging to do these types of maybe hard decisions or maybe different memory kind of things.
So there's a few different ways that I think we're sort of trying to tackle video representation learning and listening. One of them is what Justin said, which is looking at compactness of representations. We're also trying to figure out if we can build models that are smaller, cheaper, that can process things faster, so that you don't need to. You can use the smaller, cheaper versions of things to be encode things, and then only keep around the parts that are necessary for whatever use case that we want to do. And those could look, and the way you keep things around could look something similar to a memory network. Or we can rethink how we design the RNNs for current generation of things, given everything we know for transformers, for what works with sequences. We redesign them so that we can still process long sequences of things, but not necessarily keep everything around across long time horizons.
Yeah, I think we have some students and young researchers here. So what advice would you give to the students and researchers who are interested in pursuing research or career in machine
learning? Have fun. Do things you enjoy. It doesn't really matter. As long as you're having fun, I think you're going to find good problems and find good solutions. I think that's sort of what matters at the end anyway. Overall, there's quite a lot of open problems, and a lot of them are not really talked about in industry. And unfortunately, the industry happens to be the loudest voice right now in this area. But there are a ton of problems out there, as Marcus was also saying, and you don't need a lot of compute to do any of them. And we're happy to chat, you know, if you're thinking about moving further direction, about how you can go about all this.
I definitely agree with Randy. So So I think yeah, definitely solving the problem we want to solve. I think with the time goes by, we will figure out more exciting problems to hear about. But also, although like we see the game, right? So it's like visual language is taking a lot, like this GPT-4, this Gemini, or maybe things coming. But I think now for putting that the research and industry, they are kind of having a separate like track. So in this way, is that really like and also a lot of open source things is really like Llama, right? So once Llama coming out, there's tons of papers coming, and tons of research like individual model abilities on that, and which doesn't really require a lot of compute. So I think in terms of the there are also a lot of important questions we ask in this field. Definitely not going to be like even it's dominated by the what we see in the NLP, but still we can see this. I think the open source will taking things back and trying to keeping the pace. And also because it's open source and like a lot of like new research problem will come in, and yeah, I think it's still for opportunities instead of dominated by the large.
So, Elaine, do you want to comment on this? Advice for students
Yeah.
for language?
Sure. I mean, my main advice is just to like be curious, and if you see something that's like particularly interesting, like some phenomenon that you're like, wow, I'm interested in how a person is doing this. Like, it's totally fine to like think about these more nuanced problems and really carefully study like how well our systems are doing on these things. So I don't know. I guess there's a lot of open questions to echo what has been said already, and just stay curious, because I think it's going to be very worthwhile to have a lot of curiosity on all the huge amounts of nuance and variation that comes with language and grounded language.
So it is a little bit passive. I don't know if so we started a little bit late, so I don't know if any of our panelists need to leave. If so, feel free. You want to say some last words?
Maybe you could do like one or two more questions and
Okay. Yeah.
that's my favorite.
Okay. So is there any question from the audience? Okay. We have one.
Sorry, I just am curious about this topic. Maybe it's a question before, I should know before, but in this visual language research, it's a kind of combination of vision models and the language models, and it feels, maybe I'm wrong, that mostly there's when you adapt some models to fine tuning the vision models. Like, what do you think that what in the vision language compared, what do you think what is the more performance boost, let's say, comes from when you're improving vision models or language models, or you're trying to better combine them with what do you think? Because we have ICCV, yeah, what is it more like coming from the NLP, from language model, or like from the vision model?
Thank you. So to summarize, I think the question is whether we think it's more important to be improving the vision model, language model, or both.
I mean, I think it depends. It's a bit task dependent. What kind of task you're trying to do? But in general, I think one has to look forward to the action that they have done, right? So I think just I think on both ends there's sort of limitations. I mean, in language it's much more difficult to. I mean, it's very easy to understand nouns and sort of the explicit meaning of words because it's already written there, so it's already defined by that. But like understanding much more complex parts of language are more difficult or very long context, so very While for extracting things out of images that have different challenges, every object looks different. So, object that would be required.
So I think what I feel like is that so the reason why we didn't see a lot of this for example improvements over language or maybe on vision side is because they really don't know what is they don't really have a benchmark that can really testing, for example, grounding. We are always talking about vision side, but what is the grounding means in language, right? So maybe their grounding means less hallucinations on some of the tasks, but will leave that task close to visual, like perception. So like maybe these tasks, maybe they're the benchmark that cannot really giving out a good testing result. So I think this is one thing that when we care about how vision improving language, that really whether we have a benchmark can testing that. So maybe we make it real. But yeah, this is one. The second thing I feel like is that when they are tuning enterprise, basically because they have enough knowledge learned by this pre-trained model, and they want to be more efficient. And that's why we are like unlocking. But there are ways like LoRa or something that we can actually tune the model pretty efficiently. But again, these things will be biased towards the task. Whatever you do, you will be biased. So there are going to be more efficient ways or better ways that can keeping the knowledge of your old language model while adapting to new model. So there are still very ongoing development, but whether they can figure out that way and then like that, things may be helpful on some of the downstream tasks. I guess that's what I think. It's one benchmark. Second is that how can you making these things when you join learning them, but bias.
Yeah, that's a bit about. So I know this is the vision and language workshop of closing the loop on vision and language. But we also talk about videos, and in videos, there's also other modalities such as audio. And I was kind of curious on what is your thought about, is vision language enough? Or do we need to go beyond vision language? And if so, where do we go? What do we need?
So interestingly enough, there's so many things that it's really hard to capture with language or talk about. So things like being able to express three-dimensional sort of geometric information about all the objects in an image. It's really hard to do with language. It's really hard to talk about in depth and any sort of continuous field that is variable at all. And so language gives you very little information about what's in an image. There's so much more. So we're really just capturing the bare bones of high-level semantics of what's in an image. So for everything else, we need other modalities, we need other ways of doing it. A lot of the work that Justin's doing with ICCV23, you mentioned it, is trying to capture all of that additional information. But aside from that, I think what's sort of missing in all of these sort of methods is what I talked about in my talk, which is really the user humans coming in and really sort of giving you the right kind of feedback you need. And all that has to be very task dependent. People only care about getting their own applications to work. And so grounding all of this work that we're doing in vision and language in real applications with putting them in front of real people and getting that feedback loop, trying to incorporate that information that's missing for unique specific sort of tasks, that's what's sort of going to drive the next few years.
Yeah, I mean, I think additionally, sort of on the sort of actuation robotics side, similar, I think it's also those things are very difficult to express with language. So again, we're talking about other modalities for certain kind of understanding. If you are to understand how to move the body, it will be very difficult to express that language, because language not necessarily the best means to do that. So I think for PDA understanding, for the more modalities. Similar for audio, it's very difficult to describe some kind of music with audio. You could describe it, but it's not really capture it.
Elaine, do you wanna add something? Okay. She left?
Oh, okay, so, okay. Just wanted to check, so I don't know if you want to answer another question or.
Probably one last one.
Hi, so Shiro from Masman Informatics. So I have a question regarding to like nowadays like this kind of popularity of your large language models. But what's your take on whether we still need symbolic recommendations? Because as we all know, like very long history in NLP, right, using symbolic recommendations. But what do you think? Like where is the role of these recommendations nowadays?
Where's the role of symbolic representation?
And maybe that's part where we should go. I think interesting that computers are very efficient in symbolic representations and computing symbolic representations, maybe of lots of math problems, and so trying to relearn them this in an implicit fashion and language models might be a more efficient way. So I think there have been initial works of that. But trying to combine this implicit representation, which we have in language models, but also in pure vision models, and then also in the joint models, combining them with more like explicit logical representations. Could be very beneficial to get like more accurate models, but also maybe a more efficient model. Both with learning, but also I think there's lots of interesting work there. I think there's initial works, but I think there's a lot of things to explore.
Quick thing to Mark's point. A good way to think about this is perhaps thinking about the kinds of tasks that people do. We still need a lot of additional symbolic reasoning to be able to do the kinds of things we care about. So take something as simple as multiplying 2 3-digit numbers. It's not something that we automatically know how to do immediately. I think there's some people who can, but most of us can immediately. And we develop tools. We develop tools like pens and papers, and develop methodology that allows us to break down these problems. And all of that is really just symbolic reasoning. And I imagine that we're also going to be developing a lot of tools that are going to be AI tools. Some of them will be vision language. Some of them will be something else. And we're just going to be putting those tools together to solve more and more complex, long-term kind of tasks. And so this notion that we're going to just have large models solve everything is probably not going to be true. And the role that neural symbolic reasoning will definitely play is in these more complex tasks and putting together all of these models as individual tools to solve really complex work.
So let's thank our panelists.
With that, I would like to thank also all the audience and the participation from all the speakers of the day, the engagement from all the audience, and also actually what shaped today's program is really everyone here. So the poster session, this fantastic project we get exposed to during the poster session, and all the contributions from the multiple teams on the challenge. So really, I really appreciate it for you being part of this program. So, and with that, I would like to conclude. Thank you very much.